Hi everyone. So now we are going to study about coding in communication system. So first we need to study source coding, and then next lecture will be based on channel coding. So now we will study source coding. So why we need to do the source coding? What is the meaning of source coding? Everything we will understand. Just have some patience. Okay. So let's just say there is a source S which is generating four symbols: S1, S2, S3 and S4. It is generating four symbols. Now what is the job of encoder? The job of encoder is to encode these symbols in the bit stream, right? So what it can do is that, let's just say S1 is given 0 0, S2 can be decoded as 0 1, S3 can be decoded as 1 0 and S4 can be decoded as 1 1. Now these bit stream will be fed to the line coder, right? So that process would happen. So this is what we have studied till now, that four symbols will be generated and those four symbols will be encoded by the encoder in this manner. If 5 symbols were generated, then you would require 3 bits, right? If 5 symbols were generated, S1, S2, S3, S4, S5, then you would require 3 bits, right? So all these things we already know. So this is something we already know, that source is generating 4 symbols, encoder will be encoding in this manner at 0 0, 0 1, 1 0 and 1 1. Let's just say these probabilities are also mentioned. The probability of S1 occurring is 0.3, probability of S2 occurring is 0.2, probability of S3 occurring is 0.4 and probability of S4 occurring is 0.1. What does that mean? That means if I am transmitting 10 symbols, that means 3 times S1 would occur, 3 times S1 would occur and 2 times S2 would occur. So order could be anything, right? First S1 can come, then S2 can come, then S3 can come twice. Basically S3 will be coming 4 times, S1 would be coming 3 times, S1 would be coming 3 times, S2 would be coming 2 times, S4 would be coming 1 time and then S3 would be coming 4 times. So S3 is coming for 4 times, S1 is coming for 1 time, S2 is coming for 2 times and S1 is coming for 3 times. So this is the scenario, right? And now I know that S1 is denoted by 0 0, S2 by 0 1, S3 by 1 0, S3 by 1 0, S1 by 0 0, S1 by 0 0, S2 by 0 1, S4 by 1 1, S3 by 1 0 and S3 by 1 0. So this is the bit stream that you will be sending. So basically you are sending 10 symbols and total bits, how much you are sending? 20 bits you are sending. You are sending 20 bits for 10 symbol. That means per symbol how much bits you are sending? Per symbol you are sending 2 bits. Per symbol 2 bits you are sending. So there is a word known as average code word length. What it is known as? Average code word length. So what is the average code word length you are using? Our average code word length is 2 bits per symbol. So one symbol is represented by 2 bits. But what is the information in this particular source? Like what is the information of the source? This is what I am asking. So can you calculate the average information in this source? So 0.3 log to 0.3 plus 0.2 log to 0.2 plus 0.4 log to 0.4 plus 0.1 log to 0.1 with a negative sign. So what answer I will be getting? I will be getting this answer. So the answer that you are getting is 1.46 bits per symbol. That means one symbol is carrying 1.84 bits of information. But to represent one symbol, how much bits you are using? You are using 2 bits. So basically you are having a 2 bit of information. Sorry, you are having an information of 1.84. You are having a information of 1.846 bits, but you are using 2 bits. It's like you are having a water of 1.84 liter, but to carry that water you need to use a glass of 2 liter. So how much redundancy is there? What is the redundancy or what is the efficiency? How will you find out the efficiency? How much efficient you are? So actual information is this much. But you are using 2 bits. So this is your efficiency. People usually mug up the formula that Hx by L. For L as well, there will be some formula, but we will not go by the formula. We are understanding it. That per symbol, the information is 1.846 bit, but I am using 2 bits to represent one particular symbol. So to transmit one symbol, I am using 2 bits, but actually one symbol is having this much of information only. That means this is my efficiency, right? This much efficient I am. So 1.846 divided by 2, what answer you will be getting? Point 846. So 92.3. So efficiency is 92.3%. And what will be the redundancy? There is something called redundancy. That is actually 1 minus neta. So 1 minus 0.923. So that is 0.077, or you can call it 7.7%. Right. So from here I got to know one thing, that there could be a better way of coding. Like this coding that you are doing 00011011, some better way could be there, because my target is to increase this efficiency. This would be my target. Okay. What is the word for this one? Efficiency. So basically, if I am sending information of 1.846 bits only per symbol, then why I am using 2 bits per symbol on an average? This is on an average. Although every symbol is represented by 2 bits, so you would say that on an average you are using 2 bits per symbol only. But something I can do, I can improve this efficiency for sure. So this idea I have got, and from here the concept of source coding came into action. So let's revise what we have studied. Source was generating these symbols. This is how we used to do the coding. So here as well I did the coding in the same manner. Now I was transmitting 10 symbols. That means S1 3 times, S2 this much time, S3 4 times, and S4 1 time. So for transmit this bit, this symbol, to transmit this information I am using 20 bits. That means to transmit one symbol I am using 2 bits. But one symbol is actually carrying the information of 1.846 bits only. That means there is a redundancy of 7.7%. So your target is to reduce this redundancy and increase this efficiency. How did I thought of it? How did I think of it? What I did, I made a plan. That sir, if I am transmitting 10 symbols, then mostly what is occurring? Sir, S3 is occurring, and then S1, and then S2, and then S4. So this is the scenario that sir, S3 is occurring the most time, then S2 is occurring, then S1 is occurring, and then S2 is occurring, and then S4 is occurring. Sir, this is the order. So S3 is coming for the most of the times. Now what is the target? Whenever you code, what is the target? The target is that all symbols should look different. What is the target? Target is that S1, S2, S3, S4, each of them should be looking different. They should be having different kind of face. Now you know that S3 would be occurring for the most of the time. So what I am doing is that I am assigning bit 0 to S3. Then S1 is occurring. So I am assigning bit 1 to S1. Then S2 is occurring. So S2 I am assigning as 0, 0, and S4 I am assigning as 1, 1. So this is the bit assignment I have done. Are all of them different? Yes, sir. Just hold on to just have some patience. If you are having some doubt, everything would be clear. I know that this coding is wrong. Why it is wrong, that I think that thing I need to prove. Okay. So this is how I did the coding. Why I gave 1 bit to S3? I gave 1 bit to S3 because it is occurring for the most of the time. Now S3 will occur here, S3 will again occur here, S3 will again occur here, S3 will again occur here. That means only 1 bit I need to use here. Then S2 is occurring, then S3 is occurring, then S1 is occurring. S1 is occurring for 3 times. S1, S1, S1. Now then S2 is occurring 2 times. 0, 0, 0, 0, and S4 is occurring 1 time. So 1, 1. So how many bits you are using? What do you think? How many bits you are using? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you are using 13 bits for 20 symbols. That means what will be your average code word length? Average code word length, that would be 13 by 20, right? Or you can say 6.5. right? 0.65, sorry, 0.65 bits per symbol. That means to represent one symbol, you are using only 0.65 bit. And what was your information? So information was 1.846 bit. 1.846 bit per symbol. That means one symbol is carrying an information of 1.846 bits. And you are using only 0.65 bits to represent that particular symbol. It's like you need to carry the water of 1.846 liter, but you are having a glass only of 0.65 liter. Will you be able to do it? But as of now, this is the scenario that is occurring. So basically, if you calculate here nita, you feel like that, sir, it would be, I need to carry the information of 1.846 bits. But for that, I am having this much of, I am using this much of bits. So what is my efficiency? Sir, it is coming out to be greater than 100%. That means I am a great scientist now, because I have made the efficiency greater than 100%. I need to transmit the information of 1.846 bits, but for transmitting that particular information, I am only using 0.65 bits. That means surely something you are doing wrong. Because if you feel like that, sir, I have achieved something pretty remarkable, that means you have done something wrong. What wrong you have done, we will see that. Okay, so surely there is something wrong that we need to see. But before that, let me tell you just one more thing, that every time you will not calculate this average code word length in this manner. How will you calculate? So let's see how will I calculate average code word length. So S1 is represented by 1 bit. What is the meaning of average code word length? That how many bits per symbol you are using. So symbol S1 is occurring with the probability of 0.3 and you are using only 1 bit, plus symbol S2 is occurring with the probability of 0.2 and you are using 2 bit for that, plus 10 symbols were there, no, some error I did here. 13 bit for 10 symbol, that's what I was thinking. 13 bit for 10 symbol, that means 1.3 bit per symbol. So just calculation error was there. Again, efficiency would be greater than 100% only. You are using 13 bits to transmit a 10 symbol, 13 bit for 10 symbol, that means per symbol you are using 1.3 bit. Information was 1.846 bits per symbol, that means efficiency is greater than 100%. So there is some error. What is the error that we will see? But as of now, I am telling you how to calculate the average code word length. Okay, what is the length? Average code word length, or what do we call it? What is the name? Yeah, average code word length only. So how do we calculate average code word length? So S1 is occurring with the probability of 0.3, you are using 1 bit. S2 is occurring with the probability of 0.2, you are using only 2 bit. S3 is occurring with the probability of 0.4, you are using 1 bit. Okay, and S4 is occurring with the probability of 0.1 and you are using 2 bits. So what answer you are getting? 0.7, 1.1, 1.3. So 1.3 bits per symbol. Sir, how this formula came, is that concept also clear to you? It is pretty simple thing, no? It is pretty obvious thing as well, that how this formula came, right? This formula is a pretty obvious thing as well. Number of bits multiply with the probability. Number of bits multiply with the probability. So here also the same thing is happening. 13 bits for 10 symbol, you are getting 1.3 only. What we need to find? Bits per symbol. Bits per symbol. So how many bits? 1 bit, 2 bit, 1 bit, 2 bit. Per symbol, that means probability. 0.3, 0.2, 0.4, 0.1. So this is how I am going to calculate average code word length from now onwards. Okay, well and good. So what we are getting, 1.3 bits per symbol, efficiency greater than 100%, that means there is something wrong. So this is what I have written. Efficiency is greater than 100%. Idea looks good, but it is not an optimal code. What is the issue behind that? Why it is not an optimal code? So let's check that out. So similar scenario is there. There is a source which is generating 4 symbols A, B, C, D. There is an encoder. Probability of occurrence of A, everything is written, right? Every single thing is written. I am saying that A, B, C, D. Who is occurring for the most of the time? Sir, C is occurring for the most of the time. So I am denoting it by 0, 0. Okay? Sorry, not 0, 0, only by 0. Because the number which is occurring, the symbol which is occurring for more times, that will be given lesser bits. the symbol which is occurring for more times, that will be given lesser bit, so that total bits are less. Here you can see that total bits are less. So what I would do, I will give 0 bit to C, and then A is occurring, so I will give 1 bit to A. Let's see for B what I have done. Yeah, so B I will give 0 0 and D I will give 1 1. Okay, so this is what I will do. Same example is there. Now let's just say from this communication system I want to transmit a message that is a bad cab. This message I want to transmit. That means this statement I want to transmit. So what I will be transmitting? Sir, A represented by 1, B represented by 0 0, again A represented by 1, again D represented by 1 1, then sir C represented by 0, then sir A represented by 1, and then B. So this is the bit stream that I will be transmitting. Over the channel, this is what I will be transmitting. I will assume that there is no noise present. No noise present, that means whatever that I am transmitting, 1 0 0 1 1 1, 1 0 0 1 1 1, 0 1 0 0, whatever that I am transmitting, the same bit has been received. Now this bit has to be decoded. Like there will be a decoder which needs to decode. Basically, if I am saying a bad cab and you are receiving 1 0 0 1 1 1, you will not be able to understand, right? So if I am saying a bad cab, you should listen a bad cab only. So now what your receiver is going to do? Receiver knows that A stands for bit 1, B stands for bit 0 0, C stands for bit 0, and D stands for bit 1 1. So what your receiver did? First he saw bit 1 is there. Bit 1 is there, that means A. Then what he saw? Bit 0. Does he know that I need to take 2 bits? No, he doesn't know that. What he saw? He saw bit 0. What he will do? Bit 0 is C. Again he saw bit 0. What is bit 0? Again he saw bit 1. What is bit 1? A. Again he saw 1. 1. A. A. Then he saw 0. C. A. C. C. I was saying a bad cab. What you are listening? A C C C A A C A C C. You are clicking on a bad cab. Your computer is typing A C C A A A C A C C. Will you be happy? Absolutely not. So that means you thought that, sir, it is a good transmission, but here you messed up. The receiver is not able to decode it. Someone will say that, sir, the same kind of error can happen in this analysis as well, in this way as well, in this one as well. No, it will not happen. Let's just say if I am transmitting this bit stream and the same bit stream is reaching to the receiver. So receiver will be working, taking 2 bits into action at a time. So first he will take 0 0 at a time, then he will take 0 1, then he will take 1 0. So it will take 2 bit at a time. But here what you will say? First 1 bit, then 2 bit, then 1 bit, then 1 bit, then 2 bit, 2 bit, 0 bit, 1 bit, 1 bit, 1 bit, 0 bit. What you will say? How your receiver would be working? The best case would be he would be working taking 1 bit at a time. Now other way could be that he is working taking 2 bit at a time. Let's just say he is taking 2 bit at a time. That means he will take 1 0. Now what is 1 0? 1 0 is nothing. Let's just say E is 1 0. So if E is 1 0, then he will read it as E. Next he is taking 0 1. What is 0 1? 0 1 is nothing. Let's just say F is 0 1. So if it is 0 1, he will take it as F. Then he will take 1 1. He will take it as D. Then he will take 0 1. What is 0 1? 0 1 is again F. And then 0 0, that is B. So you are saying a bad gap, but what you are receiving? E F D F B. So a bad gap is not completely being received. But if I had done the transmission in this manner, in what manner? A bad cab. A bad cab. So A is represented by bit 0 0, B is represented by bit 0 1, A again by 0 0, this is 1 1, C is 1 0, A is 0 0 and B is 0 1. Now what receiver will do? Receiver will take 2 bit at a time. You are transmitting 2 bit at a time, receiver is taking 2 bit at a time. So again it will take 0 0, then 0 1, 0 0, 1 1, 1 0, 0 0, 1 1. Right? So he is able to detect as well, like decoding is also done and encoding is also done. So that was the process that we used to follow in digital communication system, and we were solving problem with respect to that only. Right? All the questions we solved with respect to that kind of encoding only. Here our brain tried to think too much. The brain said that if I want to use lesser memory, if my memory size I want to reduce, that means the number of bits that I am sending, that should be reduced. Here you reduced it, but actually you got to know that transmission is done in a good manner, but you are not able to receive in a good manner. So you felt like that, sir, here everything is end. But everything was not an end here. Who came into action? Two scientists came into action, Shannon Fano and Huffman. So we will talk about them. But here you are feeling like, sir, now this method would not work. Whatever that I thought, this initial idea, that would not work. But what if I had done the coding in this manner? What I am saying, what if I had done the coding in this manner? Sir, how did you do this coding? I will tell you. Who gave this idea? Who gave this idea? Shannon Fano and Huffman gave this idea. I did not give this idea. You will also be able to do this coding. Just have some patience. But what if I had done the coding in this manner? Will I be able to receive correctly or not? So what I was transmitting, a bad cab. C is represented by bit 0, A is represented by 10, B is represented by 110, and D is represented by 111. So first you let me know what will be the average code word length here. You will see that, sir, it is worse than this one. Like, sir, this was better, 2 bits per symbol. So do you really think that this is bad? Let's just say, you remember the probabilities, no? Here also the case is same. Probability of transmission of A is 0.3. So these probabilities are same only. Probability of transmission of bit B is 0.2. Probability of transmission of C is 0.4. And probability of transmission of D is 0.1. Now you feel like that, sir, previously I was using only 2 bits, but you are using 3 bits here. So sir, it is not a good way of coding. Previously I was using, sir, 00, 01, 10, 11. This was my A, B, C, D. So total, sir, I was using 8 bits. Here what you are doing? 3, 3, 6, 7, 8, 9. 9 you are using. Sir, it is not good. It is good with respect to the probability. See the probability, no? See the probability. Let's just say if I transmit 10 symbols. What is the meaning of 10 symbols? That C would be occurring 4 times. A would be occurring 3 times. B would be occurring 2 times. And D would be occurring 1 time. C is denoted by 0, 0, 0, 0. A is denoted by 1, 0, 1, 0, 1, 0. B is denoted by 1, 1, 0, 1, 1, 0. And D is denoted by 1, 1, 1. Previously, in this case, you need to use 20 bits. Let's see how many bits I have to use here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 1 bit less. How many bits I have to use here? 90. So this is surely a better coding, but next task could be not just the better coding. Along with that, I should be able to receive as well. No? This was the best coding. This was the best possible coding you could have done, but you were not able to receive. So here I should be able to receive as well. So it is a better way of coding. Like basically 19 bits is used to transmit 10 symbols. That means what is my coding efficiency? 1.9 bit per symbol. Not coding efficiency, sorry. This is your code word length. So how would I find out a code word length? So for code word length, you gave me a simple formula. Not formula, you know the concept as well. That A is occurring for 0.3 times and you are using 2 bits for this one. B is occurring for 0.2 times and you are using 3 bits for this one. C is occurring for 0.4 times and you are using 1 bit for this one. And D is occurring for 0.1 time and you are using 3 bits for this one. 6, 6, 9, 4, 6, 6, 12, 16, 9, yeah, 1.9. So 1.9 bits per symbol. So efficiency is also good, right? What will be the efficiency? Surely it is not greater than 100%. If it is not greater than 100%, that means something good you have done. I did not do it. Who did it? Shannon Fano did it. Okay. So efficiency is also good, but major task would be received. Whether we are able to receive it or not. First, let's see the efficiency. Efficiency and everything is going good. Everything goes good. So surely we are having a better efficiency here. 97.15%. Right? But are we able to decode it or not? So at the receiver, whatever that I am sending, the same has been received. Now I need to see whether my receiver will be able to decode it or not. So first what he will see? 1 he will see. Can he see 1 anywhere? Receiver would know that C is 0, A is 10, B is 110, D is 111. So can he see 1 anywhere? No. So I will design my receiver in a manner that If you are not able to see any of these bits, if you are not able to see any of these symbols, that means you need to go to the next bit. So first he went to 1, he was not able to decode it, then he went to 1 0. 1 0, does he see it? Yes, it is A. So this is a different design. Surely here the design would be very easy. In this case, design would be very easy, because you will tell your decoder that at a time you need to take 2 bits. So decoder would be saying, okay, at a time I will take 2 bits, my job is done. But here the decoder design would be a bit complex. You will tell your decoder that first you will take 1 bit only. But if 1 bit is not matching, then you will take 2 bits. If 2 bits are not matching, then you will take 3 bits. If 3 bits are not matching, then you will take 4 bits. So this kind of design you can do. Surely you can do. Now someone will say that, sir, this kind of design I could have done in this one as well. Try doing it. First you will take 1 bit. Just as I took 1 bit, A is received. That's it. Okay. So A was correct only. Then what you said? First you take 1 bit. He took 1 bit. C is received. Wrong. Wrong has been received. No. So here decoder design would be nearly impossible. Not nearly impossible. It would be impossible only. You cannot design. Or someone will say that, sir, I will design in a manner that first you take 1 bit, then you take 2 bit, then you take 1 bit, then you take 3 bit, then you take 2 bit, then you take 1 bit. In that manner you cannot design. You design for a particular system, right? So here I can say I am doing a particular design. The design would say that first I will take only 1 bit. If 1 bit is not matching, then you will take 2 bit. If 2 bits are not matching, then you will take 3 bits. 3 bits are not matching, then you will take 4 bits. So this kind of design I have made. So first 1 bit was not matching, he took 2 bit. Then again 1 was received. 1 was matching? No. Then he took 2 bits. 1 1 was matching? No. Then he took 3 bits. 1 1 0 is matching? Yes. B. Again took 1 bit. 1 is matching? No. Then 1 0 is matching? Yes. 1 is matching? No. 1 1 is matching? No. 1 1 1 is matching? Yes. 0 is matching? Yes. 0 is directly matching. 1 is matching? No. 1 0 is matching? Yes. 1 is matching? No. 1 1 is matching? No. 1 1 0 is matching? Yes. A bad gap. You are able to receive it. So what do you think? What is the difference in this coding and in this coding? This code is prefix free code. What is the meaning of prefix free? That means whatever the code that you see here, they are not the prefix of any other code. That means what I mean to say is that C is code 0. So none of the code is starting from 0. A is 1 0, B is 1 1 0, D is 1 1 1. So none of the code is actually starting from 0. So your receiver will not have any problem. That if none of the code is not starting from 0, that means 1 bit I will not take. I will go to the other bit as well. Is that understandable to you? Here what is the issue? That A is 1. Along with that, D is also starting from 1. Is that clear to you? Right? Now someone would say that, sir, in place of 1 1 you write down 0 1. Then what would be the issue? This would be the issue. Because C is starting from 0, this is also starting from 0. Because they are having prefix of the other code. So you always have to use prefix free code. And in that prefix free code, your efficiency would go down less than 100% for sure. You can never have more than 100% efficiency in any way in any kind of industry. So whenever I design a prefix free code, always my efficiency would go lesser than 100% only. So if you are getting more than 100% efficiency, then surely there is something wrong that you should realize. Okay. So as of now, I will put 1 1 only because they are not a prefix free code. So here it is starting from 0. This is also starting from 0 only. So always you need to design prefix free code. Now what about 1 0? 1 0. Is there any code which is starting from 1 0? It is starting from 1 1. It is also starting from 1 1. So is there any code which is starting from 1 0? No. Is there any code which is starting from 1 1 0? This is starting from 1 1 1. So there is no code which is starting from 1 1 0. Is there any code which is starting from 1 1 1? No. There is no code which is starting from 1 1 1. Now just use your brain and let me know if I needed to write down symbol E, then how would I write it down? If I need to write down E here, that would be difficult for me to write down, because let's just say if I start from 0, then there is an issue. I cannot start from 0, so I will have to start from 1. Then next, what I will put, if I put 0, then there is an issue, because this is the problem. Next, let's just say if I put 1, 1 1, no issue till this point. Now if I put 0, then B will say I am having 1 1 0. If I put 1, then D will say I am having 1 1 1. So here E will not be represented. So basically we will see the method that how did you get this code. That method we will see. There is surely some method. That method was given by Shannon, Fenno and Huffman. So that method we will see. But as of now, in this 30 minutes of discussion, did you actually understand the meaning of source coding and why we are doing so? Usually source coding is started from Shannon, Fenno coding. Like people don't even understand what we are doing. But I hope now you have a clear idea that why we are studying this source coding and what was the real motive. So here we started from, this is something that we used to do. Now if I am doing the same thing, I am not getting any advantage. Here my efficiency was 92.3%. One more thing that we have understood, one term, that is average code word length. Will you be caring about the formula of efficiency too much? No. What is efficiency? That this much bits of information you are actually having and how much bits of information you are actually using. That's it. So you don't need to mug it up, hx by L, hx by L. I have seen like a lot of students remembering these formula. Hx by L, redundancy is 1 minus neta. Average code word length is some formula they will write down. Summation, pi, log 2xi, nothing. No formula, nothing. Just pure concept. What is the meaning of average code word length? That per symbol, how much bits you are using. So probability multiply with the number of bits used. Plus probability multiply with the number of bits used. This is how you can find out average code word length as well. Right? So here I thought of an idea that the symbol which is occurring for the more times, I would assign lesser bit to that particular symbol. So if I am assigning lesser bit to that particular symbol, then my efficiency is going above 100%, right? So there is some issue. The issue is that we are not able to decode the given message correctly. So transmitted message was not able to decode correctly. So I came up with this particular method, right? So this particular coding I came up with. So here my efficiency has also improved. Along with that, I am able to receive as well. So let's compare everything. So this was our scenario. This was our information. This was our uncertainty. So basically I need to transmit per symbol. I need to transmit this much of information. For the normal coding case, whatever the coding that we used to do, in that particular case, we were using 2 bits per symbol and our efficiency came out to be 92.3%. Then I put my brain. I used my brain. When I used my brain, there was some issue that efficiency was greater than 100%, but receiver was not able to decode perfectly. So this is of no use. Whatever that you thought, that is of no use apparently, but actually it gave you at least an idea. What idea it gave you? That the bit which is occurring for more time, you should assign lesser bit to that particular bit. Sorry, not bit, I should say the symbol. The symbol which is occurring for more time, you should be assigning lesser bits to that particular symbol, because that would be occurring more times, and if I am assigning lesser number of bits to that particular symbol, that means I would require lesser storage. My memory size will be less, right? Okay, so this was the scenario. This is also a decent way of coding, right? The whole digital communication system we studied on this manner only. That no matter whatever the probabilities are, there I used to say probability of symbol S1 transmission is some 0.3, probability of S2 transmission is this much, S3 transmission is this much. But there I never used to say that you can use 1 bit or 2 bit or 3 bit. If 4 symbols are there, you will use 2 bits. If 5 symbols are there, you will use 3 bits. If 6 symbols are there, you will use 3 bits. 7 symbols are there, you will use 3 bits. 8 symbols are there, 3 bits. 9 symbols, 4 bits. So this we used to study. But now something different we are trying to do, right? So that is known as source coding. And now the best way, this was the best way. Here everything got improved. What was our L? L we saw 1.9 bits per symbol, right? And efficiency came out to be 97.15. Okay, so receiver was able to decode perfectly as well. Efficiency was also good. Along with that, average code word length, which is associated with efficiency only, so that was also pretty good. Okay, and redundancy here, redundancy 2.84, 2.85, which was pretty obvious why I picked calculator. 100 minus 97.15, I did not do it with my brain, I picked the calculator. Okay, तो ये इफेक्ट पड़ा है भाई कैलकुलेटर का. Yeah, till this point you can, till this point means till today's date, you cannot achieve better than this efficiency for this particular code. For different codes you can achieve better efficiency for sure, but for this kind of coding, like basically if this is the scenario that you design a communication system where one symbol is having probability of 0.4, other is having 0.3, 0.2 and 0.1, you can never achieve more than this one, because Shannon, Fano and Huffman has said that. Okay, so when I use Shannon, Fano and Huffman coding, I got to know that the maximum efficiency ever I can achieve is 97.15. Lesser efficiency you can surely achieve. Okay, so let's talk about Shannon, Fano coding. So this is simply a method. Sir, how this method came into action? Sir, how he thought? Nothing. It is method and it is method only. So what is the first thing we need to do? We need to see the symbols. Symbols are A, B, C, D. We need to arrange them in a manner that at the highest level the most probability should come. That means first C should come, then A should come, then B should come, then D should come. Okay, have some patience, have some concentration. One example we will see. It might happen that in one example you are not able to understand. We will see another example as well. Okay, so have some patience. Don't read out this thing. What we need to do? We need to write down the corresponding probabilities now. 0.4, 0.3, 0.2 and 0.1. Now you need to break these probabilities in a manner that the summation of some probabilities, like basically you need to break the probabilities in half. Like summation of these probabilities, what is the summation of these probabilities? Sir, 0.6. What is this one? 0.4. So it is nearly half only. No? I cannot break in 0.5 and 0.5. If I was able to break in 0.5, 0.5, that would be the best possible case. So basically I need to break the probabilities in a manner that their difference is minimum. Now someone would have said that, sir, I will break it down in this manner. Here 0.7 and here 0.3. What is the difference here? 0.4. And previously 0.4, 0.6, what was the difference? 0.2. So which is better? This guy is better, right? This guy is better, no? So how will I break the probabilities? 0.4 one side and 0.4 one side and other side is this much. Okay, so this is how I have broken the probabilities. So kind of what you will say, these are two rooms, one room and this is the other room. In this room, 3 people are remaining. In this room, only 1 people is remaining. Okay. So now, since we have broken down the room, since we have made a line here, now upper side would be defined some bit, upper side would be given some bit and lower side would be given some bit. Let's just say upper side I am giving bit 0. So lower side I will give bit 1, 1, 1. I could have done the opposite as well. Upper side I could have given bit 0. Lower side I could have given bit 1, 1, 1 as well. Like other opposite thing I could have done, that upper side is given bit 1 and lower side is given bit 0, 0, 0. That also would be fine. There is no issue. So in this room only one guy is remaining. So now I will not look at this guy. In a room, if only one guy is remaining, I will not look at this particular room. Now I will be coming to this room. In this room, how many people are there? 3 people are there. So again I need to divide. I will divide in a manner that the probabilities are split in half. So how will I split it? 0.3 and 0.3. So how will I do the division? This is how I will do the division. So upper one could be assigned bit 0, lower one could be assigned bit 1. Now this guy is having its alone room, this guy is also having its alone room. Now these two guys, now there is only one way to break them down. This is the way. So upper bit gets 0, lower bit gets 1. So eventually everyone would be having their own room. Initially C got his own room, but in one room 3 guys were there. Now again you broke them down. This was having 0.3, this was also having 0.3. So upper was defined as bit 0, 0, then 1, 1. Then again you broke them down. Here this I should have made like this, right? Then again 1, 1 I was having. In one room I was having 2 students. Again I need to break them. If 2 students are there, the only way to break them is that something should come in between. So this should come in between. So what do you see here? C is represented by 0, A is represented by 1, 0, B is represented by 1, 1, 0 and D is represented by 1, 1, 1. Are we having the same code? Yes. So this is how we did the coding. What could be the other way? Again, write down the same things. Again, start breaking in the same manner. Again, start breaking in the same manner. So this is how I will break. First break. Now the upper one I am assigning as bit 1, lower one is 0, 0, 0. Then this is how it would be broken. Sir, upper one I am assigning as 1, lower one are 0, 0. Then sir, this is how it would be broken. Upper one 1, lower one 0, 0. So again, what is the scenario? C is as 1, A as 0, 1, B as 0, 0, 1, and D as 0, 0, 0. And you can check one thing, none of them is a prefix of the other code. Like this is starting from 1, but this is starting from 0. This is actually 0, 1. This is starting from 0, 0, or it is starting from 0, 0, 1. But this is starting from 0, 0, 0. Now no one will say that, sir, these are starting from 0, 0, 0 only. This is not an issue. What is the issue? Here the starting point is 0, 1. Like this code is 0, 1. So 0, 1 is not the prefix of any code. Starting point is not the issue. The whole code should not be the prefix of any other code. And why is that so? Because of the decoder. Because of the design of the decoder. So whole code is not the prefix of any other code. Whole code is not the prefix of any other code. Right? So this kind of coding we did. Well and good. Like it is not necessary that, sir, upper one is 1, then 0, 0. Now upper one would be 1 only. No, here also I can change. Are you able to understand this point, what I am saying? Shall I make another way, another example? So let me put them somewhere here. What I mean to say is that I could have done in this manner as well, that C, A, B, D again. Okay. These are 0 0.4, 0 0.3, 0 0.2, 0 0.1. I would break down in this manner that upper one is assigned bit 1. Now lower one would be assigned the same bits. Now if I break down the room, first I broke it here only. Now in one room only one guy is there. Now I will break down 0 0.3, 0 0.3. So previously upper one got 1, lower one got 0. Now what I will do? Upper one will get 0, lower ones can get 1. And then again I am changing. Like here upper one I am assigning 1 and lower one 0. So this is also a valid code. You can see that 1 is a prefix of anyone? No. 0, 0 is a prefix of anyone? No. 0, 1, 1 is a prefix of anyone? No. 0, 1, 0 is prefix of anyone? No. So this is also a valid code. But best thing is what? In all the cases, average code word length is same. In all these cases, average code word length is same, which will be 1.9. Because in all these cases, C is represented by 1 bit, A is represented by 2 bits, B is represented by 3 bits, and D is represented by 3 bits. So in the examination, they will actually never ask that what is the valid code here. C is represented by 1 or this thing they will never ask. They will directly ask you average code word length. Okay. So my matter of concern will not be that, sir, how my symbol will look like. The matter of concern would be that C will be having 1 bit, A will be having 2 bit, B will be having 3 bit, and D is having 3 bit. Then I will multiply with the corresponding probabilities, add them up, and I will get my average code word length. Okay. So how your symbol looks like, that is never a matter of concern. Well and good. And Shannon-Fano coding always takes care of one thing, that no code is the prefix of any other code. So this is the theory that has been written. I also never read the theory. Yeah, you can read the theory. Whatever that I have taught here, the same theory has been written here. So let's see a better example now. This example we are going to see. Okay. So x1, x2, x3, x4, x5, x6. You can see 6 symbols are there. We need to write them down in the descending order, that on the upper side x2 would come. Then what will come? Then your x1 will come. Then x6 will come. 0.3, 0.25, 0.20, then 0.12, and then x5, and then x4. Right? Now write down their corresponding probabilities. x3 is having 0.12, 0.05. Right? So you can see that here I will break down, because this is 0.55, 0.55, and this is your 0.45. Okay. So this is how I will break down. Let's say upper ones are given 0, 0, lower ones are given 1, 1, 1. Now here also you are having 2 rooms, and here you are having in one room, here you are having 2 people, and here you are having 4 people. So upper one also I need to divide and lower one also I need to divide. So first I will go to this room and I will divide them because I know that only one division is required here. Upper one gets 0, lower one gets 1. Now I will go to this room and I will see here this is 0.20, upper one is 0.20 and lower ones added are becoming 0.25, right? So here the gap is 0.05, and if I had done in this manner that I add both of them, so 0.32 and 0.13, that would be the higher gap. So how will I divide? I will divide in this manner. So upper one gets 0, lower one gets 1, 1, 1. Is that clear what I did? First I divided 0.55, 0.45, so 0, 0, 1, 1, 1, 1, 1. Now I see that on the upper room 2 guys are there, in the lower room 4 guys are there. So this also needs to be divided, no? So upper room should be divided and lower room should also be divided. So I went to the upper room, I will simply divide it, only 2 guys are there. So I will simply divide them, one is getting 0, other one is getting 1. Then I go to the lower room, there are 4 guys. This is having 0.2 and all of them combined is 0.25. So again I divide them, upper one gets 0, lower one gets 1, 1, 1. Now this guy is having its own room, this guy is having its own room, and this guy is having its own room. Now in one room these 3 guys are there, so again I need to divide. So 0.12 and this is 0.13. So again I did the division. This gets 0, this gets 1, 1. And now in this room only 2 guys are there, you divide them as well. Divide them as well. So this is how I have done the division. I hope you are able to understand. Like Halfman will be tougher than this one, okay? This is the easier one. Shannon-Fano is the easier one. But you have the practice, you will be able to write down. You would see in ISRO examination, these kind of questions are asked like a lot of time. In PSU examination as well. GATE did not ask it till this point, okay? GATE is not asking this Shannon-Fano coding or Halfman coding, but they can frame a good conceptual problem from here. Okay, not from here. If they don't want to ask this one, at least they can ask some good problem from here as well. Like intelligently they can frame something out of it and they can ask you, right? Because they know that people will be mugging this particular thing up, but they will not be focusing on the concept. So they can frame something good from the concept as well. But yeah, I hope this is clear to you. If it is not clear, then get back to the video again, watch it. Again, let me repeat. 0, 0, 1, 1, 1, 1, 1. 0.55, 0.45. Then in one room 2 guys are there, break them down, 0, 1. In one room 4 guys are there, break them down because this is 0.25, this is 0.20 and this is 0.25. So break them down, 0, 1, 1, 1, 1. Now 0.12, 0.13, so 0, 1, 1. And then simply break them 0, 1. So what you can see, x2 is represented by 0, 0, x1 is represented by 0, 1, x6 is represented by 1, 0, x3 is represented by 1, 1, 0, x5 is represented by 1, 1, 1, 0, and x4 is represented by 1, 1, 1, 1. And you can see that none of the code is prefix of the other code. 0, 0, none is starting. 0, 1, no one is starting. 1, 0, no one is starting. 1, 1, 1, 0, no one is starting. 1, 1, 1, 0, no one is starting. 1, 1, 1, 1, no one is starting. Hx you can calculate what will be that particular thing. 0.25 log to 0.25, 0.3 log to 0.3, 0.12 log to 0.12, 0.05 log to 0.05, 0.08 log to 0.08, 0.2 log to 0.2. Okay, and what will be the average code word length? So that would be 2 bits you are using with the probability of 0.25. 2 bits you are using with the probability of 0.3. x2 is having a probability of 0.3. So 2 bits you are using with the probability of 0.25 and 0.3 plus 2 bits you are using with the probability of 0.2 as well. 3 bits you are using with the probability of 0.12 and 4 bits you are using with the probability of 0.08. 4 bits you are using with the probability of 0.08 plus 4 bits you are using with the probability of 0.05. Okay. Zero 0.75 into 2. 0.75 into 2, that would be 1.5. 0.36 plus 0.52. .38. Okay, so you can do this calculation, you get a 2.38. 2.38 bits per symbol. A very good efficiency you are getting, right? You can see that information is 2.36 and I am using 2.38. So it would be nearly around 99% efficiency. So 2.36 divided by 2.38. Yeah, 99.15% efficiency you are having. And sometimes they can ask the redundancy as well, which would be represented by R. So that would be 0.85%. That much redundancy is there, right? So a very good efficiency you are getting. So this was your Shannon-Fano coding. One more problem we will solve, but after studying Huffman coding. So first let's study Huffman coding. Okay. So this is a bit complex. Okay, bit complex than the previous one. So have some patience. So what you need to do, again write down in this manner, right? At the upper part, highest would come, and then the lower than that this one. So basically in the descending order you need to arrange. Then last two probabilities you will add up. So when I add up last two probabilities, what I get? So 0.3 I get. Now what I am left with? 0.3, 0.3 and 0.4. Now I will make the order based on 0.4, 0.3 and 0.3. Now I know that 0.3 and 0.3 are equal. So I can write down this 0.3 here and this 0.3 here and this 0.4. I could have written down this 0.3, like this 0.3 could be written upward as well, because both are equal, no? So basically always I need to maintain the order that probabilities are written in descending order. Probabilities are written in descending order only. So let's just say if 0.1 and 0.2 plus 0.1 was 0.4, then this 0.4 would have gone above 0.3. We will see that example, don't worry. Are you able to understand this point, what I am saying? Right? So I need to make sure that this order is maintained. Now again, I will add two lowermost probabilities. Now what do you see? 0.3 added with 0.3. What you get? 0.6. But this 0.6 is greater than 0.4. So what will happen now? This 0.6 will go above 0.4. So previously what happened? Here you see this 0.4 came here only, this 0.3 came here only, these two are added. Now this has gone above and this will come down. This is not 0.4, this is actually 0.6 and this will come down, and then again both of them will be added. Again both of them will be added. So whenever you are adding up, so forget about this one, whenever you are adding up, what you will do, you will assign 1 0, 1 here, 0 here, 1 here, 0 here, 1 here, 0 here. Whenever I am adding up, that's it. It's not that sir I will assign 1 here, no. Whenever I am adding up, I will assign 1 0, 1 0, 1 0. Is that clear to you? You can assign 0 1 as well, like 0 1 0 1 doesn't matter. One guy would be getting bit 1, other guy would be getting bit 0. Bit 1, bit 0, bit 1, bit 0. Have you studied binary search tree? Like anytime if you have studied DSA someday, then this kind of mechanism only you do when we talk about binary search tree, right? So forget about DSA. Even I am not comfortable with that, right? So let's talk about C now. So how C will be represented? So what we need to do, we need to go from C to till the end. So if I am walking from C, am I encountering any bit? No. Here I encounter some bit. What is that? That bit is 0. So when I walked from C to till the end, I encountered only one bit, that was 0. So C is represented by bit 0. Now when I am, let's talk about A. So when I am walking from A to till the end, so A, then this A goes upward and then this one. So I am encountering 1 1. So always in the reverse order I need to write down 1 1. Okay, in the reverse order 1 1. B. B2 till the end I need to go. So started from here, 1 came into action, then 0 came into action, then 1 came into action. Luckily here also 1 0 1. Basically you are not able to understand that whether we are going backward or frontward. So basically we goes backward actually. 1 0 1 you are encountering. So first 1 0 1. What about D? In D as well the same thing would happen. 0 0 and then 1. Yeah. So now what you will write down? 1 0 0. Yes, because you need to go opposite. So 0 0 1. I hope you are able to understand how we are working. You can see here I can use different color of pen, I guess. 0 0, then this path, then 1. So wherever the arrow takes you, arrow is taking me in this direction. What about this one? Sir, 1, 1, sorry, 1, 0, 1. What about this one? 1, 1. And what about this one? 0. And always write down in the reverse order. Okay. So what would be reverse order? 0, 0, 1. Right? 0, 0, 1. So these are the bit stream you are using. So you can see that code word length would be same. But sir, here C was represented by, you see this code 0, 1, 0, 1, 1, 0, 1, 1, 1. 0, 1, 1, 1, 0, 1, 1, 0, 0. Like code could be different, but you see one thing that this was represented by bit 1, this was represented by 2 bits, this was represented by 3 bits, and this was represented by 3 bits. So similar thing is happening here as well, no? Like basically code word length would be same. What that would be? That would be the same as this one, 1.9. 1.9 bits per symbol. Okay. The code could be different, but the code will also have a specialty that it will be prefix free code. That means 0 will not be prefix of anyone, 1, 1 will not be prefix of anyone, 1, 0, 1 will not be prefix of anyone, 1, 0, 0 will not be prefix of anyone. Right? Now, does that mean that Huffman and Shannon-Fano gives the same result? So let's just say, sir, a question is coming in the examination all based on Huffman coding. I will solve by Shannon-Fano because that seems easier. So I will solve by Shannon-Fano and I will put the answer for Huffman. No, Huffman gives better result. Okay, this particular thing is complex, right? If Shannon-Fano was only giving the same result, why would we study Huffman? Why would we study this much complex thing? So Huffman always give better efficiency. Okay, when it comes to efficiency, Huffman give better result than Shannon-Fano. Okay, although in this case it came out to be same. In this case as well, it will come out to be same only. 0.3, 0.25. We are taking the same example, no? 0.3, 0.25, 0.2, 0.12, 0.08, 0.05. Luckily here as well, in this case as well, it will come out to be same. But one example I will take here, and here I will explain you that why Huffman is better than Shannon-Fano in case of coding. But in case of designing, this is a complex design, but this is a very simple design, right? So we are studying Huffman as of now. So what we need to do, again add up the two lowermost. 0.08 added with 0.05, what you will get? 0.13. Is it greater than 0.12? Yes, sir. So this goes upward and this comes downward. This is your 0.2, this is your 0.25, and this is your 0.3. Okay, now add both of them. 0.25. Is it greater than 0.20? Yes. Is it greater than 0.25? No. Equal. So better, either you can put it above or you can put it equal to that. Doesn't matter. Basically, one thing I am pretty sure that, sir, this will go above 0.25. This will surely come down 0.20. Now, sir, I could have put this one above or this one lower. It's my choice, right? It's your own choice. Right, and all these are working as it is. This worked as it is, this one was as it is, this one was as it is, this was as it is, this was as it is. Okay, now what about these two guys? Added them, it will become 0.45. Is it greater than 0.3? Yes. Is it greater than 0.25? Yes. So this will go the most above 0.45, then downward 0.3 would come, and then 0.25 would come, 0.3 would come, 0.25 would come. Then add both of them. 0.55. Is it greater than 0.45? Yes. So 0.55. 0.45. If I add both of them, what I will be getting? I will be getting 1 only, but the 1 I don't need to write down. So wherever I made this particular diagram, so I will write down 1 0, 1 0, 1 0, 1 0, and 1 0, 1 0, 1 0, 1 0, 1 0, 1 0. All fine. So let's write down the codes now. X2. What will be the code for X2? So let's start working. nothing, 1, and then 1. Okay, this is how I will work. So 1 1 1 1. What about x1? Goes like this, goes like this, goes like this, and goes like this. 0 1, right? 0 1. First 0, then 1. What about this one? Goes like this. 0. Look, you follow the arrow. Okay, don't get confused. Follow the arrow. 0. This one is not coming there, right? You are following from here. You are following from here, and then 0. So 0 0 is coming actually. X6 is 0 0. What about the next one? 0 1 0 1, and then 0 0 1, and then 0. So x3 is 0 1 0. Let's recheck everything. Started like this, 1 1. Started like this, 0 1. Started like this, 0 0 0 1 0. What about x5? 1 1 1 0 1 1 1 0. And what about x6? 0 1 1 0 0 1 1 0. Okay, that's correct. So 2 2 2 3 4 4. Are we getting the same thing here? 2 2 2 3 4 4. Although the bit could be different, bits could be different, right? But the number of bits are same. Like efficiency would come out to be same only. Code word length would come out to be same as 2.38. But this is luckily only, right? It might happen that sometimes Halfman can give you better result than Shannon-Fano, but Shannon-Fano will never give you better results than Halfman. Okay, so if best coding method is there, then Halfman is the better coding method. Okay, well and good. So I hope you have understood. Just write it down. If you are not able to understand, then again you need to watch it. I cannot do anything, right? You again need to watch it. So whatever the way that I am telling, in that way only you need to solve. So try solving this question. Using Huffman and Shannon-Fano coding, you need to tell the coding efficiency and redundancy. Okay. H of x I have already calculated. You can also calculate on your own. The target would be you need to calculate your code word length. So for code word length, you need to tell how the codes will look like. So x1, x2, these probabilities are mentioned. They are mentioned in their order only. So somewhere I have written down. Okay, yeah. So symbols, these probabilities also I have written down already. So let's try doing. So what we need to do? Something very interesting I will observe here. So I will copy it again. Okay. So first, how someone will break it down? Someone will say that, sir, I will break it down like this. 0.4, 0.6. Someone will say that, sir, I will break it down like this. 0.6, 0. Basically, if someone breaks here, that means 0.4 upward, 0.6 downward. If someone breaks here, then 0.6 upward, 0.4 downward. That means both are giving you same result. 0.4, 0.6. 0.6, 0.4. That means difference is same. So someone will say I will break down like this, and someone will say I will break down like this. Then we will solve both methods. Okay. So here this guy has broken down like this, and this guy has broken down like this. So this guy got a single room. Now how will you break? 0.2 and this is 0.4. So I will break like this. Right, because this would be 0.35, 0.25. Here also 2 division I need to do. So this guy will get 0 and this guy will get 1, and here also 2 division I need to do. because in this room 2 people are left, in this room as well 2 people are left. If 2 people are left, you don't need to think, just divide them from half. So what do you see? 0, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So you can see that none of them are prefix, right? This is not the prefix of this one, and so on. What about this one? Sir, upper guys will be getting 0 0, downward guys will be getting 1 1. Sir, here only 2 guys are there, I will simply break them. What about this one, sir? This has to be broken down like this. So upper guy will get 0, this guy will get 1 1, and then, sir, in the end it should be broken like this. So here you see that, sir, 0 1 bit, then 3 bit, 3 bit, 3 bit, 3 bit. Sir, here 2 bit, 2 bit, 2 bit, 3 bit, 3 bit. Without doing the calculation, what do you think which will have better efficiency? Without doing the calculation, blindly if you see. Like, a lot of people will say that, sir, here 3 3 3 3, a lot of time 3 bits are being used, but sir, here 2 2 2, a lot of time 2 bits are being used. I feel that, sir, this will have better efficiency, but you are wrong. First thing is that there is ambiguity now. The guy should choose this one or the guy should choose this one. Both are valid code. Both are valid code. Here also you will see that none of them are the prefix of other code. 0 0 not prefix, 0 1 not prefix, 1 0 not prefix, 1 1 0 not prefix, 1 1 1 not prefix. Here also the same thing is there. So what he will choose, this kind of things will never occur in Shannon. This kind of things will never occur in Halfman. So if some guy goes with this one, then what code word length he will get? 0.4 is having 2 bits, 0.8. 0.2 is having 2 bits, 0.4. 0.15 is having 2 bits, 0.3. 0.15 is having 3 bits, so 0.15 into 3, that would be 0.45. And 0.1 is having 3 bits, 0.3. 2.25, right? 2.25 bits per symbol. So here he will say that, sir, my efficiency is 2.145 divided by 2.25. 2.145 divided by 2.25. So he will say, sir, my efficiency is coming out to be 95.33%. What about this one? It feels like that it will have more redundancy or lesser efficiency, but no, this is not the case. You see, 0.5 is 0.4 is using only 1 bit. 0.2 is using 3 bit. 0.15 is using 3 bit. That means 0.15 again using 3 bit, and this is using 3 bit, right? So this is 0.4 and 0.6 probability is using 3 bit, so 1.8, so 2.2. This is actually coming out to be 2.20 bits per symbol, and previous one was 2.25 bits per symbol. So who is having better efficiency? Obviously this one will have a better efficiency, no? 2.145 divided by 2.20. 2.145 divided by 2.20. So 97.5% efficiency it is having. So if someone has divided in the other manner, then he would have to satisfy himself with 95.33% efficiency only. Here he is getting better efficiency. So this kind of example we saw that better design would be this one. Both are correct, but better would be this one. Even 0 0 0 1 1 0, they are also correct, no? Like if I had assigned 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0. So are they prefix of anyone? 0 0 0 is not prefix of 0 0 1. 0 0 1 is not prefix of 0 1 0. 0 1 0 is not prefix of 0 1 1. Like none of the code is prefix of any other code. So this is also valid. But here efficiency will be lower, no? Right? So this was also valid. This was also valid. This is also valid. But you need to take where efficiency is maximum. So this case will give you maximum efficiency. So this problem is occurring in Shannon-Fano. But this problem will not occur in Halfman. How will you solve the Halfman one? Add the lowest two, what you will get? 0.25. You will see that, sir, this 0.25 is just below 0.4. And all these numbers will come down 0.2, 0.15. Right? Now this is 0.35. and this is 0.4, this is 0.25. 0.6, 0.4. This will add up to 1 only. So what I will do, 1 0 1 0 1 0 1 0. So what about x1? Simply bit 0. What about x2? 1 0 1. So 1 0 1. What about x3? 0 1 1, right? 0 1 1, 0 1 1. x4 1 0 1. अरे रे भाई ये तो कुछ दिक्कत हो गई. 1 0 1 is already there. 1 0 1. What about x2? 1 1 1. It was actually 1 1 1. x2 was 1 1 and 1. So x2 was 1 1 1. x4 is 1 0 1. And what about x5? This is 0 0 1. 0 0 1. None of the code is prefix of any other code. 1 1 1 is not the prefix of this one, and you can see. Okay, so what do you think? What will be the efficiency that will come out to be? That would come out to be 97.5. There could be some examples which I was not able to find out, but I have seen some examples where efficiency of Huffman is better than the best case of Shannon-Fano. Like this is the best case of Shannon-Fano. Although here they are equal, but there could be some example where the efficiency of Huffman is better than the best case of Shannon-Fano. But here this issue is also there. So you have understood that if efficiency is your target, this design would be complex. But if efficiency is your target, then I would go by this coding. Okay, and if easier design is my target, then I would go by this coding. I will never go by the coding that I have understood in communication system. This coding I will never do, right? Because here all of them are assigned the same number of bits, which is not actually necessary. All good? All fine? Okay. So that's it. This is the end of source coding. It was a simple lecture only, although it is taught in some 20-25 minutes, somewhere in between information theory. But I wanted to make a separate lecture for this one so that you don't actually mug up the things. You actually understand the things here. You have understood the things here, right? Like what is the meaning of source coding? What is the actual idea? So it was a very simple lecture. It's just that I wanted to give an idea and that we have understood. Next lecture will be our last lecture of this particular chapter, and that would be channel coding. Okay, so we will study channel coding, why it is necessary, how do we do so, everything we will study. So next lecture will be channel coding. Okay, yeah, thank you. Hi everyone. So today we are going to study about channel coding. So after this, your communication coding part would come to an end. Along with that, information theory will also end, and digital communication will also end. So this is going to be our last lecture of digital communication. Okay, so a very simple topic. First we will understand the meaning of channel coding, then we will see there are some techniques, and with that this video will end. Along with that, like in this video you would see that there are a lot of things. Okay, a lot of information would be there. It's not that I will tell you to mug it up. I will give the proper reasoning, but there will be a lot of concepts. All concepts will be very easy, but number of concepts are more. Okay, so for this particular video I would recommend that you maintain a short note, like 1 page you can take. In that 1 page you will write down some important formula. Those formula will be like class 11 12 formula, like very basic formula would be there, like even a kid can understand those formula. So you need to maintain a short notes. That short notes you don't need to make. In this video only I will make the short notes. I will make one particular slide where everything that we have studied, conclusion will be there. Okay, so just hold on to this video in a manner that there will be a lot of information in this particular video. So you need to accept that this particular thing, that information will be a lot. Okay, so let's get started. Let's get started with the basic meaning of channel coding. So you know that we will be having some source. This source will be generating some symbols S1, S2, S3, S4, S5. Let's just say it has created these 5 symbols, right? Or let's take the best case, it has created 8 symbols. So if this has created 8 symbols, then encoder will be working now. What encoder would do? that it would make it 0 0 1, S2 is mapped to 0 0 1, S1 is mapped to 0 0 0, S3 will be mapped to, in this process all these values will be mapped. Now ideally what we should transmit, that 0 0 0 will be going to the modulator and this will be transmitted. 0 0 0 will be going to the modulator. Let's just say modulator has mapped 0 0 0 to some minus 5 volt. So now this minus 5 volt will be traveling through the channel. This is what we should ideally do. But I know one thing, that in the channel there will be presence of noise. Now let's just say I wanted to send 0 0 0 which was mapped to minus 5, but somehow because of the noise this 0 0 0 became 0 0 1. So you know that effect of noise is going to come in the channel. So to reduce this effect of noise we use channel encoding. Is that clear? So why this particular block is there? When we were studying digital communication system this block was not there, but now we are studying our channel coding. When we are studying the coding in communication system, at that time this block has come into action. So this block will be used to reduce the effect of noise. So to reduce the effect of noise we use threshold detector as well, we use receiving filter as well. All these things we use in digital communication system. Surely we will use it, but in the transmitter side what we can do, that part we are seeing, that part we will see here. And what will happen here, what will be made here, receiver part would be there. So in the receiver part as well there will be a channel decoder. So whatever this channel encoder has done, the channel decoder will do the opposite process, right? So channel decoder would also be there, channel encoder is here only. So what this channel encoder would do, let's check that out. So let's just say at the input of the channel encoder 0 0 0 is coming. So ideally what should be transmitted, 0 0 0 should be transmitted over the channel. So this should be transmitted. But what channel encoder would do, it would add up some extra parity bits. What is this parity bit we will understand, but what is the name? The name is parity bits. So let's just say these parity bits are 2. So we wanted to transmit 0 0 0, but it would add up some extra 2 parity bits. So let's just say it has added 0 0 only. We wanted to transmit 0 0 0, it has added 2 extra parity bits, that is 0 0. Sir, why it is adding parity bits, you will understand. Okay, somehow these parity bits will help us to reduce the effect of noise. Okay, like noise will be there, basically these 2 parity bits will help us to determine whether there will be error or not. You are not understanding, just watch the video, you will understand. So let's just say I wanted to transmit 0 0 1. So now what this parity bit would do, that you will transmit 0 0 1, but it would add up some extra parity bit as well. Let's just say the extra parity bit is 0 1. Now you wanted to transmit 0 1 1. Okay, or let's take some other case. Let's just say you transmitted 1 1 0. You wanted to transmit 1 1 0. So what this parity bit would do now, it will add up 1 0. It would have add up 0 1 as well. Like these 2 parity bits could be anything. These 2 parity bits could be anything. So this channel encoder will decide what parity bits I need to add. So what we are making sure here, sir, no matter whether you transmit even number of ones or odd number of ones. Here what is the number of ones? Odd. Here what is the number of one? Even. And here what is the number of one? Even, because there is no one. Number of ones. Number of ones. Number of ones. So here there is 0 number of ones, here there is 1 number of ones, here there is 2 number of ones. But what channel encoder is doing? Channel encoder is making sure that whatever that I am transmitting, all these bit stream will have even number of ones. So 0 0 1 0 1 1 0 0. Sorry. What we wanted to transmit, we actually wanted to transmit 1 1 0. So what it can do, it can either add up 1 1 or it can add up 0 0. So let's just say it is adding up 1 1. So what you see here? Here also we are getting even number of ones. So what I will say to the receiver, I will say to the receiver that whatever the bit stream is coming to you, in that particular bit stream, you will always get even number of ones. What I will say to the receiver, that whatever the bit stream that you are getting, in that bit stream, there will be always even number of ones. Let's just say somehow this bit got into error. That I wanted to transmit 1 1 0, but this bit got into error. So what really happened? It became 1 0 0 1 1. Now the receiver would know that the transmitter told me that bits should be having even number of ones, but now I am having odd number of ones. That means there is something wrong. So this is the basic idea of channel encoding. I am just telling that what basically channel encoder is trying to do. This is not the only way. Like this is just one example I have told, that even number of ones should be there. It is not the only way. Other technique can also be there. But just I am telling that why we are adding up those extra parity bits. Those extra parity bit would make sure that at the receiver, when some error is happening, you are able to detect the error. Along with that, you will be able to correct the error as well. Sir, how it will correct it? We will see. Don't worry about that. But at least as of now, you are able to understand that what is the job of this channel encoder. Whatever the bit stream that I wanted to transmit, if that bit stream gets some error, then the receiver should be able to recognize that error. Along with that, it should be able to detect the error. Along with that, it should be able to correct that error as well. So somehow this receiver will get to know that this bit is in the error. And if this bit is in the error, then what he will do? 11011. Now someone can say that, sir, receiver can think, sir, this bit is in error. Or receiver can think that, sir, this bit is in error. Because eventually he needs to make even number of ones. So yes, receiver can think this bit in error. Receiver can think this bit in error as well. But somehow we will make sure that receiver will think only this bit is in error. So all the techniques we are going to understand, but as of now on the top level you have understood that what is the job of channel encoder, to add up some extra bits so that at the receiver, if there is some error in the bit, then you would be able to detect and correct that particular error. So this is the job of a channel encoder. I hope you have understood. Now we need to see some terms. So what these terms are known as, like whatever that you are transmitting, these are known as data word. Okay, what it is known as data word. So from now onwards, I will be calling them data word. And whatever that you are sending from the transmitter, whatever that you are eventually sending, that is known as code word. Okay. Now each data word is having 3 number of bits here. Each data word is having 3 number of bits. Each data word is having 3 number of bits. That means here what is the number of bits? Number of bits are 3, but we will represent them as k. Okay. Small k. So your data word would be having k number of bits and your code word would be having, how will I represent parity bits? So parity bits I will be representing by small m. So k number of bits will be added with small m number of bits. So your code word would be having n number of bits and that would be equals to k plus m. Is that clear to you? Sir, parity bit is represented by m. Data word bit is represented by k. Each data word is having k number of bits and in the channel encoder m number of parity bits are used. So whatever the code word that you are sending, that would have k plus m. So here 3 plus 2, it will have 5 number of bits. Now someone would say that, sir, in the previous video we studied the concept of encoder. There we saw that if someone is having higher probability, then we can assign them lower number of bits, and if someone is having lower probability, then we need to assign higher number of bits. So that particular scenario is not in your syllabus. Basically here your data word would be fixed. It would be having k number of bits only, like 000, 3 bits, 3 bits, 3 bits, and even your code word would be fixed. That code word would be having n number of bits only, n number of bits. Parity is also fixed. If 2 parity they are adding up, that means all the data word would get 2 parities only. So everything would be fixed. K, M and these will be fixed. It's not that, sir, with respect to the symbols, like S1 would be having different value of N, different value of M, different value of K. Sir, S4 will be having different values. No. All will have the same value. You need to assume that everything will have the same value. Is that clear? So this, like if K is fixed, M is fixed, N is fixed. So this coding is known as block code. Okay. This coding is known as block code. If all these things are fixed, no? Like if code word is having a fixed length, if this n is fixed, if this is fixed, then this coding scheme is known as block code. You don't need to remember it, but in the examination, when you see the name word written block code, you should be able to understand that what is the meaning of block code. So if all the code words are having fixed length, this is known as length. Okay, k is also known as length. Length of data word k, length of code word n. Okay, length of a code word, length of a data word is k. Number of parity bits are m. So n is equals to k plus m. Now I will ask you a very good question. If my data bits, let's just say k is 4. Okay, my data word length is 4. then how many code words I can get? And let's just say my M value is 3. Okay, K value is 4, data word length is 4, number of parity bits that I am using is 3. So what would be my code word length? Sir, your code word length would be 4 plus 3, that would be 7. So I am asking that how many code words you will be getting? 2 to the power 7 or 2 to the power 4? 2 to the power 4 you will be getting. Why? Because here you are not getting all the combination. Let's just say here code word length is 5. So it doesn't mean sir 0 0 0 0 0 will occur, then 0 0 0 0 1 will occur, then 0 0 0 1 0 would occur, then 0 0 0 1 1 would occur. So in that manner sir 2 to the power 5 combination would occur. No. At the input how many combination would occur? 8 combination would occur. Now with respect to these 8 combination, you will have 2 parity bits. That means with these 8 combination, 2 parity bits would be added up. That means with 0 0 0 0 0 is added, with 0 0 1 0 1 is added, with 1 1 0 1 1 is added, with 1 1 1 1 0 could be added, with 0 1 0 something else could be added. So basically what you are doing with respect to the data word length. Everything is happening with respect to the data word length. This is the matter of concern. Code word is just made from data word. Code word is made from the data word. So if data words are 8, then code word would be 8 as well. If data words are 10, then code word would be 10 as well. If data words are 12, code word would be 12 as well. Is that clear to you or not? So in the examination, what they can do, they will tell you the data word length, okay, and they will tell you the code word length, and they will ask you how many code words you will generate. Although these kind of questions they will not ask, but somewhere this particular thing would be used, that you would be having the value of n and k. And now somewhere I will ask you that how many code words would be there. So sir, code word means code word is having n number of bits. So sir, total 2 to the power n code word would be there. No, 2 to the power k code word would be there. Okay, so this k is our matter of concern. This is the hero. K is the hero, because for this k number of bits we are adding m parity bits and we are getting our n code word bits. Is that clear? Okay, so all these concepts we will write down. Don't worry about that. Okay, everything is fine on this slide. So let's write down everything. So this is our channel encoder. M parity bits we are using. Data word with length k. That means total 2 to the power k message symbols are possible, or input symbol you can say whatever you want to say. 2 to the power k message symbols are possible. If code word length is n equals to k plus n, then how much code words are possible? Sir, 2 to the power k code words are possible. Why 2 to the power k? Sir, you have already explained. Okay, so 2 to the power k code words only will be possible. What is the reason behind that? The reason is that with respect to the data word, we are making code word. So from the data word, we are going towards the code word. We are not going from code word to data word to code word. All good? Okay. Now, whatever the code words that you are getting, so set of code word is known as code. What if I use somewhere the word code? What is the meaning of code? All the set of code words. Let's just say I can generate 4 kind of code word. Let's just say value of k is 2. Value of k is 2. So that means I will generate 4 code words. I am saying that value of k is 2 and value of m is 3. So I will generate 4 code words like this. So these 4 code words are generated. So combine these 4 code words will be known as code. Okay. Combination of these 4 code words will be known as code. Is that clear to you? Okay. Again, let me repeat. With respect to the data word, what you have made? Code word. So set of code word is known as code. Very simple thing. So somewhere if you see the word written code, that means they are talking about the set of code words. Okay. So you will see that term minimum length of code, minimum weight of code, minimum distance of code. So minimum distance of code means minimum distance between code words. Okay, we will see that. So let's see some important terms now. So what all are those important terms? First one is Hamming weight. Forget about the word Hamming. Hamming will come into action later on. Just think of weight. What is the meaning of Hamming weight? Number of ones. Number of ones. So if some code words are given, 101100 code word is given, 100010 code word is given, 00100 code word is given, and 000 code word is given. So what is the weight of this code word? So weight of C1. What is the weight of C1? Sir, 3. Number of ones you need to check. What is the weight of C2 2. What is the weight of C3? 1. And what is the weight of C4? 0. Okay. Number of ones you need to check. What is the meaning of Hamming weight? Hamming weight means number of ones. Very simple thing. Now second term is Hamming distance. Hamming distance means by the number of bits they differ. What do I mean by that? 1 is same to 1, 0 is same to 0, 1 is not same to 0, this 1 is not same to 0, this 0 is not same to 1. So they are differing by 3 bits. So the distance between C1 and C2 is 3. Or what you can do, that you take the C1 XOR C2 and whatever the weight that you are getting, first let's take C1 XOR C2. So 1 is XORed with 1, 0, 0 is XORed with 0, 1 XORed with 0, 1, 1, 1, 0. And whatever that you are getting, just take the weight of that. What is the answer? 3 only. Basically, number of places by which the code words are differing. So if code words are different, that means their XOR operation will be 1. So in this particular code word, whatever the number of ones I am getting, that will be my distance. Very simple thing, no? Distance between code word. So between two code word, here 3 distance would be there, right? So distance between C2 and C3, what that would be? So that would also be 3. Distance between C3 and C4, it is differing by only one bit. Here the better word would be bits, number of bits by which the code word differ. So this is differing by 3 bits. 1, 1, 1. C2, C4, they are differing by 2 bits, and C1, C3, they are differing by 2 bits. Okay, they are differing by 2 bits. All good? So this is the meaning of Hamming distance. Sir, why they are useful? Somewhere they will be useful. What is the meaning of minimum distance of a code? So minimum distance of a code means minimum Hamming distance between the code word. Let's just say a particular code is generating n code words. A particular code is generating, basically this was our channel encoder, number of bits were k, m parity bits we were using, and here code word length is coming out to be k plus m, that is n. So n code words we are getting through this channel encoder, we are getting k code words, not m, right? What we will be getting? We will be getting k code words, no? Not n. N code words we will not be getting. Again, here also I did the error. If this value is n, how many code words I will be getting? 2 to the power k code word I will be getting. Again, this should be 2 to the power k. So better just understand that these many codes, let's just say 7 code words I am generating. If this is k, then how many code words you will generate here? Data word length is k. That means let's just say 3 bits are there. So with respect to 3 bits, you can generate 8 combination. So here you will get 8 code word. So basically we have generated C1, C2, C3. In that manner, 7 code word we have generated. So total 7 code word we are having. Now, there will be some distance between C1, C2, right? There will be some distance between C1, C2. There will be some distance between C2, C3. There will be some distance between C3, C4. There will be some distance between C1, C7, right? There will be some distance between C3, C7 as well. So in that manner, a lot of combination would be there, no? Out of 7, you need to choose 2. So 7 C2 combination would be there. That means 7 into 6 divided by 2, 21 combination would be there. Like C1, C2, C2, C3, C3, C4, in that manner 21 combination would be there. In those 21 combination, they will be differing by some bits, right? They would be differing by some bits. So there will be distance between the code words. Now, whichever the distance is minimum, it is represented by d minimum. So minimum of all the distance, whatever the distance that you are calculating, minimum of all these distance, that is known as minimum distance of a code, or in the examination board they can say minimum Hamming distance between the code word. Like this particular thing could be used, or they can use this particular thing as well. Your focus should be towards minimum distance. Where your focus should be? Your focus should be towards minimum distance. That means you will find out the distance between the code words, and whichever the distance you are getting minimum, that would be your answer. So this is the code that they have given. That means we are generating 4 codes. What we are generating? We are generating 4 codes. So here 4 codes are being generated. Code words, not code I should say, code words I should say. So here 4 code words are being generated. So what do you think? What would have been the length of a data word or message word? Here data word would be there, no? So what do you think? What should be the length of a data word such that you are generating 4 code word? K has to be 2, right? Because if K is 2, that means with respect to these 4 combination, you are generating 4 code words. So if K is 2, and you can see that data word length is 6, that means n is equals to 6. Data word length is 3, 3, 6. Data word length is 6. And K is equals to 2. What does that mean? That means your M would be equals to 4. So they can give this set that these are the valid code words that we are generating. This is the valid code word, this is also valid code word, this is the valid code word, and this is the valid code word. So only 4 code words we are generating. That means how many number of parity bits we have used. So 4 code word you are generating. That means data word would have been 4. If data word would have been 4, that means 2 bits would be used. Now in the code word you are having 6 bits. That means parity bits would be 4. So this kind of question can be asked. Now what other thing they are asking? Minimum distance between the code. So if you notice something, then what is the distance between C1 and C2? That we have already find out actually. Here you can see 3, 3, 1, 3, 2, 3. So this was your C1, C2, C2, C3, C3, C4, C1, C4, C2, C4, and C1, C3. So total 6 combination would be there, no? Out of 4 you need to choose 2. 4 code words are there. Out of 4 you need to choose 2. So 4 C2 combination, that means 6 combination would be there, and these 6 distance we have find out. This example and this example is same. Now what is the minimum of all of them? This is the minimum of all of them, right? Okay. So your D minimum would simply be distance between C3 and C4. Am I getting 1 somewhere else as well? No, only here only. So what would be the answer? Answer would be 1. And you can notice that distance between these two guys is 1 only. Okay. So D minimum is 1. So that's the answer. Directly, like these kind of questions are asked actually in the examination. You might feel like that, sir, what is this? This is like we are studying in class 5th or 6th. No, these kind of questions are actually asked in the examination, right? So don't feel like that, sir. This is like this is school level things you are teaching. Like this is a concept only, no? But and in this manner, a lot of concept would be there in this chapter. Like this concept you have understood. Now you are going to understand the meaning of minimum weight of a code. So what do you think? What will be the minimum weight of a code? Like there is a code word. This will have a weight of C1, WC1. This will have a weight of WC2. This will have a weight of WC3. And let's just say in place of n, I should write down 7. So this will have a weight of WCN. And whatever the minimum weight that you are getting, that would be your answer. Right? Very straightforward thing. There is nothing to learn here. But somewhere these things will be used, and that we will see. And these kind of questions can also come in the examination. So what do you think? What will be the minimum code? 3, 2, 1, and 0. So what do you think? What will be the minimum weight? That minimum weight would be 0. And this question has come in GATE examination last year only. Although it did not come in this manner, but somehow you needed to do this thing only. That you needed to check the number of ones. Here 0 ones you are having, here 1 ones you are having, here you are having 2 ones, and here you are having 3 ones. Okay. So minimum number of ones in this case you are having, but actually we will study that you don't need to consider this one. For this particular question, this would be the answer. The minimum weight is 0. But the question that we are going to solve, where they asked in the GATE examination, in that question this would be the answer. Why this would be the answer, we will see that. Don't worry. But as of now, for this particular question, if they are asking these code words are there, what is the minimum weight, your answer would be 0. And this is something that they are asking code rate. What is code rate? So code rate, simply you will remember, code rate is nothing but K by N. Okay, and it would always be less than 1, not very less than 1. It would always be less than 1. So K by N. What is the number of bits here? 2. And what is the code word length? That is 6. Same example we are taking, right? Is that clear? Four code words are there. Four code words are there. That means data word would be 4. Data word would be 4. That means number of bits that you are using. 4 data word, that would be 2. And what is the code word length? Code word length is 6. So 2 by 6. What that would be? 1 by 3. So your code rate is 1 by 3. Simply they can ask simple question, what is the code rate? So code rate is nothing but k by n. Okay. Lower the code rate, better the efficiency. What do I mean to say? Lower the code rate means n would be larger and k would be lower, which is pretty obvious because n is equal to k plus n. If you are saying that code rate is lower, what does that mean? That means m is high, number of parity bits are high. Are you able to understand this point? If your code rate is low, what does that mean? Let's just say k is fixed. What I am saying, k is fixed. If code rate is low, that means n is high. This k is fixed, that means m is also high. So number of parity bits are more. If number of parity bits you use, you get better efficiency. That means your chances of error would be reduced, or chances of error would be same, probability of error would be same, but you will be able to detect the error in a better manner. No more number of parity bits means you will be able to detect the error and correct the error in a better manner. Is that understandable to you? Okay. More number of parity bits are useful, but if you use more and more number of parity bits, like sir, till last lecture you used to say that we need to reduce the number of bits, but sir, here what you are doing, you are increasing the number of bits. So till the last lecture you were saying, you told us source encoder, in the source encoder only target was to reduce the size, that means to reduce the number of bits. But here in the channel encoder, sir, you are increasing the number of bits. We are increasing the number of bits so that we are able to detect and correct the error. That's why we are doing so. So it's not that sir, blindly I will put the value of m equals to 10. So m equals to 10 means each code word would be represented by 13 bits. So size would be very large. So there should be some equilibrium, right? You blindly cannot increase the number of parity bits. But if you increase the number of parity bits, then your chances of detecting the error and correcting the error would increase. Okay. So yeah, this is the scenario. Code rate. What would be code rate? Yeah, code rate would be 1 by 3. So k by n you need to remember. Okay. So this is the minimum weight of a code, right? Now there is something called error detection and correction. So let's understand that by example. So there is your transmitter is transmitting two kind of code words, 000, 00, 111, 11. Now find out the maximum number of detectable error. What is the meaning of that? So first we are seeing this one. Find out the maximum number of detectable error. So let's just say I am transmitted data word. Not data word, sorry, transmitted code word. So I am transmitting 00000, but what I received code word was 00001. Now receiver knows that either this would come or this would come. Either 5 times 0 would come, or 5 times 1 would come. But what you are receiving? I am receiving 00001. That means receiver would know that there is some error. Now receiver will not be able to tell that, sir, whether you transmitted 5 times 0 or you transmitted 5 times 1. He doesn't know that, but he knows one thing, that sir, either all the bits should be 0 or all the bits should be 1. Either all the bits should be 0 or all the bits should be 1. But what I am getting, 4 bits 0, 1 bit 1. That means there is an error. So there was 1 bit of error. 1 bit of error. And this 1 bit of error was detected. We are talking about detectable error. Now receiver would not know that whether this is coming from 00000 or it is coming from 1111. He doesn't know what was transmitted. He only knows that I should be able to receive these two guys and I am not receiving any of them. That means there is an error. So error is detected. It is not corrected. Correction we will do, but as of now error is detected for sure. Error is detected for sure. Now again, same code word I am transmitting, but this time what really happened? 2 bits were in error. That means 2-bit error was there. 2-bit error was there. If 2-bit was in error, either I should have received all 0 or I should have received all 1. Again error is detected. If 3-bit error is there, then also error is detected. If 4-bit error is there, then also error is detected. But if a 5-bit error is there, 5-bit error is there, that means all the bits are in error. 0 is converted to 1, 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 0 is converted to 1. Now what receiver will say? Receiver will think that 1111 was transmitted. That means error is not detected. Did you understand this point or not? So if all bits are in error, then there is an issue. Now similar thing you can do with 1111 as well. That one bit is an error. Let's just say this became 0. There is an error. 2 bits are in error, error will be detected. 3 bits are in error, error will be detected. 4 bits are in error, error will be detected. But if 5 bits are in error, error will not be detected. What does that mean? What is the distance between these two codes? I am calling that distance as d minimum, okay? Although there is no concept of minimum between two guys, right? Right? If someone is having 2 toffee and one guy is having 4 toffee, so this guy will be lesser than this one, that's it. So there is no meaning of minimum, but here as of now I am saying that this is the minimum distance between both of them. Whatever the distance is there, that would be minimum only. So I am calling this distance as d minimum, okay? And I am calling maximum number of detectable errors. What I am saying, detectable error I am calling as td. So can you let me know one relation that your d minimum should be greater than equals to td plus 1? Say yes or no. Just think about it with respect to 3 examples. Let's just say these were your code words. These were your code words. Now in these code words, first let me know what is d minimum. So distance between these two guys is 2. Distance between these two guys is 2. And distance between these two guys is 4. So what is my d minimum? So d minimum is 2. Okay. D minimum is 2. Right. Now just let me know if I am transmitting this one. If I am transmitting this 0, 0, 0, 0, 0. Somehow what really happened? This became 0, 0, 0, 1. Will you be able to detect the error? Yes, sir, because no one is matching. But somehow it became, basically in this case you are able to detect the error. But somehow this guy became 0, 0, 1, 1. Will you be able to detect the error? Receiver will say this is received. So error is not detected here. So only one bit of error is detected. In this particular example, if these are my transmitted code word, if I am receiving this one, then error is detected. But if I am receiving this one, then error is not detected. That means 2 bit of error is not detected. Only 1 bit of error is detected. That means the maximum number of error that you are able to detect plus 1 is equals to d minimum. Is that understandable to you or not? Okay. So this less than equals to sign is not important here. D minimum should be equals to td plus 1. If I am saying that maximum number of detectable error is td, then here maximum number of error that I am able to detect, that is equals to 5 minus 1. What that would be? That would be 4. Okay. So I am able to detect this much of errors. So greater than sign should not be there. I should be putting equal sign, because if I am saying td is the maximum number of detectable errors, that means maximum I can detect these many errors. Now someone will say that, sir, what if this happened, that you were transmitting 0, 0, 0, error was detected. Next time what happened? This bit was in error. What I mean to say is that next time, sir, this bit was in error. So what receiver will say? None of these are received. So that means he is not able to detect this error. Are you able to understand this point? Someone would say that, sir, what was happened was these 3 bits were in error. So what receiver will say? Receiver will say that, sir, none of them we are able to detect. That means this error he will also be able to detect. But you don't need to take the best case. In engineering, you will always take the worst case. And worst case would say that these 2 bits are converted to 1. You will take the worst case, no? Are you able to understand this point? Like some guy would say that, sir, these 4 bits I am sending, 0, 0, 0 I am sending. But what really happened? In the first case, this bit was changed. Then in the second case, this bit was changed. And in the third case, these 2 bits were changed. So, sir, in all the cases, your receiver will be able to detect the error. So, here he has detected 3 bit of error as well. but you are saying that it will be able to detect only 1 bit of error. So I am saying the worst case. In the worst case, maximum number of detectable error would be 1. I am talking about the worst case. Are you able to understand this point? And the worst case would be that these 2 bits are converted to 1 1. That would be the worst case. Is that understandable to you? Very simple thing, very straightforward, right? Easily understandable. So always I am taking the worst case. Eventually you will remember the formula, but how these formula came, that should also be clear to you. So the formula of maximum number of detectable error, that is clear to you. Now what is the meaning of maximum number of correctable error? Okay, so transmitted code word I would write down. Again I would write down the received code word as well. So somehow I will copy this much of thing. Now how this works, how your detection works. Detection, not detection, sorry, correction. Detection, how detection would work, that we have already seen. How correction works. How correction works on Hamming distance, or better I should say, yeah, Hamming distance. Correction works on Hamming distance. What does that mean? That sir, you are transmitting two kind of code words, 000, or you are transmitting 111. Now sir, your received code word is 0001. Your received code word is 0001. So 0001 is nearer to this guy, or it is nearer to this guy? Sir, it is nearer to 5 times 0. Because what is the distance between these two guys? Here the distance is 1 and here the distance is 4. So it is nearer to this guy. So now your receiver will be able to understand that I am getting 00001, which is nearer to 0000 only. That means I would be able to correct it to 00000. He will not be correcting it to 11111. He will be correcting it to 00000. Why is that so? Because receiver knows that it is nearer to your 00001 is nearer to 5 times 0. So if it is nearer to 5 times 0, that means this is how it should be corrected. Now what about this one? 00011. It is nearer to what? It is nearer to 0000 or 1111. The distance of this guy from this guy is 2 and distance of this guy from this guy is 3. So it is again nearer to 000 only. So again it is nearer to 000. So it will be corrected to 000 only. What about this one? It is nearer to this guy or it is nearer to this particular guy. So here the distance is, let's first check the distance with 111. So here the distance is 2 and here the distance is 3. So now 00001, if you are receiving this one 000111, then receiver would say that 1111 was transmitted, but that is not correct. Actually we were transmitting 5 times 0. That means when 3 bit of error was there, or 4 bit of error would be there, or 5 bit of error would be there, then they will not be corrected. That means you will receive the wrong code word. Wrong code word. Is that understandable to you or not? So what I have done, I have received the wrong code word. Okay, so how many bits I was able to detect? I was able to detect 2 bits. Okay, only 2 bits. That means from the, let's just say this is my code word C1 and this is my code word C2. And if I am saying that the maximum number of correctable error is T. So this kind of diagram you would see that from C1, if there is any code which is at distance T, from C1 if there is any code which is at a distance T, and from C2 if there is any code which is distance at T. So in between, the gap between them should be at least one distance, and between these two guys the minimum distance is d minimum. So it is written that d minimum is equals to 2t plus 1. Did you understand what I did here? Like the same case would have happened with 1111 as well, no? Like 1111 was there, let's just say 111 was received as 1110. So minimum distance with 1 1 1 would be 1 only. He will be able to correct it. What if this was received? Able to correct. But what if this is received? Not able to correct, because this is nearer to 0 0 0 0 than 0 0 0 than 1 1 1 1, right? 1 1 0 0 0 is nearer to all times 0, not to all time 1, but actually you were transmitting all time 1. That means it was not able to correct the error, right? So range should be, if I want the error to be corrected, so he will be able to correct up to t bit of error, C2 will be able to correct up to t bit of error, C1 will be able to correct up to t bit of error, and there should be 1 bit of gap should be there. So this gap is 1. So d minimum would be 2t plus 1. So from now onwards, what you will do, we will not write down this particular thing, we will not make this diagram. From now onwards, what you will do, you will simply remember the formula, and formula says d minimum is equals to 2t plus 1. D minimum is 2t plus 1, where t is the maximum number of correctable error. Correctable bit error, right? So here what was your d minimum? D minimum was 5 only. So t is coming out to be 2. Now someone will say that, sir, what if my d minimum was 4? What if my d minimum was 4? So what you will be getting? 3 by 2. So t is equals to 1.5. That means maximum number of bits that you can correct is 1.5. That means you will not be able to correct 2 bits. Maximum you can correct only 1.5 bit. That means how many bits you can correct? Only 1 bit, no? This has to be integer. Bit has to be integer, right? Bit has to be integer. So maximum you can correct 1.5 bits. What does that mean? That means actually you can correct up to 1 bit, right? ये फिर online thread. Are you able to understand this point? What I am saying? That if your answer is coming non-integer, then lower integer you need to take. Then maximum number of bits that I can correct, that would be 1. Is that clear to you? Okay, so we will write down the conclusion, but I hope the concept is clear, because a lot of places I have seen that directly formula are written. D minimum is equals to td plus 1. Sir, this should be written as tc. No. In the books as well, you would see that this is written by t only. So we will follow the convention of books. Detectable errors are written by td, but correctable errors are not written by tc. It is written by t only. Okay, so we will follow the convention of a book only. So this is t. So d minimum equals to t plus 1 and d minimum equals to td plus 1 and d minimum equals to 2t plus 1. This can you remember? Surely, sir, I can remember it. Okay, so for a code, maximum Hamming distance is equals to, minimum Hamming distance is equals to d minimum. Maximum number of detectable errors I will call as td, and maximum number of correctable error is tc. So from there you would know that d minimum is equals to td plus 1 and d minimum is equals to, not tc, only t I will write down, that would be 2t plus 1. And from here, if I need to find out the value of d minimum, td, that would be d minimum minus 1. So d minimum would be integer, 1 is also integer. So this will surely come out to be integer only. But sometimes it may happen that this is not coming out to be integer. If this is not coming out to be integer, then what you will do? You will take just a lower value, least integer function, just the lower value you will take. Is that clear to you? Okay, do you understand the meaning of this sign? Just lower value you will take. So d minimum is 3. Find out the maximum number of detectable and correctable bits. So sir, maximum number of detectable bits would be equals to 2. And sir, maximum number of correctable bits would be equals to 1. And always remember one thing, that your correctable bits would be lesser than the detectable bits. Your correctable bits would be lesser than the detectable bits. And it is pretty obvious as well. You can relate it with the life as well. Like if you go to one guy and you ask him, what all error I am having? Like what is wrong with me? Just go to one guy and ask what is wrong with me. He will give you a lot of things, that these things are wrong with me. And now you ask him how to improve those things. Hardly he will be able to tell this thing you can improve. He also doesn't know the answer of these two. Right? So that means people will be able to detect the error. So more errors could be detected, but lesser error could be corrected. Right? You will be able to tell what is the problem, but how to solve that problem, that no one can tell. So always this thing would be more and this thing would be less. So you will remember the formula t plus 1 to t plus 1. And now you don't need to worry, sir, what was coming for detectable, what was coming for correctable. You will solve the problem with respect to that only. You will realize that which will be detectable, which will be correctable. Like here, what I would do, sir, I will blindly apply the formula t plus 1. And one thing I know that, sir, other formula that I remember, that is 2t plus 1. So this much you can remember, right? So what you will get, sir, here I am getting 2.5. And sir, here I am getting 5. That means this is more. Surely it will be detectable error. And this is correctable error, which is non-integer. So what I need to do, I need to take the integer. So my number of bits that would be corrected, that would be 2. So don't put pressure of the formula. For the detectable, this formula would come, correctable, this formula would come. Simple thing you will relate, that people will be able to recognize the error more, but they will not be able to correct it. So detectable error, correctable error. Detectable error would be more, correctable error would be less. So 5 bit of error they will be able to detect, but only 2 bit of error they will be able to correct. Okay? Is that understandable to you? So these two formula are directly taught, but we have understood it with respect to the example, and with respect to example, very easily we are able to understand it. Is that clear to you? Okay. Next, we need to study special type of code now, linear code. So what is code? Code is the set of a code word. Now there is some property of a linear code. Now what all are the properties that we will understand with respect to example. And now every code is represented by n comma k, where n is the code word length and k is the number of message bits, or better I should write down k is, this doesn't look good, that k is the number of message bits. This doesn't look good. What I will write down, k is data word length, right? This would look better. K is nothing but data word length. Or you can say number of bits that are used in a message word. In your one message, let's just say I'm sending 001, then 3 bits are used. So that is your k. So every code will be written as n comma k. So there is 5 comma 2 linear code. What all are these properties, sir? We will understand that. Have some patience. Okay. So there is something called linear code. Do you remember linear system? Right? You remember linear system. If I am sending x1t, what I will get? y1t. If I am sending x2t, what I will get? y2t. If I send x1t plus x2t, what I will get? y1t plus y2t. Okay? Right? If you add both of them, this will also be added. So similar thing would happen with linear code as well. Is that clear? So let's see that. Have some patience. So 5 comma 2 is a linear code. 2 code words are these. So 2 of the code words are, your code word C1 is 10110, and other one is 11010. Okay. Now just let me know one thing. How many code words you will get? What is the value of k? Sir, value of k is 2. Value of n is 5. That means value of m is 3. So if value of k is 2, that means I will get 2 to the power k, 4 code words. So total code word that I will get is 4. But how many code words you are getting? Only 2. What they are asking you to find out? Find out the remaining code word. Now if it is a linear code, then 101% sure is that all 0 code word is always a valid code. What is the meaning of all 0 code word? That everything is 0, 0, 0, 0, 0, 0. So here what is the code word length? Sir, code word length is 5. So surely one of the code would be 0, 0, 0, 0, 0. And in your all cases, in all the cases, these length will always be same. So you don't need to worry, sir, this is having 5 bits, this is having 5 bits, this may have 4 bits. No. Always the length would be same. So your code words are 10110, other code word was 11010, and since you saw that it is a linear code, so linear code have a property that all 0 code word will always be a valid code. So this will surely be a valid code for sure. There is no doubt about that. Is that clear to you? Now what would be the other code? So the other code you can find out, always your linear code follow one property, that if you do XOR of this guy with XOR of this guy, then you will get a new code. What I mean to say is that, sir, as of now, you know that these codes are there. As of now, you know that these codes are there. Now you take any two code word, do their XOR operation. Whatever the code word that you are getting, do their XOR operation. Now, whatever the code word that you are getting, that would be a valid code word for sure. So I am taking 0 0 0 0 1 0 1 1 0. If I do their XOR operation, what I will be getting? 1 XOR with 0 1, 0 XOR with 0 0, 1 XOR with 0 1, 1 XOR with 0 1, 0 XOR with 0 0. Is it a valid code word? Yes, sir, it is a valid code word. We already know that. Now, sir, what if I do the XOR of these two guys? If you do the XOR of these two guys, what you will be getting? Sir, again, sir, I will be getting 1 1 0 1 0 only. Is it a valid code word? Yes, surely it is a valid code word. 1 1 0. Here only you can see, no? It is a valid code word. Now, sir, what if I do the XOR operation of these two guys? So, if I do the XOR operation of these two guys, I will get 0 1 1 0 0. What I am getting? 0 1 1 0 0. 1 XOR with 1 0, 0 XOR with 1 1, 1 XOR with 0 1, 1 XOR with 1 0, 0 XOR with 0 0. So, this will be your fourth valid code. Now, someone will say that, sir, if this is a valid code, sir, if this is a valid code, so what I would do? This is also my valid code now. Now, if I do the XOR operation of these two guys, then whatever the code that I am getting, that should also be a valid code. So, surely it will be a valid code. Do the XOR operation of these two guys. 1 XOR with 0, 1. 1 XOR with 1, 0. 0 XOR with 1, 1. 1 XOR with 1, 1. 0 XOR with 0, 0. 1 0 1 1 0. Is that a valid code? 1 0 1 1 is 0. Yes. That means in linear code, you can pick any two code word, do their XOR operation. Whatever the final code word that you will get, that will be a valid code word for sure. So that means the fourth code word would be 0 1 1 0 0. In these four code words, you can pick any two code word. In these four code words, you can pick any two code word, do their XOR operation. The whatever the code word that you will be getting, that will be one of these guys only. So this is the meaning of linear code. The sum of two code word belonging to the code is also a code word. Okay, from the code you take any two code word, do the sum of that, you will get a valid code word for sure. Someone would be saying that, sir, what if I do the XOR operation of these two guys, this guy and this guy? Do the XOR operation. 1 XOR with 0 1, 0 XOR with 1 1, 1 XOR with 1 0, 1 XOR with 0 1, 0 XOR with 0 0. Okay, so properties are clear to you, right? Pick any two code word, do the XOR operation, you will get the fourth code. Do the XOR operation of this one, you will get this one. Do the XOR operation of these two guys, you will get this one. And 0 0 0 will always be a valid code word. So 0 0 0 will always be a valid code word. So these two properties are clear. Now what this property is saying? The minimum Hamming distance between any two code word is any two code word. Now the minimum, fine. What is the meaning of this one? The minimum Hamming distance between two code word. What that would be equivalent to? Minimum Hamming distance between two code word is equals to minimum distance of code. What was your minimum distance of code? Minimum distance of code was minimum Hamming distance between any two code word. So basically what it is saying that, sir, you are having four code words here, right? You are having four code words. Now, sir, you will calculate the distance between these two, then these two, then these two, then these two, then these two, and then these two. Whatever the minimum distance that you get, that would be equals to W minimum. So let's check that out. Let's see what I am trying to say. A very, very important property which no one actually tells. People only study these two properties about linear code. If you have already studied this topic, then I am pretty sure that you have studied only these two properties. But this is also one of the valid property of a linear code. What this property is saying, that, sir, you are having these four codes. So first thing what you do, what they are asking here, minimum weight and minimum distance. Yeah. So first thing what you do, sir, find out the weight of C1. Sir, weight of C1 is coming out to be 3. Sir, weight of C2 is coming out to be 3. Sir, weight of C3 is coming out to be 0. And sir, weight of C4 is coming out to be 2. Okay. So in this question, what they are asking, find the minimum weight of code. Ignore all zero code word. All zero code word. All zero code word. Is that clear to you? This question I am making a change that you need to find out the minimum weight of a code, minimum weight of this code, but you need to ignore all zero code word. This would be written that you need to ignore this all zero code word. All zero code word, you need to ignore this one. So what will be the minimum weight? So the minimum weight will be equals to 2. I need to ignore this one. This is ignored. Because I know that for a linear code, all zero code word will always be there. Like for a linear code, this will always be there. And if this will always be there, then what is the meaning of minimum weight? Minimum weight will always be 0 only. So I am ignoring this one. Okay. Now what you need to find out? You need to find out the minimum distance of the code. What is the meaning of minimum distance of the code? That means, sir, you find out the distance between C1, C2 first. What is the distance you are getting? Sir, 1 bit, sir, 2. Distance is 2. Then you find out the distance between C2 and C3. So that is coming out to be 3. Then you find out the distance between C2 and C4. So that is coming out to be 1, 2, 3. Then sir, you find out the distance between C1 and C4. So that is coming out to be 1, 2 and 3. Then sir, you find out the distance between C1 and C3. So that would be 3. And then you find out the distance between C4 and C3. So that would be equals to 2. Now what is minimum of them? So D minimum is actually coming out to be 2. Minimum of them is 2. So sir, W minimum was coming out to be 2. So D minimum is also coming out to be 2. So for a linear code, always and always, D minimum would be equals to W minimum for sure. Always. Where W minimum is calculated, considering that you are ignoring the all zero code word. So what is this line written? The minimum Hamming distance between any two code word, or you can say the minimum distance of the code will be equal to the minimum weight of any non-zero code word. Any non-zero code word. So these are the weights of the code word 3, 3, 0, 2. So what is the minimum weight? That is 2. And between the distance of these two guys, what is the minimum distance? That is 2. So here only 4 code words there. Let's just say I frame a problem of a 7,4 linear code. 7,4 linear code. That means value of k is 4. So total number of symbols will be 16. So that means 16 data word would be there and 16 code word would be there. Now in the examination, what they are asking, find out the minimum distance of the code, or what they are asking, find out the minimum Hamming distance between the code word. That means 16 code words are there. In these 16 code words are there, C1, C2, 16 code words are there. You find out the distance between all the two code words, between C1, C2, between C2, C3, between C3, C4, between C1, C4 as well. So basically out of 16, you need to choose 2. So you do this much of calculation. Here, how many calculation I need to do? 6. That means out of 4, I need to choose 2. So you do the calculation of only 6. Out of 16, you choose 2. That means you need to do the calculation of 120. So this 120 calculation you do, this 120 distance you find out, and then whatever the minimum distance that you are getting, that distance will be your answer. So do you really think that you can do this 120 calculation? No. So in the examination they are asking D minimum, I know that it would be equals to W minimum. So I will have those 16 code. In those 16 code, I would see that which code is having minimum number of ones. So here which code was having minimum number of ones? Sir, this code was having minimum number of ones, that was equals to 2. So my D minimum will surely come out to be 2 only. Is that clear to you what I am saying? So if the number of code words are more, you cannot actually find out the distance between any two code word. It will take a lot of time. But since it is a linear code, I know the property that D minimum is equals to W minimum. And D minimum is equals to W minimum, then your job will be done. What you need to do? You need to take the minimum weight, and that would come out to be D minimum only. So these 3 properties are there. All the properties are very, very important. This topic is also very, very, very important. Is that clear to you or not? So this is the meaning of linear code. Let's see what we have next slide. So we need to study something called generator matrix. Okay, so we will study that, but it's been 1 hour. I will take a break and then I will come back. We will start studying about generator matrix. Again, a very simple topic, very, very straightforward. So we will study that and move ahead. So till this point, if you feel like that, sir, there are a lot of things. No, there are not a lot of things. Quickly we can revise. We first study the meaning of a channel coder. Data word length would be k, code word length would be n. number of parity words would be m, n will be equals to k plus n. So number of code word would be 2 to the power k, right? Set of these code word would be known as code. Hamming weight will be number of ones. Hamming distance would be by the number of bits they are differing. Then minimum distance, find out all the distance, whatever the distance that you are getting minimum, that would be the minimum Hamming distance between the code word, right? Then we study about minimum weight of the code. Minimum weight of the code, whatever the weight that you are getting, what is the minimum of that? That would be the minimum weight. Although here all zero code word also be considered, but you don't need to consider this all zero code word. All in the examination they will never ask you that 4 code word they will give, and they will ask you what is W minimum. If they ask, then answer would be 0 only. But why I said that you need to ignore 000 code word when it comes to linear code word? At that time you need to ignore it. But first we studied the concept of error detection and correction. What is the meaning of detection and correction? So here your d minimum would be equals to td plus 1 or d minimum would be equals to 2t plus 1. So number of bits that could be corrected or detected, that could be find out from this particular formula. Okay, so these two formula we have written. From there you can find out maximum number of detectable error and correctable error. One thing I told you, that number of detectable error would always be greater than equals to, would always be greater than number of correctable error, right? So this thing we have seen, and then we studied about linear code. One property is there, all zero code word will always be a valid code word. Other property is there that sum of any two code word would be the next code word, and d minimum is equals to w minimum. So these are the property, and any code is represented by n comma k. So first n would be written, then k would be written, right? So n will be representing the bits in the code word, k would be representing the bits in the data word. So this is how it would be written, d minimum equals to w minimum. Okay, and now we will study something called generator matrix. So what will be the job of this generator matrix? What is the name? Generator matrix. So what it will generate? It will generate the code word. So what generator matrix do? Generator matrix will generate the code word. So let's just say our data word was of length k and our code word was of length n. So n is equals to, and here we are using the parity bits. Parity bit is m. So n is equals to k plus m, right? So 5 comma 2. So you are using data word length is 2. Number of bits are 3. Okay. So your code word will have a length of 5. Now this generator matrix G is given. Sir, how this generator matrix came into action, we will see that. Sir, how to create this matrix, we will see that. But as of now, this generator matrix G is given. From this generator matrix, you need to find code word with respect to all the data word, and you need to find out the minimum distance of code. Minimum distance of code means minimum distance between the code word. Minimum distance between code words. This is something that you need to find out. Okay. So here data word length is 2. Data word length is 2. That means how many data words are possible? If data word length is 2, that means 2 to the power 2, 4 data words are possible. So if 4 data words are possible, what does that mean? 4 data words are possible, and each data word would be having 2 bits. That means one data word would be 00, other data word would be 10, other would be 10, and other would be 11. So these are the data words that I will be getting. I am representing it by capital D. Say yes or no. Data words that I am getting are 00, 01, 10, 11. So here at the input of channel encoder, you will be having 00, 01, 10, 11. Now this channel encoder would be converting these 00 into 5 bits. This 00 will be converted to something that I don't know. This 01 will be converted to something that I don't know. This 10 will be converted to something that I don't know, but I know that number of bits will be 5. Is that clear to you? Data word length is 2. That means at the data, how many data words would be possible? 4 data words would be possible. 4 data words are possible. Those 4 data words would be 00, 01, 10, 11. Now they will be giving you respective code words. So what all those code words would be there? Find code words with respect to all data word. So that code word would be equals to. So your code word is C equals to DG. So generator matrix you are having. Generator matrix you are having. Now data word is 00, 01, 10, 11. So with respect to data words, you can get this kind of matrix. You can get this kind of matrix, and you can get this kind of matrix, and you can get this kind of matrix. So these are the data words I am having. 0 0. So what I will do, I know one thing, C equals to dg. So I am finding code word with respect to d1. What is my d1? Sir, my d1 is 0 0. So what will be your c1? C1 would be equals to d1, which is 0 0, multiply with the generator matrix. So simply copy the generator matrix. Simply copy the generator matrix. So C1 equals to D1 into G. Now 0 will be multiplied with 1, what you will be getting 0. 0 multiplied with 0, what you will be getting 0. Here you need to do the summation, but you will do XOR operation. Whenever you talk about bits, always do the XOR operation. So 0 multiplied with 1, 0. 0 multiplied with 0, 0. 0 XOR with 0, what that will be? 0. 0 multiplied with 0, 0. 0 multiplied with 1, 0. 0 multiplied with 1, 0. 0 multiplied with 0, 0. And I am adding both of them. Basically, I need to do the addition. How do you do the matrix multiplication? A, B, C, D, E, F. So E multiply with A plus F multiply with C. So similar thing, 0 multiply with 1, 0, 0 multiply with 0, 0, 0 XOR 0 will be 0. 0 multiply with 0, 0, 0 multiply with 1, 0, 0 XOR 0, 0. 0 multiply with 1, 0, 0 multiply with 0, 0, 0 XOR 0, 0. Again 0, 0. So basically, your data word was 0, 0. This was the scenario. This was your channel encoder. Your data word was 0, 0. It was encoded into 0, 0, 0. It was encoded into 0, 0, 0. So I was supposed to send 0, 0, but after the channel encoder, I will be sending this particular thing. Let's talk about 1, 0 or 0, 1. What is our C2? Sorry, what is our D2? D2 is 0, 1. So D2 will be 0, 1. So my D2 is, C2 will be equals to D2 into G. So D2 is 0, 1. Multiply with the generator matrix. So 0 multiply with 1, 0. 1 multiply with 0, 0. So 0 XOR 0, 0. Next. 0 multiply with 0, 0. 1 multiply with 1, 1. 0 XOR 1, 1. 0 multiply with 1, 0. 1 multiply with 0, 0. Okay, 0, 0. 0 multiply with 1, 0. 1 multiply with 1, 1. 0, 0. So with respect to data word, you wanted to send 0, 1, but now what you will be sending? You will be sending 0, 1, 0, 1, 0. Do the same thing with C3 as well. Can I do the same thing with C3 as well? Yes, sir. Surely you can do the same thing with C3 as well. Here I draw a line. This C3 is 1, 0. Right? C3 will be D3 into G. D3 is 1, 0. D3 is 1, 0. 1, 0 will be multiply with this one. So 1 XOR 1, 0 XOR 0, 1. 1 XOR 0, 0 XOR 1, 0. 0, 0. You can do the calculation now. 1 multiply with 1, 1. 0 multiply with 0, 1. 1 multiply with 1, 0. Sorry, 1 multiply with 1, that would be 1. 0 multiply with 1, that would be 0. So 1. And then this would be 0. Again, let me check. 1 multiply with 1, 1. 1 multiply with 1, 1. Yeah, correct. So you wanted to send 1, 0, but actually you are sending 1, 0, 1, 1, 0. Okay. What about C4? Sir, in C4, I actually wanted to send 1, 1, but what I will be sending? Sir, I will be sending this thing. This is something that I will be sending, sir. So what I am sending? 1 multiply with 1, 1 multiply with 0, 1 only. 1 multiply with 0, 1 multiply with 1, 1. 1 multiply with 1, 1 multiply with 0, 1. Now this one, 1 multiply with 1, XOR 1 multiply with 1. So 1 XOR 1, what that would be? 0. Actually it should have come, sir, 1 plus 1 is equals to 2. But no, 1 plus 1 is not equals to 2, 1 plus 1 is actually equals to 0. So this would be 0 and next would be 0. So sir, I wanted to send 1 1, but actually I am sending 1 1 1 0 0. So basically this was my scenario, that there was this channel encoder and then there was this data word, and this is your channel encoder. So input was 0 0, like data word was 0 0, symbol S1 was 0 0, but actually instead of transmitting S1, I am transmitting this one. If input is 0 1, instead of transmitting 0 1, I am transmitting 0 1 0 1 0. Instead of transmitting 1 0, I am transmitting 1 0 1 1 0. And instead of transmitting 1 1, I am transmitting 1 1 1 0 0. So this generator matrix has helped you to find out all the possible data words. Sorry, all the possible code words. So these are my all possible code words. 4 code words I am getting. Okay. Although nowhere they said that it is a linear code. They did not talk about linear code, but when you notice this particular thing, these are linear code only. All 0 code word is there. Okay, this should be given. It is a linear code, yeah. Because generator matrix they are talking about, no. So generator matrix, all other matrix we are going to see. They will talk about. They will be linear code only. So sorry to say, this is linear code only. And looking at the code words. So basically, what code words I am getting, I will write down all the code words. They are very important for me. So code words are all 0. Other code word is 0 1 0 1 0. The other code word is 1 0 1 1 0. And sir, the fourth code word is 1 1 1 0 0. Okay. Now you can check that. Take any two code word, do the XOR operation. Do the XOR operation of these two guys. 1 1 0 XOR with 1 1 1 XOR with 0 1 0 XOR with 1 1 1 XOR with 1 0 0 XOR with 0 0. C4 I am getting. Take C3 and C4. 1 XOR with 1 0 0 XOR with 1 1 1 XOR with 1 0 1 XOR with 0 1 and 0 XOR with 0 0. C2 I am getting. So take any two code word. When you do the XOR operation, you will be getting the next code word. And all 0 code word is a valid code word. That's for sure. So all these 4 code words I am getting. Okay. Right. Now just let me know what is your D minimum. Minimum distance. First, let's talk about W minimum. What is your W minimum? Forgetting about W minimum for non-zero code word. So forgetting about all 0 code word, what is your W minimum? So sir, here the weight is 2. Here the weight is 3. Here the weight is 3. So what is your W minimum? That is 2. So what will be your D minimum? Arey yaar. What will be your D minimum? The D minimum would be 2. So D minimum is coming out to be 2. Do I need to check it? Yes, you can check it. What you can do? So D C1 C2 if I want to find out. So D C1 C2 is coming out to be 2 only. So D C2 C3 if I find out. So that is coming out to be 3. So D C3 C4 if I find out. So that is coming out to be 1 2. D C1 C3 if I find out. So that is coming out to be 3. So D C1 C4 if I find out, that is coming out to be 3. And so D C2 C4 if I find out, C2 C4. So 1 2 and 3. So you can see here what is the D minimum? That is equals to 2 only. But actually I don't need to check. Why is that so? Because it is a linear code, and since it is a linear code, for the linear code I know a property. The property says that whatever your W minimum is there, ignoring the non-zero code word, that would be your D minimum, and it is coming out to be the same as well. Now other interesting observation is also there. Do you see generator matrix? Do you see this generator matrix? Okay. What are the rows of generator matrix? Rows of generator matrix. Row 1. What is your row 1? 1 0 1 1 0. And what is your row 2? 0 1 0 1 0. Both are a valid code word. With respect to which data word, I don't care, but surely both are the valid code word. 0 1 0 1 0. This was your C2. 1 0 1 1 0. This was your C3. So I know that these would be my valid. These two would be my valid code words for sure. That means just by looking at the generator matrix, I got to know that I am having these two code words for sure. If I am having these two code word and it is a linear code, so one thing I already know that I will surely have a all zero code word. And if I need to find out the other code word, can I do it? Yes sir, just do the XOR operation. 1 1 1 0 0. So answer would be 1 1 1 0 0. So if they wanted me to find out this generator matrix, they would give me, and they wanted me to find out what is your valid code words, what I would have done. So directly I would see this generator matrix. The rows of generator matrix would always represent a valid code word. The rows of generator matrix always represents a valid code word. Sir, how this generator matrix is made, we will tell you, don't worry about that. But rows of generator matrix always tells the valid code word. I got to know that C2 and C3, this row and this row will be a valid code word. Since it is a linear code, all zero code word will also be a valid code word. So which code word is left? Only one code word is left, which will be XOR of these two operations. And I got the XOR operation. So C1, C2, C3, C4 I got. And what if now they are asking me D minimum? In the examination, what they asked me? They gave me this generator matrix and they asked me D minimum. What they asked me? They asked me D minimum. Yeah. They asked me D minimum. So I know that I am having these 4 valid code words. What I am having? These 4 valid code words. And I know that my D minimum would be equals to W minimum. Surely there is a condition. The condition is that you need to ignore non-zero code word. So what answer I will be getting? Sir, here the weight is 3, here the weight is 2, here the weight is 3. So what should be the answer? Sir, answer would be 2. So my D minimum would be equals to 2. Is that clear? In the examination, they gave me this generator matrix and they asked me what will be my D minimum. So I know that these will be my valid code word. I got these are my valid code word. From here, I got my 4th data code word. Along with that, I also know that this will also be my, so not data code word, I should say code word only. So this is my 4th code word and this is my 1st code word. So all 4 code word I got. They are asking me D minimum. Now I will not calculate the distance between these two guys and then these two guys, then these two guys. This distance I will not calculate. This much calculation I will not do. What I will do? Sir, I know that D minimum is equals to W minimum. So sir, my D minimum would be equals to the minimum weight of these codes. So this is having weight of 3, this is having weight of 2, this is having weight of 3. So answer would be 2. This is the other observation that we are getting. One more observation is there. So whatever the generator matrix they have made, in this particular generator matrix only, whatever the generator matrix that they have made, in this particular generator matrix only, you will surely get your W minimum. Here what is the weight? Sir, here the weight is 2 and here the weight is 3. So sir, if they are asking me directly D minimum, I don't need to calculate a 4th code word. I don't need to calculate 1st code word. Sir, whatever the weight you are getting in this matrix, in these weights only, whatever the minimum weight that you are getting, that will be your final answer. I think you are not understanding much, or you are understanding completely. What I am saying, observations I am taking. Generator matrix was given. First observation that I took, that all the rows of generator matrix, they represent a valid code word. So if I know these 2 code words, I can determine other code words as well. I was able to determine all 4 code words. Now in the examination, they are asking me D minimum. Now what one student would be doing? That sir, he knows all 4 data, he knows all 4 code words. So what he would do? He would calculate the distance between these 2 guys, then these 2 guys, then these 2 guys. In that manner, he will do 6 calculation and he will mark that D minimum is equals to 2. Now the other smart student, who knows the property of linear code, what he would be doing? He knows that sir, I am having 4 code words, all are linear code. Then whatever the minimum weight that you are getting, that will be your D minimum. So here I am getting, sir, minimum weight equals to 2. So this will be my D minimum. Now other smarter student who has done more observation, what he would say? That, sir, I know that I will be getting 4 code word. I know that I would be getting 4 code word. All of them will have some different minimum weight. All of them will have some different minimum weight. But sir, I have observed one thing, that always and always the minimum weight code word is hidden in generator matrix only. So in the generator matrix only, this minimum weight code word would be there. So whatever the code words that you are getting from the generator matrix, they will only represent W minimum. And if you know that W minimum, then you surely know that D minimum as well. Is that point clear to you or not? All observation. Okay. And you pick the notes of any educator. These things you are not going to find out in any educator's notes. And last year, the question came from here. And ditto same problem was given in that book that I told you about. I will share that book in the Telegram group. I cannot share the book actually. I will share the name of the book. You need to ask me. Okay. So ditto same question was given. And if I had taught information theory, I would have surely taught this concept. And you can check anyone's content. This concept was not even there. Till this date, this concept is not there. They are also doing the same thing, that they will find out all the code words, then they will find out the minimum distance. Like first method that I told you. What is the first method? That, sir, you send 0, 0, 0, 1, 1, 1 and 1, 0. In that manner, you find out all the code words. Once you have find out all the code words, from these code words, what you see, you calculate the distance between the two guys, then whatever the D minimum that you are getting, that will be your final answer. But the one who is very smart, who knows the conclusion of everything, what he would see? He would see this row, this row. Okay. So in this row, what is my minimum weight? Minimum weight is 2. That would be my D minimum. That's it. So these two conclusions are very, very important. Each row of generator matrix represents a valid code word. At least remember this one. This is must remembering. Okay. Each row here, this is 7,4 linear code. Okay. Linear block code. What is the meaning of block code? Block code means your length of code word would be uniform. All the code word would be of 7 bits. All the code word would be of 7 bits. Right. What they are asking? They are asking D minimum. So one guy would know that, sir, here 7,4, that means value of k is 4. So how many code words you will be getting? The code words that I will be getting is 16. So 16 code word I will be getting. So C1 will be 1 0 0 0 0 1 0. Sir, C2 0 1 0 0 1 1 0. Sir, C3 0 0 1 0 1 0 1. Sir, C4 0 0 0 1 0 1 1. So in that manner, C5 would be there, C6 would be there. Total 16 code word would be there. So 16 code word would be there. So one thing I can do that, sir, I can find out all the 16 code words and then I can see what is my minimum weight, because I know that my D minimum would be equals to W minimum. So sir, I will find out all the 16 code word and then I will say what is my minimum weight. Now whatever the minimum weight that I will be getting, that would be my final answer. But I am smart. I know that the minimum weight has been hidden in these 4 guys only. So here what is the weight? Sir, here the weight is 2. What is the weight? Sir, here the weight is 3. What is the weight? Sir, here the weight is 2. Sorry, 3. Here the weight is 3. So minimum weight will surely be equals to 2 only. You can find out all the 16 code word. How will you find out all the 16 code word? Do the XOR operation of these 2 guys, then do the XOR operation of these 2 guys, then do the XOR operation of these 2 guys, then do the XOR operation of this one, then do the XOR operation of this one, then do the XOR operation. In that manner, more code words you will generate, then keep on doing the XOR operation and you will find out 16 code words. Okay, and in those 16 code words, what you would do? You would find out the weight of all the code word. Here the weight is 3. Sorry, here the weight is 2. The weight is 3. The weight is 3. The weight is 3. Now let's just say I find out another code word, that is C5. So C5 would be XOR of these 2 guys. So 1 XOR with 0 1, 1 XOR with this would also be 1 0 0, then 1 0 0. So here the weight is coming out to be 3. So in that manner we will find out everything and we will notice one thing, that minimum weight will be 2 only. So here the simple answer of D minimum would be equals to 2. Very, very straightforward, very, very simple. D minimum is equal to 2. Okay, so just by looking at the generator matrix, I would be able to tell the answer. I don't need to do all this analysis, because in the generator matrix only all the valid code words are present, and in the generator matrix only the minimum weight code word is also present. Okay, so from the generator matrix itself, you can see the second line, the minimum weight among all these rows gives the minimum Hamming distance d minimum of the code, or it gives the minimum weight of the code as well. So minimum weight of the code is hidden in this generator matrix only. Is that understandable to you or not? If it is understandable, you need to comment down. Just comment down that, sir, awesome concept, and more awesome things are going to come up. You need to have some patience. But as of now, we will see what is the pattern of generator matrix. How do we generate the generator matrix? Okay. What will be the order of generator matrix? Sir, this generator matrix, you have understood the property of generator matrix, sir. What is the use of generator matrix? Everything we have understood. But sir, how do you generate a generator matrix? That we need to check. So that we will see. But as of now, did you like this concept or not? So comment down that, sir, we have understood something new here. We used to study channel coding in formula based manner, sir. We used to remember the things, but now, sir, actual things we are understanding. Okay. So we will see the pattern of generator matrix, how to generate the generator matrix. But before that, I need to take a break now. Okay. Okay then, yeah. So I will take the break and then I will come back. Yeah, hi everyone. So let's see the generator matrix. So what will be the pattern of generator matrix that we will see? Because in the previous video we have seen that these generator matrix were given, right? These generator matrix were given. How did we create that generator matrix? That we are going to see. Okay. So what is given, that we need to create a generator matrix for 7,1 code. So generator matrix would be given. Most probably in the examination, generator matrix would be given. But what is the pattern of that generator matrix, that you need to understand. So I will denote my generator matrix by G. Okay. Now first thing I will see that what is my data word length? 7. What is my code word length? That is 4. That means each data would be represented by 4 bits. Each data would be represented by 4 bits. So first thing what I need to do is that when I am making this matrix, so first thing I will do, I will make an identity matrix of 4 cross 4. What I need to do, sir, I saw that 7, 4 code is there. That means the number of data bits that I am using, that would be 4. That means here what I will do, I will make a 4 cross 4 identity matrix. So 4 cross 4 I matrix or identity matrix I will make. Now here, after this, parity bits would come up. What would come up? Parity bits. Now parity bits could be anything. It might happen that, sir, it is 101. It might happen that for this one it is 011. For this one, sir, it is 111. For this one, sir, it is 101 could also be possible, right? But let's take a different one. Let's take a 110. So these are the parity bits which could be completely random. I am not sure about these parity bits. It could be anything. But did you understand the pattern? The pattern says that first you are going to make an identity matrix of order k, and here you are having parity bits. So what is the order of this matrix? Sir, 4 rows are there and 7 columns are there. That means what is the order? Sir, order is k cross n. You will remember by G is having k cross n. So you will remember the term gk. Okay. We will study parity matrix as well. This is known as parity matrix. Okay. This is your parity matrix. So this parity matrix we will study. It will have a order of m cross n. What is k? What is n? What is m? Everything you know. K plus m is equals to n. So parity matrix will have an order of m cross n. Generator matrix will have an order of k cross n. So you need to remember this one. How will you remember? Gk. So if you remember Gk, you would remember one thing, that in both of them n would be coming in the end. So k cross n. And what about h? Then what would be left? K is coming, n is coming. Then what is that? M is left. So h will have an order of m cross n. So you need to remember anyhow. I hope you will be able to remember it. Okay. So G will have k cross n, h will have m cross n. Is that clear to you? So these parity bits are random. I don't know. In a manner that code is defined, I would be able to understand these parity bits. I don't know what all are these parity bits. These parity bits are very, very random. Okay. Now one thing I told you, that each row in generator matrix would represent a valid code word. This line I told you, each row in generator matrix would represent a valid code word. So this is a valid code word for sure. This code word is valid. Right? All these are valid code words. All these are valid code words. Now you know that these are parity bits. So what do you think what these are? These are your data bits. Say yes or no? So generator matrix will simply tell you that with respect to 1000, when your data bit is 1000, at that time you are sending 101. When your data bits are 0100, at that time you are sending 0100, 011. That means with respect to 1000, your parity bits are 101. With respect to 0100, your parity bits are 011. With respect to 0010, your parity bits are 111. With respect to 0001, your parity bits are 110. So this portion, this left side of portion is representing data bits and this is representing parity bits. Is that understandable to you or not? Let's go back to our previous example. In this example, you see, this is actually representing data bits. So when I was transmitting 10, what did I see? With respect to D3, what you are getting? 10110. So when you were transmitting 10, you are getting 10110. So this particular portion was representing your data bits. Is that clear to you? Here 01 I was transmitting, I was getting 01010. So this was representing your data bits. What about 11? 11, with respect to 11 you are getting 100. With respect to 00, you are getting 000. Now there is another point, there is one more important point, is that it is not necessary that first identity matrix would be written and then parity matrix would be written. What I mean to say is that they can define generator matrix in this manner as well. In which manner? In this manner, that first what you need to see, sir, 7,4 code is there. 7,4 code is there. What does that mean? That means, sir, k is 4. What is the meaning of k is 4? So data word would be of length 4. Data word would be of length 4. That means I need to make identity matrix of order 4. I need to make an identity matrix for 4 cross 4 order. So that identity matrix I can make here as well. 1000, 0100, 0010, 0001. Right? So this is the identity matrix, and here I can write down the parity bits. Okay, and let's make the same parity bit only 101. This is the parity bit. These are the parity bits. 101, 011, 111, 011, 111, and 110. It could be anything. It would be defined how this 7,4 code is defined. Is that clear? What I am saying? These parity bits are defined as per the code. What kind of coding you are using? If you are using Hamming code, then this kind of code would be different. If you are using some other kind of code, then this coding would be different. Parity bits will be defined with respect to the code that you don't know. Here I am putting random words. 101 randomly I am putting. 011 randomly I am putting. 111 randomly I am putting. 110 randomly I am putting. Okay. So these are very random codes. These are very random parity bits. But I am just telling you the pattern. What does the pattern say? That, sir, you need to see what will be my data word length. Data word length is 4. That means I will make the identity matrix of 4 cross 4. So this is my identity matrix of 4 cross 4. Eventually what it is representing? It is representing data word. It is representing data word. So your data word are 100, your data word are 0100, 0010, 0001, and these are representing your parity bits. What it is representing? It is representing your parity bits. So this could be the order of generator matrix. This could be the order of generator matrix. Now in the worst case, what may happen? In the worst case, your parity bits and data words could be shuffled. What I mean to say is that this would be your worst case. Okay, this would be your worst case. I know that, sir, there would be identity matrix of 4 cross 4 for sure, because I know my code word is having a length of 4. That means identity matrix of 4 cross 4 would be surely there. So what they would do? First line they have written down in this manner. Then the second line they have written down in this manner. The third line they have written down somewhere here. And the fourth line they have written down somewhere here. In between they will include parity bits like 101, 101. They will include 0, 1, 1. They will include 1, 1, 1. And then they will include 1, 1, 0. Okay. So let's just say if I call this position as C1, this position as C2, this position as C3, C4, C5, C6, C7. Basically, one of my code word is represented by C1, C2, C3, C4, C5, C6, C7. Okay. Then C1, you could see that, sir, this is the part of identity matrix 1 0 0 1. Like basically I need to identify where is my identity matrix. So you can see that, sir, 1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 this part and this part. You could see that, sir, these are the part of identity matrix. That means C1, C2, C4 and C6. C1, C2, C4 and C6. These are representing my data bits. These are your data bits. These are your data bits. And these are your parity bits. Okay. C3, C5, C7 are your parity bits. C1, C2, C4, C6, they are your data bits. So this is the scenario. Is that understandable to you? So this is known as asystematic generator matrix. Okay. And these two are known as systematic generator matrix. Till this point in gate examination, till this point, till today, always this matrix has come. Always. That first they will make identity matrix here and here they will write down parity matrix. So this is the systematic way that they have introduced till this date in the gate examination. This may also happen, right? Here they will write down identity matrix. That means this is representing your data word and this is representing your parity bit. Or what may happen is that they can frame it randomly as well. But it is not important for you that, sir, where is the identity matrix, or what will be your data word. It is not important for you. It is not important for you. What would be important? What they would do? What kind of questions they will ask? They will give you a particular matrix. Then what they would say? That I am transmitting a data of, let's just say, 0110. What would be the code word with respect to that data? These kind of questions they will ask. Then you know that what I need to apply. C equals to dg. Here we have solved the problem. C equals to dg. Right? Here also we saw. Here we did not need to find out. So basically data word multiply with your generator matrix, you will get your code word. So they will ask you to find out code word, or this kind of questions they can ask. Here you can also see what you can notice here. Here you can notice that this particular part would be your code word and this particular part would be your parity, right? Now let's just say I generated this C5 code word, right? My C5 code word was 1100100. So somehow my answer, they asked some question and the answer of that particular question was this data word. Sorry, not data word, this is code word. So they asked some question, answer of that question was this code word. Now they are asking what will be the data word here. So you know that when I went to the generator matrix, I know that first 4 bits are representing the data word, rest 3 bits are representing the parity bits. So they will be showing the parity bits. And this will be my data word. This will be my data word. And you can check, what you can check, multiplication of 1100 to this matrix, to this G matrix would result in the same code word. What I am saying, you multiply 1100 with this matrix, this answer you will be getting. And it is pretty obvious as well that with respect to this data bit, this code word should be made. So try multiplying 1100 with this matrix. So you can see that 1 will be multiplied with 1 will be multiplied with 0, 0, 0. So 1 you will be getting, then 1 you will be getting, then 0, 0 you will be getting. After that, what will be your parity bit? Sir, 1 multiplied with 0, 0. 1 multiplied with 1, 1. 0 multiplied with 1, 0. 0 multiplied with 0, 0. So what will be the parity bit here? 1. Then 1 multiplied with 1, 1. 1 multiplied with 1, 1. 1 XOR 1, 0. Next 0, 0. So parity bit would be 0. Next 1, 1, 0, 0 multiplied with 0, 0, 1, 1. So 0, 0, 0, 0. So this would also be 0. So with respect to this data word, you will get this code word only. But if code word is given, then also you should have the habit to recognize which is representing data bit and which is representing parity bit. So how would you recognize? How would you recognize which is data word and which is your parity bits? So how would you recognize? You would go to the generator matrix, you would see the pattern. You would know that, sir, it is for 7, 4 code. What does that mean? That means, sir, I will find out 4 cross 4 identity matrix. So 4 cross 4 identity matrix is saying that C1, C2, C3 and C4. These should be your data bits. So C1, C2, C3, C4, these are my data bits. That's it. And rest all are parity bits. Sir, what is the logic behind parity bits? You don't need to think. How these parity bits are written? C5, C6, C7. Sir, what is the logic behind these parity bits? I don't know. They are coming randomly. Some code they have used. It depends on the code. I don't care about the parity bits. I just know this will be my data word. Is that understandable to you or not? I hope everything is making sense to you. Is that clear? So this is known as asystematic G matrix, which they did not ask yet in the GATE examination. Okay, they never asked asystematic G matrix. They never gave asystematic. They always used to give systematic, this one or this one. Till this date they have always given this one, but you should not be surprised if this matrix is coming here and this matrix is coming here. So just I have interchanged the matrix, nothing else. So this matrix this side and other matrix this side. And in the examination, when they will make G matrix, they will not make this dot sign. Okay, they can either make this dot sign or they can ignore this dot sign. Sir, here why you did not make dot sign? Because here your data bits and parity bits are shuffled, right? Two data bits, then one parity bit, then one data bit, then one parity bit, then one data bit, then one parity bit. So data bit and parity bits are shuffled here. But here data separate, parity is separate. Data separate, parity is separate. That's why I made this dot sign. But in the examination, what may happen is that this dot sign might not be there. Okay, this whatever we call it, ratio sign, this might not be there. Okay. So now what I have written, I have just written the pattern of generator matrix. So pattern of generator matrix is identity matrix, parity matrix, identity matrix, or identity matrix and parity matrix shuffled. These are the patterns of your generator matrix. Is that clear to you? So pattern was necessary. Properties and everything we already know. Now this pattern was also necessary. Is that clear? Okay. Can we see some question regarding it? If you want to see any problem, if you want to see any question. Let me pick this one. This is your generator matrix. You would be able to solve it. Is an easy question only, not tough. Question says find out the code word for data word 1101. This is the question. Okay, you need to find out the code word for data word 1101. So what you would do, sir? I know that code word is given as DG. So sir, what I would do, 1101, and then I will write down this generator matrix. I will multiply both of them and I will get my answer. Other smart student, what he will do, what he knows, that all these are valid code words, right? Now what I need my data word to be 1101. So can I notice one thing? If I call this as C1, if I call this as C2, if I call this as C3 and this as C4. So can I notice one thing, that if I do the XOR operation of C1, C2 and C4, what I will get? Just look here. Just look at the side of your identity matrix. Because these parity bits are random, I don't know anything about these parity bits. So always I look for our identity matrix. I know one thing, that sir, this answer that I am going to get, this answer will come out to be in the form of parity bits 1101. Say yes or no? Because I know that sir, they are representing a valid code word. If they are representing a valid code word, that means sir, this part is of a data word. My data word is 1101. So this part is of data word, and sir, this part is of parity. Now I know one thing, this is a linear code. This would be given that it is a linear code. Okay, this is given, it is a linear code. Sir, it is a linear code. If I do the XOR of any two guys, I can get, I can do the XOR of any code words and I will get new valid code word. So if I do the XOR operation of C1, C2 and C4, so what data word I am getting? 10000100. So data word you will be getting is, sir, 1 1. Here 00 is there. Now 00 will be XORed with 01. So what you will be getting? 01. Just do the XOR operation of your parity bits as well. So what I need to do, 101 XOR with 011 XOR with 110. So if you do the XOR of these two guys, what you will be getting? 101. So 101 XOR with 101, what you will be getting? 000. So what is the answer you are getting? Sir, 101 XORed with 011 XORed with 110. So 110 11 011 XORed with 011, you are getting 000. So this will be your valid code word. So your answer would come out to be 0001101. This would be your answer. 99% of the students will be solving like this. Okay, but let's just say if I make a very big matrix in the examination, then it would take a lot of time. Like this is 7,4. What if I make the matrix for 15,11? If I make this much of big matrix, it may take a lot of time in the examination, no? So smartly you need to see that your data word is this one. Can I find out the code word for this particular data word from this matrix only? Very easily you can find out. Otherwise, what you can do? Like method says C equals to DG. So 1101. Like basically first these things came up and then these things came up. Are you able to understand this point? Like first they noticed this thing that with respect to 1000, if I write down these parity bits, then I can make a matrix. From this matrix I can solve for any data words. So first this method came up. Then with respect to these methods, they actually made the matrix method. So here we are going by the core concept, but here we are going by the matrix. Right? So here you don't need to use your brain. You know that data word is given, C equals to DG, 1101 you write down, generator matrix is there, just multiply both of them, you get your answer. If I want to use my brain, then this is how I can use the brain, that 1101 I will get here, so I will simply do the XOR operation and then I will get the answer. So 110, then 110 XOR with 110, so answer would be 0001101. So in this method I will not even use the pen, directly I will do the XOR operation. Right? All good? So till this point what we have studied? We have studied that generation of valid code word. Code words are generated. So here our data word was there, this is our D, multiply with the generator matrix which is specific to the code only. So here what we got? We got our code word which was C equals to DG. Now this code word would be sent over the channel, right? This code word would be sent over the channel. Let's just say I wanted to send this code word 1011000. I wanted to send 1011000. Now if I wanted to send this one and the same has been received to the receiver, then it is all good. I wanted to send this one and same has come here, then it is all good. But what if one bit has been flipped or 2 bit has been flipped? That means what if there is some bit error? Right? There could be some bit error as well, no? So there this channel decoder will come into action. The job of this channel decoder would be first to determine if there is any bit error. The second job would be to correct that bit error. What are the jobs? Jobs are first to determine if there is any bit error. Second would be to correct that bit error. So now our task would be that we have generated the valid code word. Now we need to detect the valid code word as well. If there is some error in this code word, that we need to detect and we need to correct that as well. So detection and correction both we need to do. So for that new matrix came into action, that is known as parity matrix. Okay, but let's see like what is the issue here. So what we will call it? We will call it received code word. What this is known as? This is your transmitted code word. This R is known as received code word. Now this received code word could be equals to C. This received code word could be equals to C and it could not be equals to C as well. If your received code word is equals to C, that means no error. If received code word is not equal to C, that means there is some error. Okay, so let's understand it by an example. If I am saying that my transmitted code word is 1011011, okay, this was my transmitted code word. Now I am saying that when it was traveling through the channel, when this code word was traveling through the channel, its third bit got some error. Third bit from left, 1 2 3, third bit from the left got some error. That means this was received correctly, this was received correctly, 1 is received as 0, 1 0 1 1. This is something that you have received. Third bit from the left got some error, this bit got some error. Okay, so this is your received code word which is not equals to C. So can I write down my R as, just look at the screen, can I write it down in this manner? Plus means XOR operation. 1 XOR with 0, 1. 0 XOR with 0. Basically, what I am doing, 1 XOR with 0, 1. Corresponding bit XOR operation I need to do. Okay. 1 XOR with 0, 1. 0 XORed with 0, 0. 1 XORed with 1, 0. 1 XORed with 0, 1. 0 XORed with 0, 0. 1 XORed with 0, 0. 1 XORed with 0, 0. So are you getting the same thing? Yes. So wherever there is an error, in the bit wherever there is an error, what I have put? I have put 1 there. So can I write down R equals to, this was your actual code word, and then there is some error. So R equals to C plus E, can I write it down? Where this is your E and this is your actual code word. And this E is all 0, just it is having 1 at the place where there was an error. Okay. Similarly, if there is an error in a 5th bit from the left, 1, 2, 3, 4, 5, 5th bit from the left, then what you will be receiving? Sir, 1, 0, 1, 1, 1, 1, 1. This is what I will be receiving. I wanted to send 1, 0, 1, 1, 0, 1, 1, but I am receiving 1, 0, 1, 1, 1, 1, 1. So what I am receiving? 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, but actually I was transmitting 1, 0, 1, 1, 0, 1, 1 plus 0, 0, 0, 0, 1, 0, 0. This is the scenario, right? 1 XORed with 1, then 0, then 1, then 1, then 0 XORed with 1, 1, then 1 XORed with 0, 1, 1 XORed with 1, 1. So R will be receiving the same thing. So every R could be written as C plus E. If E is 0, then all good. But if E is non-zero, then there is an issue. Like if E is 0, that is representing no error. But if E is non-zero, that means there is an error. Okay. So how do we take care of this E? What this E will do, that we need to study. But before that, we need to study something called parity check matrix, or sometimes I will call it parity matrix only. So parity checker matrix we need to study. So this parity checker matrix H, what do we call it? We design parity checker matrix H in a manner that C multiply with H transpose is coming out to be 0. Basically, we design this H matrix in a manner that C and H matrix are orthogonal to each other. Is that clear? Like if you multiply this valid code word, this is a valid code word, right? But this is not a valid code word. This R is not a valid code word, because here 3rd bit from the left is getting some error. This is also not a valid code word, right? But this is a valid code word, no? This is a valid code word. So they are the valid code word. So when you multiply any valid code word with your parity checker matrix, doing the transpose, you will get 0 answer. Is that clear? Now you know one thing, that C is equals to dg. So in place of C, what I can do? dg H transform equals to 0. D is simply a data bit only. So from here, what I can see, G into H transpose is also coming out to be 0. So what do you see? Two things I can see here. C into H transform is 0. G into H transform is 0. So H matrix is orthogonal to code word matrix. H matrix is orthogonal to G matrix. Now I know how to make G matrix. I know what is the pattern of G matrix. So will I be able to determine the pattern of H matrix as well? Very easily you will be able to determine the pattern of H matrix. So we will see the pattern of H matrix, but before that, let's understand what will be the use of this H matrix. So let's just say if C is equals to R. If C is equals to R, then can you let me know the answer of this one? What that would be? I will take my received code word. I will have the H matrix. I will take the transpose of that, and then I will multiply both of them. What I would do, I would multiply my received code word, this code word, with H matrix. If that is coming out to be 0, that means I will say, sir, there is no error. But if C is not equals to R, then what will happen? Then sir, R would be actually equals to C plus E multiply with H transpose. So that can be written as C into H transpose plus E into H transpose. Sir, this will go out to be 0, but this will come out to be non-zero. So, sir, your R into H transpose will actually come out to be E into H transpose, which is not equal to 0. That means, sir, I will say that there is some error. So, I will take my received code word, I will get the parity checker matrix. How I will get that I will tell you. Then I will multiply this parity checker matrix with R matrix, and I will see whether I am getting 0 answer or non-zero answer. So, if I am getting non-zero answer, that means there is an error. That means error is detected. Now, how will I correct it? So, that we will see with respect to an example. Okay, with respect to one example, we are going to see how we will correct the error. But as of now, we have understood that how we will detect the error. So, let's take an example. With respect to example, you will be better able to understand. So, what they are asking, for a 7,4 linear code, H matrix is given. Okay, this C 0100110 you are sending, is it a valid code word? This is the question. So, if C is a valid code word, then C into H transpose is equals to 0. So, you do the multiplication C into H transpose. I will take a break, okay, because something is happening in my eyes. Okay, I will take a break. You do this particular thing. Can you take the H transpose? Very easily I can take the H transpose, right? 0 1 1 0 1 0 0. Okay, 1 1 0 1 0 1 0, and then sir 0 0 1 1 0 0 1. So H transpose I have taken, sir, right? Rows will become column, column will become rows. Multiply with C. What is C? This is your C. 0 1 0 0 1 1 0. So 0 multiply with 0. You do this calculation, I will come back. Okay. Yeah. So you try this one. What will be the answer? Answer is coming out to be 0 0 0 only. Okay. 0 multiply with 0, 1 multiply with 1 1, 0 multiply with 1 0. This is also 0. Then 1 multiply with 1 1. Then 0 0. So answer would be 0. Second row also you can multiply, answer would be 0, and third row also you can multiply, answer is 0. That means C into this code word multiply with H transpose, that is coming out to be 0. That means C is a valid code word. So 0 1 0 0 1 1 0, that is a valid code word. So what I have written, this C is a valid code word which is sent over a noisy channel. Now since there is some noise present in the channel, then what really happened? The third bit got flipped. Okay, this third bit which was 0 only, it got flipped. So it has become 0 1 1 0 1 1 0. So the received code word was 0 1 1 0 1 1 0. This was your received code word. Now you know that the bit has flipped. This is your received code word. Now is it a valid code word? There has been some error, no? So what does that mean? Sir, now I will do R into H transpose. Now I will see what happens. So let's do R into H transpose and let's see what really happens. So what I am doing? R into H transpose I am doing. So 0 1 1 0 1 1 0. What I need to do, I just need to copy it. I will just paste it here. So let's see what answer we are getting. So 0 0 multiply with 0 0, 1 multiply with 1, that would be 0 0 0 1 0 0. Let me check again. 1 0 0. So this is coming out to be 1. Okay, you can do the multiplication on your own. This would be 0, then this would be 1, then this would be 0, then 0, then 1 1 1 would be 0 only. Okay, and then you can do 0 0 1 0 0 0 0. Answer is 1. Answer is coming out to be 101. Can you see this 101 somewhere? Yes, sir. In the H transpose matrix, can you see this 101 somewhere? Here I can see. And this is your third row, right? I can see 101 in third row. And where was the error? Error was there also in the third bit. Sir, is it just a coincidence that, sir, whatever the answer that you are getting here, I checked this 101, I found it out in the third row, and the error was also there in the third bit from the left. Basically, you will start counting from here only, no? First bit, second bit, and third bit. So, error was also there in the third bit, and sir, you go to the third row only. Sir, is this a coincidence? No. So, how this magic happened? The magic happened with respect to this concept R equals to C plus E. So, let's check that out. So, for this particular scenario, can you write down R and C? So, what was my C? So, this was my C, 0, 1, 0, 0, 1, 1, 0. So, what would be your E? You know that there is an error in the third bit. So, now if you add both of them, 0 added with 0, 0, 1 added with 0, 1, 0 added with 1, 1. So, this is the R you are getting. Then 0, 0, 0. So, this is your error bit, right? And you know that when I am doing R into H transpose, what I am actually doing? C plus E into H transpose, or you can say C into H transpose, E into H transpose, and you know that, sir, this is equals to 0 only. So actually you are doing E into H transpose only. So actually you are doing this calculation, but eventually what you were doing? You were doing the calculation of E into H transpose only. So what was your E? This was your E. Or forget about this E, first let's write down the H transpose. So this was my H transpose, right? This was my H transpose. अरे भाई यार, this was your H transpose. Okay. Now, what do you think? What should be written here such that my output is the third row? What I should write down here such that my output is third row? What is third row? 101. So, what do you think? What you should write down here? You should write down 0, 0. Output is third row. 1, 0, 0, 0, 0. Are you able to think? No, it is not very easy to think, right? Like what you should multiply with, it is not the simple multiplication, it is matrix multiplication. But you can notice one thing, that 0 multiplied with 0, 0 multiplied with 0. Now only this 1 is coming into action, no? Only the third bit is coming into action. That means only third column is coming into action. So third column will be multiplied with third row. And where was the error? Error was also there in third bit. Third bit has resulted into third column, and third column is being multiplied with the third row, and that third row is coming in the output. Basically everything would be 0, only this part would be remaining. Only this particular row would be remaining. No, I hope you are able to visualize now. Like how this magic happened. That, sir, the error was there in the third bit. The answer that you got, 101, that was there in the third row. So how did you get to know that, sir, third row, third bit, how they are matching? Is this just a coincidence, or is this just a coincidence, or is there some magic? So this is the magic. What is the magic? R is equals to C plus E. So C into H transpose is 0, but E into H transpose will result into something, and when we check it, we get to know that there was an error in the third bit. If there was an error in the third bit, that's why we wrote down 1 here. That means third column now will be multiplied with third row. So output will also be third row only. So we are actually getting the output to be third row only. So this is how this magic happened. Okay. So in the examination, what kind of questions will be asked? They will give you a received code word, and then they will ask you whether it is a valid code word or not. I hope I have written a question. Yeah. So H matrix is given. Received code word is given. They are asking if it is a valid code or not. If it is not, then make it a valid code word. So what you will do? Sir, received code word R into H transpose. If it is coming out to be 0, then it is a valid code word. If it is not coming out to be 0, then what you will do? Sir, in whichever the row, my value is matching, in that particular row, there will be an error, and I will change that particular bit. So we will solve that problem. Okay. If you are making your own note, just keep some space here. Okay. If you are making your own note, just keep some space here. So it's like a movie, and you feel like that, sir, movie has ended here, right? If it is a movie, you feel like that, sir, movie has ended here. It was a good movie, but there is some twist left. Okay. Some twist will come into action, and that twist we will see after this question. So first let's solve this question, because these kind of questions can be coming in the examination. So first solve this question. So what do you see? 1 multiplied with 0, 0 multiplied with 0, 0 multiplied with 0. This is also 0. This is also 0, 0, 0, 0. Then let's check 1 multiply with 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So it is matching with 1, 2, 3, fourth row. That means there is a problem in a fourth bit. That means this is not a valid code word, not valid, not valid. So what is the actual code word? The actual code word would be 100, and fourth row is having some error. That means fourth bit should be changed. So this bit would have been flipped. So this bit should be changed. 010. So this could be a valid code word. So with respect to this generator matrix, sorry, not generator matrix, with respect to this H matrix, there would be some code words, right? This is your H matrix. This H matrix is defined for M value is 3 here and value for 7,3 code word. How did you write it down, sir? I will tell you later on. But as of now, you know that what is the order. I told you for H matrix, the order is M cross N. So value of M is 3, row is 3, and value of N is 7. So this H matrix has been written down for 7,4 code word. For 7,4. That means there would be total 16 code words, right? 7,4. What does that mean? There would be total 2 to the power 4 code words. So there would be total 16 code word. So out of these 16 code word, this will be one of the valid code word. So they asked the question that out of these 16 code word, is this a valid code word? Your answer was no. This is one of the valid code word. Is that understandable to you? Okay. So you feel like that, sir, yeah, this kind of question would be coming, and this much is taught everywhere. But there will be some twist. Let's see this question. What is the twist with respect to this question we are going to solve? Your given code word is C, 010110. It is a valid code word. This I have already checked. When you do C into H transpose, value of the matrix of H transpose is already given. When you do C into H transpose, that is coming out to be 0. This has been already checked. If you want to check on your own, you can check it. 0 multiply with 1, 0, 1 multiply with 1, 1, 0, 1, 1, 1, that would be 0 only. Then you multiply 0, 0, 1, 1, then 0, then 0, then 1, 1, 1, that would also be 0. Multiply with 0, 0, 0, and that would also be 0. So C into H transpose will come out to be 0 only. This has been already checked. So this is a valid code word. Now what really happened? Due to the noise, the code word C was received as R. That means there was an error in third bit. There was an error in fourth bit as well. So third bit and fourth bit were in error. These two bits were in error. Is that okay for you? Third and fourth bit. Third bit and fourth bit. These two bits were in error. And this is something that you received. Now try finding RH transpose. That means they are in error. That means you are receiving some other code word. Basically, your R is not equals to C. So what you are expecting? As of now, what you are expecting? You are expecting that, sir, R into H transpose should not be equals to 0. So let's try finding R into H transpose. What we are trying to find? R into H transpose. One zero one 110 100 100 010 001. Okay, so let's see what happens here. 0 multiply with 1, 0, 1 multiply with 1, 1, 1 multiply with 1, 1, 1 XOR 1, that would be 0, 0 multiply with 1, 0, 0, 0. Then you multiply this with this one, 0, 1, 0, 0, 1, 0. What is the answer? 0, because 2 times 1 is coming. Then 0, 0, 0, 0, 0, everything is 0. And there you go. So there were the error in third bit and fourth bit. I did R into H transpose, answer is coming out to be 0. R into H transpose, answer is coming out to be 0. Sir, our method is failing. Can you see 0, 0, 0 anywhere? No. Basically, you cannot see 0, 0 anywhere. Even if it was there, the concept says that if R into S transpose is 0, that means this is a valid code word. So this is a valid code word. But sir, what you actually sent? Sir, you actually sent 010110 and received was 01111010. So sir, now they are saying that it is a valid code word. Yes, it is a valid code word. Why is that so? H matrix is given for 6 into 3 code. Sorry, 6 3 code. That means there will be total 2 to the power 3 code word. That means there will be total 8 code words. Now out of these 8 code words, this is one of the code, and this can also be one of the valid code. No? Are you able to understand this point or not? Here there will be 8 code words. No? So this was one of the code word. You were sending this code word. Now what really happened was 2 bits got flipped. These 2 bits got flipped. Then what really happened? This became your R. Now this R was also a valid code word. What I am saying, this R was also a valid code word. This C got flipped, it became R. Now this was also a valid code word. So what did you understand from here? This R into H transpose. If R into H transpose is equals to 0, does that mean there is no error? Absolutely wrong. This statement is wrong. R into H transpose is equals to 0. It doesn't mean that there is no error. In this case, there was no error. There was error. No, you were actually transmitting 010110. But receiver received 01111010, and as per the receiver, this is correct. Receiver said that, sir, everything is correct. I don't need to do any correction. But actually, it was correct. No, it was not correct. So if R into S transpose is coming out to be 0, it doesn't mean that there will not be any error. But if R into S transpose is 0, what does that mean? That means R will be a valid code word. That's it. So this R into H transpose method, this parity matrix is not actually helping you to recognize the error. It is only helping in what? It is only helping in letting you know that whether the received code word is a valid code word or not. That's it. Is that understandable to you or not? A very, very, very important point. So if R into S transpose is coming out to be 0, then it doesn't mean there is no error. There could be error. Sir, I cannot comment. What I am saying is that I already know the received code word. I don't know what was transmitted. I am standing at the receiver. I only know the received code word. I know the parity matrix. I took R into S transpose. I did 0, 0, 0. I got 0, 0, 0. Now, what I will say? Whatever that I have received, that is a valid code word, but I am not sure what was sent. Okay. And one more important thing is there, when you see this matrix, I will tell you this method later on. So here 2 rows are same, right? If these 2 rows are same, then your D minimum would be equals to 2. And if D minimum is equals to 2, then maximum number of detectable error would be 1. And here there is an error of 2 bits. So he will never be able to determine the error of 2 bits. This particular matrix has been made for this 6,3 code. This 6,3 code will never be able to determine 2 bit of error. He will be able to detect only 1 bit of error. So if there was 1 bit of error, he will be able to detect it. But if there is 2 bit of error, when we did the 2 bit of error, we got to know that it has actually become a valid code word only. So the bottom line is, forget about this concept. As of now, you don't even know that what is the meaning of D minimum here. Like from the H matrix, how did I get D minimum? That I will tell you. Okay, we will study that. Don't worry. From G matrix, how will you get D minimum? That you already know. D minimum would be equals to weight minimum. So always D minimum would be equals to weight minimum only. But for H matrix, there will be a different trick. You will just have to see the rows or column. You will get the answer. That I will tell you later on. But as of now, from this slide, what you are learning? From this slide, sir, I am learning one thing, that R into H transform doesn't care about error. It only tells whether the code word is valid or not. So whenever you see a question of R into H transpose, you will always see that they will be talking about valid code word. That's it. They will never talk about error or anything. So wherever we have written no error, we need to change that. So let's get back to our concept now. So what we did, this was our received code word. Here what we saw, that R would be equals to C plus E. If E is equals to 0, that means there is no error. Can we write down in this manner? Absolutely not. So what we should have written, if E is equals to 0, that means you will cut it down. What you will write down? If E is equals to 0, that means I have received valid code word. If E is not equals to 0, what does that mean? Not valid code word. Not valid code word. Or here you can write down that error has occurred, because if you are sending a code word, that means that was a valid code word, and if E is not coming out to be 0, that means some error has surely been occurred. Are you able to understand this point? If E is not 0, that means E into S transpose will also not be 0. So R into S transpose that you are doing, that is also not 0. If that is also not 0, what does that mean? That means you sent a valid code word. Now whatever that you have received, that is having some error. Like in this example we saw, no? In which example? In this example. So here this was not a valid code word. That means there was surely some error. So if you are receiving not a valid code word, that means surely there would be an error, no? Very simple thing, very basic aptitude. I am sending a valid code word. I am sending a valid code word. Then I did R into S transpose. I am getting non-zero value. What does that mean? That means surely there was some error. You sent a valid code word, but you are receiving an invalid code word. That means there was some error, right? So if E is not equals to 0, then you can say that there was error for sure. But if E is equals to 0, that doesn't mean there was no error. There could be error, but the code is valid. So if E is not equals to 0, here E is not equals to 0, no? In this case, E is equals to 0, no. In this case, E is not equals to 0. How would you know E is equals to 0 or not? Because you don't even know what was the code word that was sent. Are you able to understand what I am saying? Not in this example. Yeah, in this example. Sorry guys, sorry. So this was the code word that we sent, and this is the code word that we received. So what is E here? E here is first bit no issue, second bit no issue, third bit issue, fourth bit issue, fifth bit no issue, sixth bit no issue. So this was your E, which is not equals to 0. Right? So surely there is some error. Surely there is some error, but you are not able to recognize that error. If I already know the received, if I only know the received code word, I would never be able to tell what was sent. Although in this question I already know what was sent. This question is just an example to make you understand what is the meaning of R into S transpose. So if you only know the received code word, you will never be able to tell what was transmitted. You already know the received code word. Now someone would ask you that this received code word, it was valid? Yes. Can you let me know what was transmitted? Sir, I cannot know. Sir, I cannot tell what was transmitted. Right? Now in this question, received code word is there. Right? There is some error in the received code word. Now if they ask you, is there any error in the transmission? You will surely say, sir, yes, there is some error in the transmission. Why there is some error in the transmission? Because sir, R into S transpose, whatever the code word that I am receiving, that is not a valid code word. That means surely sir, there was an error in the transmission. So only thing that you can conclude from this discussion is that there is some error in the transmission. When you see this particular thing, what you will say? Sir, there is some error in the transmission. Error in the transmission. Okay. So let's improve our slides now. So if R into S transpose is 0, does that mean no error? No. What does that mean? That means R is a valid code word. Okay, here C is equals to R already I have written, so let's not write it down. And if R into S transpose is not coming to be 0, that means there is surely some error, right? If R into S transpose is coming not to be 0, that means R is not a valid code word. If R is not a valid code word, that means some error has surely occurred. So error, or you can say R is not a valid code word. Right? Anywhere else do I need to change? Yeah, that's it. Okay, fine. Now let's understand how to make a H matrix from G matrix. We will come back to this discussion with another problem. we will frame one more question would come, and this discussion will again come up. But I hope you have understood the depth of this particular discussion. Say yes or no. You have surely understood, right? One good question I have framed. Where is that question? Yeah, this is the question. But for solving this particular question, what you need to do, here G matrix is given, and I have given the received code word, and now I am asking what was the transmitted code word. So from G matrix, first you need to make H matrix, no? Right? From G first you need to make H, because here what I need to do? I need to do R into H transpose. This is the thing I need to do, right? So first I should know how to make H matrix from G matrix. So let's just say this G matrix is given, and I need to make H matrix out of it. So first thing what I will do, I will always look for identity matrix, where I can see my identity matrix. So this is my identity matrix. So what does that mean? This is your parity bits. So what is the way of writing down generator matrix here? First identity matrix and then parity. So what will be the pattern of H matrix? First thing you let me know what is the relation between G and H. The relation between G and H is G into H transpose is equals to 0. Okay. So we will not go into mathematics. I will simply tell you the method. What does the method says? Method says only one thing, that you look at the identity matrix, you look at the parity bits. Now whatever the parity bits that you see, take the transpose of that parity bit. So if I take the transpose of 0 1 0, so 0 1 0 1 1 0 1 0 1 0 1 1. So this is the transpose I will be getting. Okay. Now here there was identity matrix, so here also identity matrix would come. Now this identity matrix will be having 3 rows, that you are surely sure. You are sure about it, right? You are sure about it that here surely I can have only 3 rows. So how many columns will be there? Identity matrix is a square matrix. So how many columns will be there? Columns will also be 3 only. So basically I will make a 3 cross 3 identity matrix here. Are you able to understand or not? You might not be able to understand, but we will see one more example. Okay. After that it will be clear. A lot of times you will do this process, it will be clear to you. From G to H I am going. What I will see? First I will look at the identity matrix, then I will look at the parity bits. Now parity bits, what I would do? I would take it this side. Parity bits would be coming this side with being transpose. So here the pattern is IKP. Now H will have a pattern of PIK. But P will be transposed. So P will be transposed 0 1 0 1 1 0 1 0 1 0 1 1. Now how this identity matrix would come? Here I should not write down, here I should not write down K. Okay. Identity matrix would come. I don't know what will be the order of identity matrix. I don't care about that. What I would see that here there are 3 rows. So identity matrix will also have 3 rows and 3 columns. So actually this order came out to be n minus k. But you don't need to mug it up. Okay. Don't remember it. This order actually came out to be n minus k, or you can say this order is m. Okay. And the total order would come out to be m cross n. Although you don't need to mug up anything. Only thing you need to remember, G matrix will have gk. K cross n order. So H matrix will have m cross n order. That's it. This thing you don't need to remember. Why you don't need to remember? Because I have told you the process. Look for parity bits transposed 3 rows, so 3 column. That's it. Okay. And this is something that I have written here. But before that, let's solve another problem. So here look for your identity matrix. This is my identity matrix. And this is my parity bits. So what do you think? What is the value of m? M value is 3. What is the value of k? Value of k is 5. Because this is representing your data words. So what is the value of n? N is 8. So what kind of code it is? 8, 5. Now you know that, sir, this is identity and this is parity. So parity would go here, identity would come here. So first what I would make? First I would make parity. So what does this parity pattern tells me? That whatever that you are having here, just transpose it. So if I do the transpose of all these guys, what I will get? 1 0 1 1 0 0 0 1 1 0 1 0 1 1 0. Okay, transpose I have done. Now here 3 rows are there, so 3 columns would be there. There you go. ओके। अरे यार ये थोड़ा सा अजीब तो लग रहा है। Okay, not a very good diagram, but it is what it is. So this is your H matrix. Okay, and how this concept came? This concept actually came from G into H transpose equals to 0. But I don't want to go into the mathematics. This pattern you remember, this process you remember, and you will be able to understand. Okay, so for how you go from G to H, this is how you go from G to H. So G was having a pattern of ik into p comes here, ik goes there. Okay, this becomes n minus k, order is m cross n. If ik is here, so ik comes here, p goes here. So basically you need to interchange the positions. When I interchange the position, I would make sure that I will take the transpose. So I took the transpose. Now this order I don't need to remember. What I would see, 3 rows are there, 3 columns would be there. So I will make an identity matrix of 3. Here also I made an identity matrix of where is the identity matrix? Yeah, here is the identity matrix. So I made an identity matrix of 3 here. So did you understand how to go from G to H? We will go from H to G as well, but as of now you have understood how to go from G to H. All clear? Okay. So we have understood how to go from G to H. Now solve this question. A very good question, and surely it is coming in gate examination in future. Take your time. Take your time. Use your brain. Okay. You have to use your brain. This is MSQ. If this question is coming in the examination hall, forget about the students. Every coaching institute, every single coaching institute will be giving this answer. But what would be the answer? This would be the answer. So have some patience, use your brain and try solving it. So what I would see if I look at this question, received code word is given, G matrix is given, they are asking what could be the transmitted code word. That means if there is any issue in this code, that I need to check. Whatever the code that I am receiving, is that code correct? Is that a valid code word? First thing that I will check. So R into H transpose. First thing is that you need to find out H transpose. So G is given. So first let's find out H. How will I find out H? Sir, identity, parity. So my matter of concern would become parity. Parity checker matrix. What is the name? Parity checker matrix. So who would be your matter of concern? Parity, no? So 0, 1, 1. So sir, this will become 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0. And then what I need to do? Sir, I need to make this particular thing. Sir, H matrix I have written. Right? Now my target is doing R into H transpose. So that I will do, sir. Now first I would be requiring H transpose now. So I will do the transpose of this one. So R into H transpose. R into H transpose. This is what I am doing. 0, 1, 0, 0, 1, 1. 0, 0, 1, 1, 1. Multiply with H transpose. Multiply with H transpose. This would be a tough task to write down. Right? You need to do the H transpose. So 0, 1, 1, 1, 0, 1. 0, 1, 1, 1, 0, 1. 0, 1, 1, 1, 0, 1. 1, 1, 1, 0, 1, 0. 1, 1, 1, 0, 1, 0. 1, 0, 0, 0, 1, 0, 0, 0, 1. 1, 0, 0, 0, 1, 0, 0, 0, 1. Let's just recheck once, okay, because one bit wrong, that means whole question is gone, right? So nothing should be wrong. 0, 1, 1, 1, 0, 1, 1, 1, 1. 0, 1, 0, 1, 0, 0. Yeah. Okay. Yeah, okay, fine. Now we will do this thing. What answer I will get? 0, 1, 0, 0, 1, 0, 0. So 0 you are getting. 0, 0, 0, 0, 0, 1, 0, 1. Then 0, 1, 0, 0, 1, 1, 1. So what we are getting? 0, 1, 0. Let's check again. Last row I need to check 0 1 0 0 0 0 1 0 1 0. Yeah. So what you are getting? You are getting 0 1 0. Can you see it somewhere? Yes. 1 2 3 4 5 6, sixth row. So there is an error in the sixth row. If there is an error in the sixth row, that means sixth bit will be in error. 1 2 3 4 5 6. So sixth bit is in error. That means sir, the code word would be 0 1 0 0 1 0 1. So they will all click on this option. Okay, so this is correct. MSQ question was there, sir. Needlessly they framed 4 options just to make us confused. Sir, I clicked on option A. I will be getting 2 marks. And there you go. This is wrong. Let's just say I am sending this code word. Okay, I actually sent this code word. Oh, forget about it. This code word you have already sent. So this is the received code word. Let's just say I sent actually this code word. I tried to send 0 0 1 0 1 1. I tried to send this code word. Okay, did they say how many bits of error would be there? There could be 1 bit of error, there could be 2 bit of error, there could be 3 bit of error, right? So I tried sending this code word. Okay, and then what really happened? This was received as it is. There was an error in the second bit. There was error in the third bit. This was received as it is, and then all these were received as it is. So there were error in second and third bit. So this was my received code word. Is it similar to this one? Yes. And what I actually sent? This I actually sent. So this will be the answer. This could be the answer. You are not sure. Why is that so? Because the first task would be, can you actually send this code word? Like, is it even a valid code word? Like, is it even a valid code word or not? You will be able to send this code word. What they are asking, transmitted code word you need to find out. So is it a valid code word or not? First thing is that then only you will be able to send it, no? So you will be able to send this particular code word if it is valid. If it is valid, then any amount of bit error could be possible. They did not say that there will be only 1 bit of error. If there was only 1 bit of error, it is able to recognize it and your answer is A. But what if there is a 2 bit of error? So yes, both bits are converted and both bits are changed now, right? So received code word is the same, but this was your transmitted code word. This will be the answer if this is a valid code word. And is it a valid code word? So let's check. Can you check from the generator matrix? Each row of generator matrix represent a valid code word. So from the generator matrix only I get to know that there you go. This is a valid code word. This is your valid code word. C2 let's call it, or let's call it C3, whatever it is. So this is a valid code word. 0 0 1 0 1 1 1. So I was sending 0 0 1 0 1 1 1. There were 2 bit of error that got flipped into this R. When I calculated R into H transpose, I got the answer 0 1 0. I got the answer 0 1 0. Right? Now this answer 0 1 0, this answer 0 1 0 is telling me that you need to make a change in the 6th bit. This answer received code word 2. Okay. Sixth bit. Just a second. Yeah, sorry for the interruption. So what I was saying, that we did R into S transpose. We got 0 1 0 as the answer. This R is telling me that there is an error in the 6th bit. So whatever the R that you are getting, that is having an error in the 6th bit. So if you change that error, what is the answer you are getting? Sir, 0 1 0 0 1 0 1. So as per me, I thought that answer should be A. That is fine. That 0 1 0 0 1 0 1 will be a valid code word. There is no issue. It might happen that, sir, this was transmitted. Right? But who knows this was transmitted? 0 0 1 0 1 1 1. This could also have been transmitted. Did they talk about that how many bits of error was there? No. They did not talk about how many bits of error was there. So this could also have been transmitted. No. So did you understand the point of this question? This R was just there to confuse you. There is no meaning of this R. They actually wanted to ask which of them are a valid code word. That's it. This is the question. Because R is the received code word and channel is noisy. So the channel can flip any number of bit. Here they are flipping number 2 and number 3 bit. What if I am sending this one? First thing is that is it a valid code word? Can you actually transmit it? Can you actually transmit this one? Then you would say, sir, it is a linear code, and in linear code, all 0 code word is always a valid code word. So yes, sir, I can actually transmit it. If you can actually transmit it, then there is a noisy channel. There is a noisy channel. Now what this noisy channel would do? The noisy channel is doing, there was no error. Here in the second bit there was an error. Third bit no error, fourth bit no error. But in the fifth, sixth and seventh, all bits got flipped. So here 4 bit got flipped. So this is a noisy channel. No, how many errors are there in the noisy channel that they did not specify? So this answer is also possible, no? So this R was there just to confuse you. There is no meaning of this R. Are you able to understand this point or not? Surely in the GATE examination this kind of question is coming. Because people don't even understand what does R into H transpose represent. R into H transpose doesn't tell about like it tells about the error, but it mainly tells about the valid code word or not. So this is not a valid code word. We did the calculation, we got to know that problem is there in the 6th row. We changed the 6th row and this is the option that we are getting. That means this will surely be a valid code word. But you cannot tell this was transmitted. What was transmitted you don't even know. But I know one thing, that what was transmitted, that has to be a valid code word. Whatever that was transmitted, that has to be a valid code word. So simply through this question, what they wanted to ask? Through this question, they wanted to ask which of these options are a valid code word. This is the question that they wanted to ask. Now, sir, is this a valid code word? From this matrix, I am not able to recognize whether it is a valid code word or not. I am asking, is it a valid code word? So what about this particular scenario? This particular scenario will have 2 to the power 14, 16 code words. So basically there would be 16 answers of this question. There would be 16 answers of this question. Out of those 16, these are the 3 options. But will it be a valid code word? Who knows? But if it is a valid code word, then you know that C into H transpose would be equals to 0. But when you do C into this code word you take, okay, and then multiply with H transpose, what you will get? You will get a non-zero answer. Okay, for this particular case, you can do it. What you would do? You would take this C, you will multiply with H transpose, and you will get a non-zero answer. What does that mean? That means it is not a valid code word. And if it is not a valid code word, that means you cannot send it. Are you able to understand what I am saying? If it was a valid code word, then you could have sent it. No. From the transmitter, what would come? From the transmitter, a valid code word would come. Now what they are asking, that what could be transmitted? That means a valid code word could be transmitted. So this valid code could be transmitted, this valid code could be transmitted, this valid code could be transmitted. Is this a valid code word? If it is not a valid code word, then how it would be transmitted? So this R was there just to make you fool, so that you would click on option A only. But whatever that could be transmitted, that has 16 options. So any of these 16 options could be your answer. But here if they had specified that there is only 1 bit of error, then only answer A would be there. Because if you are transmitting 001011, that means there are 2 bits of error. If you are transmitting all 0, that means there are 4 bits of error. If they have specified that there is only 1 bit of error, then only answer would be A. But if they don't specify the number of error, then the question simply becomes find out the valid code words. So this is not a valid code word. How can I determine it? I will do C into H transpose. I get to know that it is not a valid code word. Or if I am more smart, if I am a smarter guy, what I would do? I know that what I need to generate 1110. This side should be 1110. That means my data bit should be 1110. What if I do the C1 XOR C2 XOR C3? What I would get? C1 XOR C2 XOR C3. 1 XOR with 0 XOR with 0, 1. 0 XOR with 1, 1. 1 and then 0. 1 1 XOR, that would be 0. 1 1 XOR, that would be 0. And 1 1 1 XOR, that would be. So this will be a valid code word. But what you are actually getting? This you are actually getting. That means this will not be a valid code word. So this C into H transpose calculation, this also I will not have to do. That means when my data bit was 1110, my parity bits were 001. How did I get to know? From this generator matrix. But what this is saying, when your data bit is 1110, your parity bit should be 010. That means it is wrong. So this code word can never be transmitted. Out of these 16 code words, this code word will never be there. I hope you are able to enjoy it. I hope you are able to appreciate it. If you are able to appreciate it, share it with your friends. Okay, like you can take any gate notes in the whole industry, you take any gate notes, this topic will not be taught in this manner. They will say R into S transpose, there is no error. This is known as syndrome decoding. So they will simply say that you will find out syndrome, take the 6th row, then change the bit. Okay, but I'm pretty sure they have started asking questions from coding, from source coding, not from source coding. Till this point, they never asked question from source coding, but from channel coding, they have started asking the problems. From information theory part as well, they have started asking the problem, and now the level will be rising up. Okay, till this point, they used to ask simple problems only, but the level will be rising up. And if the level rises up, then this kind of questions will be coming. Okay, and we have studied whole digital communication system in this manner only. And forget about digital communication system, we have studied all 10 subjects in this manner, right? There is always a hidden beauty in all the subjects, and that hidden beauty you need to appreciate and you need to study as well, right? So I hope you have understood the meaning of everything that we have seen now. Okay, so from G matrix we have understood how to make H matrix. This question we need to solve. So blindly I would have solved this question. I don't even need to do this particular calculation. What I would see, look, okay sir, they have given the received code word. What they are asking transmitted code word. So from the received code word, how can I say what was transmitted? I cannot say that. And neither they are specifying that how many bits of error was there. That means any number of bits error could be there. So my task would be only to determine the valid code word. So 16 valid code word could be there. Out of these 16 valid code word, which of them is a valid code word? That I need to determine. This is my target. So what I did, I kept on checking option A, B, C, D. Now will I do C into S transpose, C into S transpose every time? No. What I would do, generator matrix would represent a valid code word for sure. That means 0100, 0100, 101, 0100, 101. Is it a valid code word? Yes, sir. I would click on option A. Then 0010, is it a valid code word? I would click on option B. Then 0000, this will surely be a valid code word. Now 1110, I am not able to determine here, but I know that if I XOR all these 3 rows, then I will get this particular thing. And when I XORed it, I got to know that 1110 will have a parity bit of 001, but they are saying 010, so I will cut on this option. So if I have my concept clear, then within 30 seconds I will be able to get the answer of this particular question. Nothing calculation, no calculation. Okay, so from the received code word, the transmitted code word could be anything. In a lot of notes, I would find that they have written down this is the received code word, find out the transmitted code word, and they have given this answer in all the notes, of gate industry. Received code word, find out the transmitted code word, they have given this answer, which is absolutely wrong, right? It could be anything. They could have asked data word as well. What would be the data word? They could have asked, with respect to this received code word, what would be your data word? So ABC are the answer. Out of these are the data words, right? These are the data words. These are the data words, and these are the parity bits. Okay. How do you know, sir, these are the data words? Because where is the identity matrix? First 4 bits are identity matrix. First 4 bits are identity matrix. That means first 4 bits are your data word. So this is the data word. This is the data word. This is the data word. All good. Let's go to our next point. Okay, this question is solved. Why this space is there then? Let's go to our next point. From H matrix, we need to go to G matrix. You can do it on your own. What do you think? How will you do it? From G to H, you know, from H to G. Same thing is there. First, you find out the identity matrix. Then you find out. These are not parity bits, right? These are not parity bits. I will not say this is a parity bit. This is actually parity transpose, right? Okay. So what will be your G? So this parity would go here. It will be transpose. Like transpose, again transpose. What that would be? Parity only, no? So as of now, I will not care about my identity matrix. What I would care about, that sir, these guys will be transposed. So 0 0 0 1 1 0. So this would become a row. This would be the scenario. 1 1 0 1 0 0 1 1. So this would be the scenario. Now there are 4 rows, so there would be 4 columns. If there are 4 rows, then there would be 4 columns. अरे रे भाई. Okay, with the cool mindset, if you do, this would be very easy. This would not be tough. Okay, just you need to have a cool mindset. Okay, so don't rush in the problems of coding. Okay, H was given, G I need to make. I looked for this guy and then I looked for the parity, interchanged it, like basically took the transpose, and from here I was able to make my generator matrix. So now what do I know? I4, and these are 3 parity bits. So number of parity bits are 3, K value is 4, so N value is 7. Okay, and this is your 3 cross 7. From here as well I could say that M is 3, N is 7. So what will be the value of K? If they want to ask an easy question, then these questions they would ask. They would make the matrix, they would ask what is the value of M and K. These values they can ask, right? Or they can ask one more question. They would give this H matrix, they would ask what is D minimum. They would give this H matrix. From H matrix, as of now, do you know how to find out D minimum? No. But from G matrix, you know how to find out D minimum. What that would be? So that would be equals to W minimum. So here, what do you see W minimum? 1, 2. Here was 3, here 3. Like what is the weight of this one? The weight of this one is 3, weight of this one is 3, weight of this one is 3. Here the weight is 2. Here the weight is 2. So answer would be 2. So as of now, H matrix was given. I made the G matrix and then I said answer is 2. But I will tell you another method. Here only I can tell that method. What does that method say? You see the columns here. You see the column of H matrix. What is the minimum number of column? Listen to me very carefully. What is the minimum number of column such that you do the XOR operation and answer is 0? If I take this column and I take this column, if I do the XOR operation of these two guys, what will be the answer? 0, 0, 0. You need to determine the minimum number of columns such that the XOR operation would throw answer 0. So the minimum number of columns are 2. Right? So basically what I need to find out, the first thing that I will find out is that am I getting identical columns in H matrix? This is the method for H matrix. For G matrix we have already seen, right? 4 rows are there, see the minimum weight, that would be the answer. D minimum would be 2. But for H matrix, what you would do? For H matrix, what you would do? First, you will try to find out if there are any 2 identical columns. Because if there are any 2 identical columns, then what will happen? So 0 XOR with 0, 1 XOR with 1, 0 XOR with 0. So what will be the answer? 0 only. So if identical columns are there, that means only 2 columns can make sure that XOR operation can throw 0. This is just an observation, nothing else. The best way could be, sir, if you don't want to, sir, I don't want to remember anything, I don't want to put stress on my brain, what I would do in the examination, sir, if H matrix is given, I will make the G matrix, put the answer. That's it. You can do it. Okay. From H, sir, I will simply make the G matrix. My job would be done, sir. I don't want to think about anything else. So from H to G you make, your answer would be done. Or if you want to solve in a quicker manner, then you need to determine the number of columns such that their XOR operation would be 0. So 0, 1, 0, 0, 1, 0. That means first task would be that I would determine if there are 2 columns identical. If there are 2 columns identical, my job is done, D minimum would be equal to 2. We will see more examples, have some patience. Okay. So for the given H matrix, you need to find out D minimum. So sir, if I don't want to think anything, blindly I need to solve, what I would do? Sir, I would make G matrix. How would I make G matrix? Sir, first I need to look for, this is my identity and these are my parity. So parity are written here. So identity would be, basically they need to be interchanged, no? This is your parity transpose, right? So they will come here. First thing they will be transposed and then they will interchange the position as well. So they will be transposed 1, 0, 1, 0, 0, 1, right? And then sir, this is my identity matrix. Now I know that there will be 2 rows and 2 columns. So 1, 0, 0, 1. So this will be the scenario, sir. This is my generator matrix. Sir, I have made the generator matrix. Now, sir, I can see that my D minimum is equals to 2. Why D minimum is 2? Because here the weight is 2. So answer is 2. But sir, without even doing so, what I could have seen? I could have seen that, sir, in this H matrix, two columns will be identical. What all are those two columns? Sir, this column and this column are identical. If your observation is good, sir, 0, 0, 1, 0, 0, 1, they are identical. That means d minimum would be equal to 2. So two columns are identical. That means d minimum was 2. What about this one, sir? Sir, if I don't want to use my brain, what I would do? I would make the G matrix. So, sir, what I saw here, this was identity and this was your P transpose. So, sir, this will come and it will be transposed 0, 1, 0, 0, 0, 1. And sir, here the order would be 2. अरे यार यहाँ पे भी यही सेम केस हो गया क्या? Here also two rows are identical. Okay, this and this are identical. But I wanted to take a case where d minimum was actually 3. Like d minimum equals to 2, that is a very simple case, no? We will take one example where d minimum is equals to 3 through the H matrix. Okay, here also d minimum equals to 2 because here you can see that weight is 2, and along with that these are identical matrix as well. So you would say d minimum is equals to 2. But I wanted to take a case of 3 as well, which I haven't taken here, right? So I need to take a case where d minimum is actually equals to 3. So what I would do? We will take the example later on. As of now, you can see only in all the cases answer is coming out to be d minimum equals to 2. But what will happen in the case of 3? So there you will have to determine, there apparently no two columns will be same, right? The columns could be in this manner 0, 1, 0, 0, 0, 1, 1, or can we see those columns here somewhere? Somewhere here also d minimum is 2 only. So just let me see some example. In that example we can solve it. Here what is the d minimum? 3, 2. Here also d minimum is 2 only. Here also d minimum is 2. Whatever the example that I have taken, everywhere d minimum is 2 only. What about this one? 0, 1, 0, 0, 1, 0. Here also identical. 0, 1, 0, 0, 1, 0. This is also identical. Yeah, this example looks good. So let's take the example of this G matrix. Okay, let's take this G matrix. This G matrix is given. This G matrix is not given actually. H matrix would be given. Okay, H matrix would be given, and you need to tell this G matrix is not given in the question. What is given in the question? H matrix is given. So question says H matrix. So H matrix was given, that was actually equals to. So can you make from G to H? Yes. What you will look for? Oh, this will be very difficult, right? Basically, here the problem would be that this is not here the shuffled identical matrix is there, no? Identical matrix and your parity bits are shuffled. So that would be a very tough case. For that, we don't understand how to make the parity checker matrix. Okay, so I will make a easy case. Easy case would be that these are not shuffled. So better let's take the case of not being shuffled, so that we can find out somewhere here only. This case we can take, right? They are not shuffled. Yeah, this case we can take. This G matrix we can take. Okay, so this G matrix we can take. So what will be your H matrix? This will be given in the problem. Okay, this H matrix is given in the question itself. They have made the H matrix as this will go here. So this would become 1, 0, 1. In that manner, here there will be 3 cross 3. This will become 1, 0, 1, 0, 1, 1, 1, 1, 1, and 1, 1, 0. So this is the scenario. Okay. What they are asking? They are directly asking you d minimum. So what some guy would be doing? Or they are asking maximum number of They did not ask D minimum. What they asked? Maximum number of detectable errors. Maximum number of detectable and correctable errors. Okay, this is the question that they are asking. So someone who don't want to use his brain, what he will do? He will make the generator matrix. What he will say? Sir, 3 guys and 4 guys. So they will be transposed. Yeah. So they will be transposed here. So they have transposed 101, 011. I will take the transpose of these guys here, and then identity matrix would come here. So sir, 101, 011, 111, 110, and this identity matrix has come here. So this is my G matrix, sir. Here what do I see? Weight is 3 here. Here also the weight is 3. Here also the weight is 4, and here the weight is 4. So sir, D minimum would be equals to 3. If I know the D minimum, then I can tell maximum number of detectable and correctable error. What would be the detectable error? So that would be TD plus 1. So maximum number of detectable error would be 2. And sir, if D minimum is equals to 3, then you know that 2T plus 1, that means sir, correctable error would be equals to 1. So detectable are 2, correctable are 1. This is how one student would solve it. Now other student who want to use his brain, what first thing what he would see? Sir, I directly want to solve from H matrix. My target is to find out D minimum. So sir, what I will do? First I will check if there are any two columns which are identical. So I checked this one. Like basically I will see through my eyes if there are any two columns which are identical. I cannot see any identical columns. Now next what I would do? Randomly what I need to check. Now what is my target? I need to check 3 columns. I need to check 3 columns such that their XOR operation is giving you 0. This is my target now. So what I would do? First I would take any 2 columns and I will randomly do their XOR operation, and then I will check if I am able to get column 3 or not. What I mean to say, let's just say if you do the XOR of column 1 and column 2, column 1 and column 2, what you will do? 1 XOR 0, 1, 0 XOR 1, 1, and 0 XOR 0, 0. Now I will check, am I getting 1, 1, 0 anywhere? Yes. What does that mean? That means column 1, column 2, this would be 3, 4, 5, 6, 7, and column 7. Column 1, column 2, and column 7. If you do the XOR operation of these 3 guys, the answer would be 0 only. Why is that so? Because 1 and 2 is giving you 1, 1, 0. Now 1, 1, 0 will be XORed with 1, 1, 0, answer will be 0 only. So here you need to use the brain. Here surely your brain have been used. Right? If you don't want to make generator matrix, then this is how you need to think. If you make the generator matrix, it becomes very straightforward. You just need to see the number of ones. Your job is done. But if you don't want to make the generator matrix, you want to solve it from the parity matrix only, then what you would do? Then you would see the number of columns, do the XOR operation, minimum number of columns such that their XOR operation throws 0. So those minimum number of columns are 3. So these are your 3 columns. That means D minimum would be equals to 3. And how would I check? Sir, first I will be checking if 2 columns are identical or not. Most probably in your examination, if they have given H matrix, 99% chances are there that sir, you will be able to get 2 identical columns. I am telling you this thing. Okay. If this question is coming in the examination till this date, it never came. When it comes, you will notice this thing. That 101, not 101%, 99% chances are there that 2 columns will be identical. So directly you would be able to solve D minimum equals to 2. If it is not that case, then what you would do? Randomly take any 2 columns, or just try thinking that if I do the XOR operation of these 2 guys, I am getting 1, 1, 0. Or if I had taken these 2 guys, then 0 XOR with 0, 0, 1, 1. Am I able to get 0, 1, 1? Yes. Here also it is happening, no? If you take these 2 guys, if you do the XOR operation of these 2 guys, what you will get? 0, 1, 1. Are you able to see 0, 1, 1 here? Yes. That means column 2, column 3 and column 4. If you do the XOR operation of these 3 columns, then also you are getting 0. That means minimum number of columns such that your XOR operation is throwing 0. That will be your D minimum. That is equals to 3. So it is also not that tough. Randomly take any 2 columns. Randomly I have taken these 2 columns. Am I getting what will be the XOR of these two guys? 1 1 0. Am I getting 1 1 0 anywhere? Yes. So first task would be that you see if two columns are identical or not. If they are not identical, then you would move to the next thing. That randomly you take two columns, do their XOR operation. It should match with the third column. Is it matching? Yes, it is matching. The answer will be D minimum equals to 3. As a student, I would not prefer this one. Okay. As a student, I will solve from the parity matrix only, because method I have told. So now your most of the things are completed. Okay, most of the things where brain is used, that is completed, and I told you that we will write down some short notes. Whatever that we have learned, everything we are writing down here. Because here you might feel like that, sir, there are a lot of concepts, but a lot of concepts are there, but easy concepts are there. Like the good thing started from here. From where? From this generator matrix. Just as this generator matrix came into action, you kind of felt that now we are learning communication, right? First we studied about the generator matrix, then we solved a particular problem, that what it is doing. Then one good conclusion that we saw here, that each row of generator matrix represent a valid code word, and if generator matrix is given and they are asking you D minimum, then first thing you know that D minimum is equals to weight minimum. Now for weight minimum, you don't have to check the weight of all the code words. Whatever the code word that you get from the generator matrix, just check their weight, that would be your final answer. So whatever the weight that I am getting from here, whichever the minimum weight is there, that would be my final answer. So these two good conclusion that we have seen, right? Then we saw the pattern. What is the pattern? That first what I need to see, how many number of bits we are using in the data word. 4 bits we are using. So 4 cross 4 identity matrix would be there. With respect to that, there will be parity matrix, or interchange could also be there. Interchange could also be there, right? Then we saw about the generation of valid code word. Now we needed to talk about the detection of valid code word. So C has become R. Now C into H transpose, we have developed a matrix such that C into H transpose would be equal to 0. That matrix is known as parity checker matrix. Then C and H are orthogonal to each other. G and H are also orthogonal to each other. So if received code is not equal to C, that means there has some error occurred. Okay. So R could be written as C plus C, and this thing we saw. Everything we have seen here. Then we saw some example. If C is a valid code word or not. So then you got to know that this is a valid code word. So if some error is happening, then you saw that whatever the answer that we are getting, that would match with the particular row. And if you make the change in that particular bit, then you would receive a valid code word. But it doesn't tell R into H transpose. Very important conclusion that we saw here, that R into H transpose equals to 0. It doesn't tell that there is no error. Error could also be there. Here in this case, error was there, but it was not able to detect that particular error, right? Error was there, it was not able to detect that particular error. Can you let me know why it was not able to detect that particular error? What would be the D minimum for this case? H transpose is made, no? H transpose is made. In H, what we used to check? We used to check the column. So in H transpose, what we will check? We will check the row. So if I check the row, what do I see? These two rows are same. What does that mean? That means D minimum is equal to 2. And if D minimum is equal to 2, that means the maximum number of detectable bits should be 1. So this particular matrix or this particular code would be able to detect only 1 bit of error. But here what is happening? 2 bit of error is happening. That's why it is not able to detect that error. Everything are you able to relate now? So 2 bit of error you are not able to detect here. Only 1 bit of error you could have detected. So if 2 bit of error is happening, still you are getting a valid code word. So R into H transpose never ever tells that there is no error. R into H transpose only talks about validity of the code word or not. So if it is coming out to be 0, that means you are having a valid code word. If it is not coming out to be 0, that means you are not having a valid code word. That's it. Okay. And then we saw how to go from H matrix to G matrix to H matrix, or H matrix to G matrix. Right? We saw the process. If you repeat this process 1 or 2 times in your rough notebook, then you will be able to do it. Then we saw this particular question. There they were asking that what could be the transmitted code word. So looking at R into H transpose, you can never tell what was that transmitted code word, because they did not specify the number of bit error. So the transmitted code word could be any valid code word. So any valid code word could be the transmitted code word. And how do we check valid code word? From the generator matrix, I could have checked it. Then we saw how to go from H to G matrix. This is how we can go. Then we saw the concept of D minimum. this should come later on, right? Yeah, this should come a bit later on here. This slide should come later on. Yeah. So this concept we have seen, concept of D minimum from the H matrix itself. So number of columns which would turn the summation into 0. The number of minimum columns which would turn the summation into 0, that would be your D minimum. Okay. Otherwise you can solve from H2 you go to G and you can get your answer. Okay. Now summary we are writing down. So first thing is that data word length is K, number of parity bits are M, then code word length is N equals to K plus M. Then we study about the distance between code words, then we study about the weight of the code word, then we study about the minimum distance, then we study about the minimum weight. Okay. Now if TD is the detectable bits, T is the correctable bits and D is the minimum Hamming distance, then D minimum is equal to detectable bits TD plus 1 and D minimum is equal to 2T plus 1, right? Then for linear code, all 0 code word will be a valid code word. Any code word could be like XOR operation of any 2 code words would be a valid code word as well, and D minimum is equal to W minimum. So this was the property of your linear code word. There is something called singleton bound. Okay, this is a new thing that I have written here. One question has been asked. So in any kind of code, D minimum would always be less than or equal to N minus K plus 1. If you don't want to remember N minus K, then you can remember M plus 1. So D minimum would be less than or equal to M plus 1. Okay. In any code word, not code word, in any code, in any kind of code, like it could be linear code or it could be anything. So in any kind of code, D minimum would be less than or equal to M plus 1. Okay, or N minus K plus 1. This is known as singleton bound. Sir, how this came? Simply remember it. Okay, just simply remember it. You don't need to, every time you don't need to think that, sir, how this formula came, that came. Just simply remember it. D minimum should be less than or equal to N plus K plus 1, N minus K plus 1. Okay. Then we studied about generator matrix. Two important properties were there. Each row of generator matrix is a valid code word. W minimum of a row is equal to D minimum of the code. Okay. Only you need to look at the rows. And this is how generator matrix is written. It could be written in other ways as well, right? Then we studied about parity matrix. Now parity matrix is designed in a manner that C into S transpose is equal to 0 and G into S transpose is equal to 0. Now sir, what this you have written? Now I say that A and B are orthogonal to each other. That means you will say that, sir, matrix A multiply with B transpose is equal to 0. Can you also say the same thing, that B into A transpose is equal to 0? So similar thing I have written here. C into H transpose is equal to 0 or H into C transpose is equal to 0. G into H transpose is equal to 0 or H into G transpose is equal to 0. Right? Matrix, nothing else. I know that I have designed the parity checker matrix in a manner that C into H transpose equals to 0. Then H into G transpose equals to 0. H into C transpose equals to 0 and G into H transpose equals to 0. Right? Matrix only, nothing else. And we will solve a problem of this one. It will be clear to you. D minimum should be less than or equal to N plus K, N minus K plus 1. We will solve a numerical problem. It will be clear to you. Now this one. If R is the received code word, if R into S transpose is not equal to 0, then R is not a valid code word. And D minimum of a code from parity matrix, how would you determine the D minimum of a code? So minimum number of rows with sum equals to 0, we are talking about parity matrix. So you need to find out the minimum number of rows where sum is equal to 0. So this is the conclusion of everything that we have studied till now, right? So this slide you will revise again and again. Some more concepts are there that we will see. So let's solve this question first. What this is saying: consider a binary channel in code which code word has a fixed length of 5. The Hamming distance between any pair of the code is at least 2. So this is the minimum value of a minimum Hamming distance. What I mean to say is that this is the minimum value of a minimum Hamming distance. What they are saying, Hamming distance between any pair of distinct code word is at least 2. So D minimum only you can write down. And doesn't make any sense. D minimum equals to 2. Find out the maximum number of code word. So what will be the maximum number of code word? Maximum number of code word. You know that, sir, it will be 2 to the power k. Right? Now D minimum n. From there you need to find out the value of k. Do you remember some relation? Should be less than or equals to n minus k plus 1. Right? So what is the value of D minimum? 2 should be less than or equals to n minus k plus 1. So k should be greater than or equals to, or k should be less than or equals to, that's what I was thinking. So what you are getting, k is less than or equals to 4. Right? So what is the value of k minimum? K minimum is equals to 4, and you need to find out, k maximum, sorry guys, what is the value of k maximum? Right? Maximum number of code word they are asking. So what is the value of k maximum? K maximum is equals to 4. That means maximum number of code word would be equals to 2 into k to the power maximum. So that would be 2 into 4, answer would be 16. So one time the question has been asked. Who knows, it can be asked again. So if n is given, k is given, you know one relation. D minimum should be less than or equals to n minus k plus 1. Okay, this is known as singleton bound, which you should be remembering. Now there is a concept of probability and concept of erasure. You don't need to study this concept, you already know it. Now what is this erasure, that we will see, but first we will study probability of error. Okay, so directly with respect to the question you will be able to solve. Try solving this problem on your own. Try solving this problem on your own. Okay, then try solving this problem on your own as well. You don't know Hamming code, but without even understanding the Hamming code, this question can be solved. Okay, so try solving this one and try solving this one on your own. Use your brain. I am pretty sure you will be able to solve it. And after that we will study the concept of erasure. What is the meaning of erasure? What is the meaning of error? Right? Very simple thing. Let me take some break and then I will come back. We will start studying this particular topic. Okay, yeah. Or should we make a different video for this? I can make a different video. Okay, separate video I will make, because this video has been of 3 hours I guess. So one more video I will make. Okay, yeah. Hi everyone. So now we will see probability of error, and then we will see concept of erasure. So let's solve this question. Probability of error directly we can study with respect to the problems as well. So what this question is saying, you need to consider a binary symmetric channel with the probability of error being p. Now if we are transmitting bit 1, then we are transmitting a sequence of 3 ones. Let's just say what I want to transmit 1. But instead of transmitting 1, what I would transmit? I would transmit 1, 1, 1. If I want to transmit 0, then instead of transmitting 0, I would transmit 0, 0, 0. This is what I am saying. This is what this question is saying. Now what they are saying, that if you are transmitting 1, the receiver will interpret the received sequence to represent 1 if at least 2 bits are 1. What does that mean? That means this was transmitted. If received is 1, 1, 1, then he will be able to detect that it is 1 only. If received is 1, this was your transmitted. This is received. If received is 1, 1, 0. So what is the major number here? Major number is 1 only. 1 is coming 2 times and 0 is coming 1 time. Then also it will be able to say that it is received as 1 only. But if received is 1, 0, 0, then he will say 0 is received. And if received is 0, 0, 0, then he will say 0 is received. So this is the scenario. Is that understandable to you? Right? So what is the probability that the transmitted bit will be in error? That means this is the bit that you are actually transmitting. 1 you are actually transmitting. So this bit will be an error, will depend on these guys, right? So what will be the scenario? Transmitted bit will be in error. How it will depend? It will be in error if there is 2 bit of error, or if there is 3 bit of error. This particular thing we have already seen in the previous video when we were studying information theory. In information theory, we have understood the meaning of p x equals to 2 plus p x equals to 3. We have already seen it. That means out of these 3 bits, if 2 bits are in error, then there is an issue. Out of these 3 bits, if 3 bits are in error, then there is an issue. So out of these 3 bits, 2 bits will be in error. So probability of success here is P, because what is P? P is represented by probability of error is being P. So probability of success here is 2 and probability of not getting success is 1. Like basically chances of getting success here is 2 and chances of not getting success is 1. Or what you can see that here there is an error, here there is an error, here there is no error. So P into 1 minus P. And now you know that this 0 0 can be changing the places. This 0 0 can be in the initial, the 1 0 could be here, other 0 could be here. So there are total 3 chances. So 3C2 will be 3 only. P square into 1 minus P. Then out of these 3 you need to pick 3 only, multiply with P cube. Why P cube? Because this bit will be an error, this bit will be an error, and this bit will be an error. So probability of receiving this bit would be P, P, B. So it would be P cube. So what answer you are getting? 3C2 is actually 3 only. So 3P square into 1 minus P. 3C3 is 1, P cube. So P cube, 3P square into 1 minus P. That's it. Very, very straightforward question. Right? 1 we are transmitting. Actually we wanted to transmit 1, but we actually transmitting 1 1 1. Problem will be if you are receiving 1 0 0 0 0 0. Then there will be problem. Right? So if these two guys are in the problem, that means 2 bits could be in error or all 3 bits are in error. So out of these 3, you need to choose 2. Right? P square into 1 minus P. Out of these 3, you need to choose 3 P cube. Okay. What about this one? You don't know Hamming code, but this question is not depending on Hamming code. Just study it once. What this question is saying? Communication, consider a communication over a memoryless binary symmetric channel using a 7,4 Hamming code. Each transmitted bit is received correctly with the probability of 1 minus epsilon. Epsilon value is introduced here. Epsilon value is 0.1. So probability of receiving the corrected bit is 0.9 and probability of receiving the bit in error, that is 0.1. Okay. Probability of receiving the bit in error, that is 0.1 and probability of receiving the corrected bit is 0.9. Okay. For each code word transmission, the receiver performs minimum Hamming distance decoding. What do you understand by this line? The receiver performs minimum Hamming distance decoding. Do you remember that how do we decode our signal? Basically, if I am transmitting 0 0 0 and other thing I am transmitting is 1 1 1. Now let's just say at the receiver I am getting 0 0 1. Then what the receiver will say? 0 0 1 is near to 0 0 0, then he will decode it as 0 0 0 only. If it is 0 1 1, then the receiver will say that it is nearer to 1 1 1, then he will decode it to 1 1 1. That means it is performing minimum Hamming distance decoding. That means here the distance was 1 and here also the distance was 1. So basically here the distance was 2. So the distance where it is minimum, that coding it will perform. So 0 1 1 is nearer to 1 1 1. 0 1 1 is nearer to 1 1 1. That's why this 0 1 1 will be decoded as 1 1 1. So this thing we have already seen. Although this is not useful for solving this problem. Okay, it is not useful for solving this problem, and correctly decodes the message bits if and only if the channel introduce at most 1 bit of error. What they are saying? That they will be able to correct 1 bit of error only. Maximum number of bits that could be corrected, that is 1. Correctly decodes means correctly decode. Correctly decode means you have modified the error. I was transmitting 0 0 0. I actually received 0 0 1. I got to know there is an error, and then I said that instead of transmitting 0 0 1, you are actually transmitting 0 0 0. So I have detected the error here. Along with that, I have corrected as well. So decoding perfectly means error has been corrected. Okay, and this is done only for 1 bit. Like you will be able to correct if there is only 1 bit of error. Epsilon value is 0.1. Then the probability that the transmitted code word is decoded correctly. This is something that they are asking. So what you are actually transmitting? 7,4 code word is there. So you are transmitting a code word of length 7. You are transmitting a code word of length 7. Right? Now in this code word, if there is 1 bit of error, then there is no issue. But if there is more than 1 bit of error, then there is an issue. If 0 bits are in error, then perfectly your receiver will be able to receive the bit and he will be able to say that there is no error. Basically, he will be able to decode it perfectly. Or if there is 1 bit of error, because they have said that t equals to 1, that means only 1 bit of error he will be able to take, or there is 1 bit of error, then there is no issue. If there is 2 bit of error, if let's just say C1, C2 both are in the error, then some problem will happen. Like here there was 2 bit of error, no? In this particular scenario, 0, 0, 0 were converted to 0, 1, 1. So there was a 2 bit of error, and this 2 bit of error was not recognizable by the receiver. He decoded it to 1, 1, 1. That means it was not perfect decode. It was not wrong decoding. It was your actually wrong decoding. It was wrong decoding. But this is correct decoding. Correct decoding. So what they are asking? They are asking the probability that transmitted code word is decoded correctly. That means in this case only he will be able to decode it correctly, no? Are you able to understand this point? If the error in the bit is either 0 bit error is there or 1 bit error is there, then only your transmitted code word would be decoded correctly. So this is something that they are asking. Out of these 7 bits, 0 bit should be in error, and all 7 bits should not be in error. So what is the probability that all 7 bits are not in error? So 0.9 to the power 7, and out of these 7 bits, 1 bit should be in error. So 1 bit should be in error, and all the 6 bits should not be in error. Again, let me repeat what I am saying. Very simple thing. Okay, probability of receiving corrected, probability of correct decoding. So that would be if only 1 bit is in error or 0 bits are in error. If no bit is in error or only 1 bit is in error, because what they are saying, if and only if the channel introduced at most 1 bit of error. At most 1 bit of error means 0 bit of error could be there or 1 bit of error could be there. So probability of x being 0 plus probability of x being 1. That means out of these 7 bits, 0 bit could be in error, or out of these 7 bits, 1 bit could be in error. So no bit is in error, that means all bits are corrected. And here only 1 bit is in error, that means 6 bits are corrected. 0.9 I should write here. 6 bits are corrected. Right? So when you solve it, as far as I remember, answer is coming out to be 0.85. That's it. Okay? Very simple thing, very straightforward. If these kind of questions are coming, then they are aptitude only, or you can call it mathematics. These are aptitude of mathematics. There is no communication system involved here. Just bit transmission is there, bit receive you are getting, then how it is decoding. So this question is purely your aptitude, right? I hope you are able to understand this problem. Let's understand the concept of erasure. So in the examination, this word could be mentioned, erasure. What is the meaning of erasure? So let's understand that by an example. So I was transmitting this code word 10110010. Now this code word would be going to a modulator, or you can call it a line coder, right? Now what this modulator would be doing? Sir, 1 is represented by +5 and 0 is represented by 0 volt. This is what this modulator is doing. Okay. Now we have designed the system in a manner that we are having a noise margin of 1 volt. What is the meaning of noise margin of 1 volt? That means even if you are receiving the signal between 4 volt to 5 volt, it will decode it to 5 volt only. Like margin of 1 volt you are having. Margin of 1 volt means if from 5 volt, if you are going to 4 volt as well, then also you are fine. And here also margin of 1 volt you are having. That means if you go from 0 volt to 1 volt as well, then also you are fine. It will be decoding it to 0 volt only. So you are having a margin of 1 volt. Is that understandable to you? So at the receiver, I was receiving this kind of voltages. So first I received 5 volt. That means 5 volt will be decoded to 5 volt only, and I will know that 1 was transmitted. Then I received 0 volt. I know that 0 was transmitted. Then I received 5 volt. That means 1 was transmitted. Then I received 4.5 volt. I know that I am having a margin of 1 volt. That means it is 5 volt only. 5 volt means 1 was transmitted. 0.5 means I am having a margin of 1 volt. That means actually 0 was transmitted. Then 4.5, 1 was transmitted. Then let's hold on to this one 3.5. Then what about this one 0.5? That means 0 was transmitted. What about this one 3.5? Now 3.5 is neither lying in this category nor it is lying in this category. So what receiver will say, sir, I don't know what was transmitted. So is it in error? No, this is not in error. You don't even know what was transmitted. So this is known as eraser. Okay. And which bits are in error? 1 0 1 1 0 1. This is your error. So here you have received wrong bit, right? This bit is in error. Is that understandable to you? And this is your eraser. Did you understand the meaning of eraser? Wanted to transmit this one. 1 was represented by plus 5 to plus 4. Sorry, plus 4 to plus 5 will be recorded as plus 5. Wanted to transmit 0. So 0 will be recorded as 0 to 1. Then I received these many voltage. From here I got to know that this is 1 0 1 1 0 1. This I don't even know because 3.5 is lying in no category and 0.5 is recorded as 0. So this is known as eraser and this is known as error. So did you understand the difference between error and eraser? So now what this eraser would do? How this eraser will change our equations, that I need to check. So how this eraser will change the equation? Let's just say I was having two code words C1 and C2. What was my D minimum here? 5. Between them, what is that distance? 5 bit of distance is there. 0 1 0 1 0 1 0 1 0 1. So 5 bit of distance is there. So my D minimum was 5. Now let's just say they are saying that R equals to 2 eraser has occurred. That means 2 eraser has occurred. What does that mean? That means 2 of the bits are gone. I don't know in place of 0 what was transmitted. I don't know in place of 0 what was transmitted. Or if I transmitted, or if I was transmitting 1, then I don't know what was transmitted here. So when I see the received bits, I don't know what came here. There was no issue with these one, or there could be some issue with these one. As of now, I don't care about the error. I only care about the eraser. So when I saw the received bits, I couldn't comment about these two initial bits. These two initial bits I could not comment. So initially my D minimum was 5. Now I will take the worst case. What will be the worst case? I will take the worst case that sir, both of these bits are same. So what will be my D minimum? Whenever you talk about D minimum, you are going to take the worst case, no? So whatever the previous D minimum you are having, D minimum after eraser, okay? D minimum after eraser. Whatever the previous D minimum you are having, minus the eraser. So eraser is equals to 2 here. That means now your D minimum has become D minimum after the eraser. This has actually become 3 only, because I will take the worst case. No, I will take in place of a question mark sign, either I will take 0 0 0 0 or I will take 1 1 1 1 or I will take 1 0 1 0. I will take the worst case that sir, I don't know what was received here, but I will take the worst case that sir, whatever that was received here, both were same. So your D minimum has reduced now, right? So now the new D minimum has become D minimum minus R. So only thing you need to remember is if eraser is mentioned, your D minimum would change. That's it. If eraser is mentioned, your D minimum would change. Only thing you need to remember is this much. From the whole discussion of eraser, if eraser is mentioned, then your D minimum would become D minimum minus R. Can you remember this much of thing? Yes, sir. So if D minimum has changed, then will these equations change? Yes, sir. D minimum minus R, let's put the equal sign only. D minimum minus R would be equals to TD plus 1 and 2T plus 1. These equations will also change. Okay. Now try solving this question. This question will be like a conclusion of everything and important. These kind of questions are coming very soon in the examination. Now 15,11 linear block code with the parity matrix have been given. Now someone would say that sir, how many errors they are asking, how many errors could be detected? That means sir, basically they are asking D minimum value. So sir, now what I will do, I will make the G matrix from here. Do you really think that making G matrix is easy? No. Why? Can you find out where is the identity matrix? And even if you are able to find out where is the identity matrix, how larger would be your G matrix? On one page it would look very large. And second thing is you are not even able to find out where is your identity matrix, because here identity matrix and parity bits are shuffled. 1 0 0 0 0 1 0 0, right? And then 0 0 1 0 and then 0 0 0 1. So these are your identity matrix. Here identity matrix and parity bits and parity matrix are actually shuffled, right? So if they are shuffled, then how would you write down G matrix? That I did not even teach you, because that is a very complex concept. So that I did not even teach you. So from here, finding G matrix is gone. Now what is our method left? The method left is try finding out if there are any two rows identical. So can you find any two rows identical? So sharp eyes has to be there. So if I look by my sharp eyes, I don't think I can find any of the two rows identical. Or what you can do, if you cannot see by the sharp eyes, then you can start writing 1 0 0 0, then 0 1 0 0, then 1 1 0 0. So in that manner you would be able to analyze. So anyway you need to analyze that if there are only two rows identical, that means D minimum cannot be 2. It would be greater than 2 for sure. So what next I told you? Take any two random, take any two random columns, do the XOR operation. What you are getting? 1 1 0 0. Is it matching to any other column? 1 1 0 0. 1 1 0 0 is not anywhere. Oh, it is matching with this one only. Okay, take any two and do 1 1 0 0. So you can see that XOR of these three guys, XOR of these three guys will result in 0 only, right? XOR of these three guys would result in 0. What does that mean? That means D minimum is equals to 3. So minimum number of rows whose XOR operation is resulting in 0, that would be 3. Okay, so you can say that, sir, column 1 XOR with column 2 XOR with column 3 is resulting in 0. That means my D minimum is equals to 3. If D minimum is 3, then how many errors are detected? So TD would be equals to 2. Next, how many errors could be corrected? So T would be equals to 1. And now next what they are asking, how many errors it can detect if the presence of one eraser has occurred. One eraser has occurred. That means what will be your new D minimum? That would be 2, right? One eraser has occurred. So new D minimum would be older D minimum minus 1. And how many errors it will be able to detect? That would be TD plus 1. So answer would be TD new, I will write down. TDR I am writing down. After that, eraser. So TDR, that is coming out to be 1. So previously it was able to detect 2 bit of error, but now it is able to detect only 1 bit of error only. Okay, so these are the 3 answers. So I told you whatever the method that I am teaching, every method is helpful, because I know that a lot of students would have given up on this H matrix method. They would say that, sir, if H matrix is coming, then I will make G matrix, and most probably H matrix would be smaller only. You would be able to make the G matrix. But what if examiner wanted to set a very good question? Then he would make the bigger H matrix. Along with that, he will shuffle the identity matrix and your parity matrix. Actually, it is parity transform matrix here, not parity matrix, but they are shuffled here now. Okay. So which method is useful here? The method says that try getting two columns, do the XOR operation and check it with the third column. Are you getting that third column or not? So if I am getting the third column, that means yes, D minimum is equals to 3. It will not be that tough to verify, right? Because any two random rows you take, do the XOR operation, it would surely match with the third column. If it is not matching, then any 3 you take, then match with the fourth column. It will surely match. Then you can write down your D minimum. All good? All fine? Okay. Now we will get started with Hamming code. But before starting Hamming code, I will do a discussion of 1 or 2 minutes. Okay. So now this discussion would go around like roughly around 20 to 30 minutes, hardly 30 minutes. Now in these 30 minutes, sir, your ideology was whenever you teach in a manner that everything should be understandable, everything has a proper reasoning. Sir, you should learn by concept. All these things you used to say. But all these things will be killed when we are studying Hamming codes. Here you will, a lot of time I would say, I will not tell you the answer of why. Okay. A lot of time I will say, remember it. hardly 3 to 4 things would be there, but I will ask you to remember it. I'm not going to give the core concept behind it, because if I give the core concept behind it, it would take more than 2 to 3 hours, and it is not worth to spend more than 2 to 3 hours on this particular topic, because till this date only, like, a lot of questions have been asked based on Hamming code, but all the questions can be solved with our basic concept, right? We have seen a lot of questions that has the word Hamming code. Here also the word was Hamming code. In the gate examination as well, you would see a lot of questions are coming from generator matrix, parity matrix. They will have the word Hamming code, but it doesn't mean that you need to apply any concept of Hamming code there. With the basic concept of linear code, we can solve it. So whatever the concept that we have learned, based on that we can solve those problems, right? Purely on Hamming code, there has not been any question in the examination till this date. Now next topic would be cyclic redundancy check, CRC. That topic would be of hardly 10 minutes. So till this date only one question has been asked, and that was also very easy. So that topic as well we will learn on surface level only. So in Hamming code and in CRC, you would see that, sir, you are teaching on a very surface level. You are teaching the way other coaching institute teach. So this topic would be taught in that manner only. If you want to learn in depth, then you need to study computer organization and computer networks. So these are the topic of COA and computer networks, and these are there in CSE syllabus. In CSE, if you would see that always every year one question would be coming from Hamming code. So they are included in the CSE syllabus. If I was teaching CSE student, then I would have taught in an in-depth manner. Now from here onwards in Hamming code, you would see that sir is going on a very, very surface level. Sir is asking us to remember few things the way other coaching institute does. So I am going to do the same thing here. Okay, no offense to anyone, like everyone is a good teacher. I'm just telling that this particular discussion would go on a surface level. Okay, and hardly 20-30 minutes of discussion would be there, and hardly you need to remember 3 to 4 things, and we will do so much of practice that within this session only you will be able to remember these things. Okay, and you can make the short notes as well, right? So we will get started with the discussion of Hamming code, but the screen is lagging. Okay, screen is lagging a bit, so I will pause the video and then I will come back. So till then you revise whatever that we have studied, and then we will get started with Hamming code and CRC. Yeah, thank you. Yeah, welcome back. So now we need to study about Hamming codes. So what is the first property of Hamming code? That they are the linear code. Okay, so they are the linear code. Whatever the property that we have already seen, for all the linear codes, that property would work for the Hamming code as well. What all are the properties? The properties are that all 0 code word would be a valid code word. Okay, along with that, this property was there, and along with that, what was the property? One property was that your d minimum would be equal to weight minimum, right? Okay, now it will be represented by n comma k only, where m plus k would be equals to n. What is m, what is k, what is n? That you already know. K is the data bit length of data word, then length of code word is n, and m parity bits you are using. Now here there is another property. What is that property? That your 2 to the power m should be greater than equals to m plus k plus 1. It would be tougher to remember, so what do you remember? That your 2 to the power m should be greater than equals to n plus 1. So as of now, I have asked you to remember 2 things. One was singleton bound. This is not specific to Hamming code. This singleton bound would work for anyone. So that singleton bound was n minus k plus 1. This would be tougher to remember, so how you can remember? So d minimum should be less than m plus 1. DM, right? Have you heard this term DM? I have the course of this particular coaching. Can you please DM me? Direct message. DM. So d minimum should be less than or equals to m plus 1. Right? Okay. And other thing that I'm asking you to remember, that is your 2 to the power m. Now m has already come here, so here n would come, n plus 1. So better than remembering n minus k, m plus k. So you would mess it up in the examination, right? Here you will put plus, here you will put minus. So everything would be messed up. So better remember these two things. Okay. D minimum should be less than equals to m plus 1. dm you would remember, and here 2 to the power m. So if m has already come, so here n would come. In none of the formula k is coming. So don't remember k. Okay, because k is studied with the pure concept. Here I am asking you to remember this one. Sir, how this formula came? Not important for you, but let me tell you in brief manner. I will tell you. So let's just say your k was 4, m was 3, so your n was 7. What has happened to the pen? Okay, let it be. Yeah, so k was 4, m was 3 and n was 7. That means you are generating a code word of length 7. Now in this code word, how many kind of error could be there? Sir, it might happen that there is no bit of error, or it might happen that sir there is 1 bit of error, or sir 2 bit of error, or sir 3 bit of error. So how many type of error could be there? 8 type of error, no? Sir, no bit of error, 1 bit of error, 2 bit of error, 3 bit of error, 4 bit of error, 5 bit of error, 6 bit of error, 7 bit of error. So total 8 type of error would be there. Now in Hamming code, the job of this parity bit would be, now how many pairs this parity bit can generate? Like parity bit get a length of 3. That means this parity bit can generate 2 to the power 3 pairs. So the job of these 2 to the power 3 pairs, that means this job of these 8 pairs, which will be 0, 0, 0, 0, 0, 1 till 1, 1, 1. So job of these pairs would be that they compensate for all the type of errors. So here the total errors are happening, that is n plus 1. And now these 2 to the power m pair, these 2 to the power m pairs of a parity bit should compensate for all kind of errors. So your 2 to the power m should be greater than or equals to n plus 1. Is that clear to you or not? Not much clear that sir why they need to compensate. No need to study that much of depth. If you are remembering this particular thing, then at least you will be able to write down this formula. That is 2 to the power m should be greater than or equals to n plus 1. Okay, and I have already told you that Hamming code we are going to study on surface level only. So don't expect much of depth. Okay, surface level that would be more than enough. So what you need to remember, 2 to the power m should be greater than n plus 1. Now this n plus 1 will not be a tough task for you to remember, because you know that if n code words are there, that means total combination will be n plus 1. So now you have a better idea how to write down this formula. So 2 to the power m should be greater than or equals to n plus 1 and d minimum was less than m plus 1. This is generalized. This is for general only and this is for Hamming code. So this would work for any kind of code word, right? For any kind of code word this would work, but this is only working for Hamming code. Now let's just say k is equals to 4. What does that mean? That means 2 to the power m should be greater than m plus k plus 1. That means 2 to the power m should be greater than m plus 5. Okay, now what could be the value of m? If m is equals to 1, then 2 should be greater than 3, not working. If m equals to 2, then 4 should be greater than 7, not working. If m is equals to 3, then 8 is greater than or equals to 8. That is fine. So what should be the answer? M equals to 3. So number of parity bits should be equals to 3. K are the data bit. So what does that mean? N will be equals to 7. So 7, 4 is a valid Hamming code. 7, 4 is a valid Hamming code. Now a lot of valid Hamming code could be there, but 7, 4 is very famous. So this question I am asking, which of these are valid Hamming code? 7, 4 is very famous. What about 15, 11? Let's check that. So for 15, 11, what is the scenario? Value of n is 15, value of k is 11 and value of m is 4. What do we say? 2 to the power m should be greater than or equals to m plus k plus 1, or you can say n plus 1. So 2 to the power 4, that would be 16, should be greater than or equals to n plus 1. What is n? 15. So 16 equals to 16. That means this will also work. What about this one? 2 to the power m. Let's do it here only. So here value of n is 31, value of m is 5, right? So 2 to the power m should be greater than or equals to n plus 1. So 2 to the power 5 should be greater than or equals to 32, which is correct. What about this one? These are very famous actually, 15, 11, 31, 26. What about this one? N is equals to 13, m is equals to k. So 2 to the power m should be greater than n plus 1. Again and again you write down this formula, it will be clear in your mind. So 2 to the power 2 should be greater than 14, which is not correct. So this answer is not correct. Okay, well and good, very simple thing. Now these d minimum and everything is fixed in case of Hamming code. Okay, in case of Hamming code, d minimum is fixed, that would be 3. For Hamming code, you are having fixed minimum Hamming distance, that is equals to 3 only. Okay, now what do you think, what will be the maximum number of detectable error? You know that d minimum is equals to td plus 1, and other thing you know that d minimum equals to 2t plus 1. So 3 minus 1, that would be 2. 3 minus 1 divided by 2, this is 1. So only thing you need to remember is that for Hamming code, this thing you need to remember. For Hamming code, d minimum, these are some standard code, no? That's why we are studying in this manner. Like these are standard code. That means if this happens, this happens. So they are some standard codes. So d minimum equals to 3. This is something that you need to remember for Hamming code. So detectable error would be 2, correctable error would be 1. Okay. So in Hamming code, this is the new thing that you are learning, and this is the new thing that you are learning till now. Now let's take an example of 15,11 Hamming code, and let me explain you what kind of questions can be asked. Okay. So 15,11 Hamming code. So have some patience, just look at the screen, you will be able to understand. So what is the number of data bit? 11. What is the number of parity bits? 4. And what is the number of total code word length? That is 15. Code word length is n is equals to 15. So in code word total 15 places would be there. C1, C2, C3, C4 till 15 places would be there. Now in these 15 places, your data bits would be 11 and 4 would be parity bits. So previously what we used to do, sir, data bit, parity bit, data, parity, or sir, parity, then data. This is what we used to do. But in Hamming code, in standard Hamming code, again I am saying, in standard Hamming code, the position of parity bits are fixed. What that position would be? Sir, position would be 1, 2, 4, 8. That means the position would be in 2 to the power something. Either they will be at the first position, or they will be at the 2 to the power 1, or at 2 to the power 2, or 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, 2 to the power 7. So they will be in the position of 2 to the power. That means these are your 15 position. So your parity bit would be here, or here, or at the fourth position. So this should be P3, but I will write it down as P4 only. Okay, just to maintain the consistency that C4 is written below P4. So it is actually P3. This is the third parity bit. And where will be your fourth parity bit? Fourth parity bit would be here. So basically your P4 is third parity bit. Okay, but we are writing down as P4. And P8 is fourth parity bit. But we are writing down as P8. Is that understandable to you? The position of parity bit is fixed. This is a standard Hamming code. So they have made some standards. Right? Like a lot of kind of code would be there. We are only studying about Hamming code. Hamming code is having some standard. Having some standard means some standard rule it is having. Previously we used to write down data, parity, parity, data. So what do you think, what is Hamming code? Hamming code is asystematic linear code. Hamming code are asystematic linear code. Why asystematic? Because in systematic data, parity, parity, data, this scenario should have been there. Right? First data, first all data and then parity, first all parity, then data. So this should have been the scenario in systematic code, but this is asystematic because first parity would come, then data would come, then parity, then 3 data, then parity, then all data. Right? So data bits are 11. So data bit 11 would be written in this manner. Charger is not on, guys. Okay, so I will turn on the charger. Yeah. So actually screen went off. So from there I can understand that charger is not connected. So D1, D2, D3, D4, D5, D6, D7, D8, D9, D10 and D11. Now sir, these data bits would be given. I need to determine the parity bit. Sir, previously if I need to determine the parity bit, what I would have done? Sir, I would have taken the use of generator matrix. So here they want to kill this generator matrix, that's it. Without the help of generator matrix, with our simple logic, you need to determine the parity bits. P1, P2, P3, P4. So you will listen to me very, very carefully. What will be your P1, P2, P4 and P8? Listen to me very, very carefully, otherwise you will not be able to understand. You need to determine parity bit 1. First parity bit you need to determine. That means you will care about first place, then leave one place, third place, leave one place, fifth place, leave one place, seventh place, then ninth place, 11th place, 13th place and 15th place. So if I need to determine P1, then I will do C1 XOR C3 XOR C5 XOR C7 XOR C9 XOR C11 XOR C13 XOR C15. But I know that C1 is itself P1, so I will ignore that. So what I would do, I would actually do C3 XOR, basically I would have actually started from C1 XOR C3 XOR C5 XOR C7 XOR C9 XOR C11 XOR C13 XOR C15. This is how I should have done, but I know that C1 itself is P1, so I have to ignore this one. This is just a method I am telling, that how will you remember, okay? Otherwise people you usually mug it up, but we are not going to mug up. This is how I will remember. P1 is there, that means I will start from first bit. First drop 1, drop 1, drop 1, drop 1, in that manner I will keep on going, okay? Next I will talk about P2. So P2 is there at the second bit, P2 is there at the C2. So it will start from C2, but there is 2 written, no? So it will take 2 bits at a time, then drop 2, 2 bit at a time, drop 2, 2 bit at a time, drop 2, drop 2, 2 bit at a time. Is that clear? Let me explain it again. Sir, I will take 2 bit at a time, C2 XOR C3, then drop 2, C4, C5, then C6, C7, then I will drop C8, C9. I will take C10, C11, I will drop C12 and C13, and then I will take C14 and 15. 2, 3, 6, 7, 10, 11, 14, 15. But I know that C2 is unknown to me. Like C2 only I need to find out. No, I need to find out P2 only. So I will ignore this one. I will just remove that, and this would be my P2. So somewhere in rough you can write down this logic. I am giving you this space. Here you can write down this logic what I am telling. Okay. Next to P4. So I know that, sir, P4 is starting from 4th position. P4 is starting from 4th position. So what I would do? I will take 4 bit at a time and then drop next 4. Then I will take 4 bit at a time. After that there are no bits, so I don't need to care about that. So what I would do? I would take 4 bit at a time. So C4. So C4, C5, C6, C7, but I know that C4 itself is P4, so I will ignore this C4. What I will write down? C5, C6, C7. Then drop 4. That would be 8, 9, 10, 11. So it would be 12, 13, 14, 15. 12, 13, 14 and 15. This is what we are getting. Next P8. P8 is starting from 8th position. That means what I will take? 8 at a time, then drop 8, then 8 at a time. Basically 8 at a time. So C8, C9, C10, C11, 8. 1, 2, 3, 4, 5, 6, 7, 8. So till from C8 to C15 I will take, but I know that C8 I itself need to find out. That means it would be C9, C10, C11, C12, C13, C14 and C15. This is how you would be able to find out the parity bits. Is that understandable to you? Nothing to understand. You need to remember. That's it. Now let's just say, sir, what if there was only till C12? These C13, C14, C15 was not even there. Sir, n was equals to 12. What if, sir, this was the scenario, that n was equals to 12? Then sir, you would say that, sir, there would be problem in these guys. Like these C14, C15 would not come. This C4 would be stuck at C12, 13, right? So till the point you are having the bits, till that point only you will write down. What I mean to say is that, sir, if I am writing P8, now P8 would say that, sir, I need 8 bits, but actually you are having 5 bits only. So till 5 bit only you will write down. C8, C9, C10, C11, C12. C8 is something that you need to find out. That means you will write down C9, C10, C11, C12. So till this point you will write down. Are you able to understand this point? That if it is a valid Hamming code and here it is requiring 8 bits, but actually you are able to get 4 bits only, then till 4 bit only I will write down. Is that clear? We will see some example. It will be more clear to you. But I hope it is very simple thing that is clear to you. Okay. If you are not getting 8 bits, that is not a matter of concern. At the point where it is ending, at that point it should end. That's it. Okay. So P1, how did you write down? First place, drop 1 place and keep on going. P2, take 2 at a time, drop 2 at a time. Take 2 at a time, drop 2 at a time. P4, take 4 at a time, drop 4 at a time. Take 4 at a time, drop 4 at a time. P8, take 8 at a time, drop 8 at a time. Okay, and what will be the position? Position starts from here only. C1 means start from here. P1 means start from 1 position. P2 means start from 2 position. P4 means start from 4 position. P8 means start from 8th position. Right. So this is the scenario. Now let's see the questions. With respect to questions, it would be more clear to you. 7,4 Hamming code is there. Data bit is this one. What would be a transmitted code word? Now I know that the length of the transmitted code word would be 7. So I know that my transmitted code word would look something like this. Okay. How many parity bits would be there? Sir, parity bits would be 3. So these parity bits would be P1, P2, P4, right? And I know the position of parity bits, those will be 1, 2, 4, 8 and so on. So parity bits are 1, 2, 4, 8th position is not even there. I don't even need the 8th parity bit, and you can see here 8th parity bit, like 3 parity bits are only there, no? So only 3 parity bits are there. 4th parity bit will not even come into action. Now what about the data bit? So data bit would be fed 1011. 1011. Okay, data bit would be fed in this manner. Right? Now I need to find out P1 value. So what I will do? So start from C1, drop 1 and keep on going. But starting from C1 itself is P1, so I will drop it. Drop this one as well. I would do C3, XOR, drop 1, go with the next one. C5, XOR, drop 1, go with the next one. So C3, C5, C7. C3, C5, C7. What would be P2? P2, C2, C3, drop these two guys and then take these two guys. So C2, C3, C2 will be dropped. Why so? Because C2 itself is P2. So C3, drop two guys. That would be C4, C5 and then take C6, C7. C6, C7. So C3, XOR, C6, XOR, C7. That answer would be 1. And what about P4? Start from 4, take 4 guys, but you know that C4 will be dropped. So only 3 guys are left. So I will take these 3 guys. Ideally, I should have taken C4, C5, C6, C7, then drop 8, 9, 10, 11. Then I should have taken 12, 13, 14, 15. But 12, 13, 14, 15 are not even there, so I don't care about them. Okay, and C4 will be dropped only because it is itself P4. So what you are getting? 0, XOR 1, XOR 1. So these are your parity bits. Your parity bits are 0, 1, 1. Let's check back the calculation once again. Yeah, it is coming out to be 0. What about these two guys? 1, 1, 1. It is coming out to be 1 and this is 0 only, no? 1 XOR 1 is 0, 0 XOR 0 is 0. So you are getting your parity bits at 0, 1, 0. So what you are getting? Your data word would be, so that would be 0, 1, 1, 0, 0, 1, 1. That would be the data word. Now I will tell you one thing. Either this option could be mentioned in the examination or exact opposite could also be mentioned. Like this is also correct or exact opposite. Like in some textbook you would find out that, sir, this is P1, this is P2. What I mean to say that, sir, C1, C2, C3, C4, C5, C6 and C7 you will write it down. Sir, in some textbook in our college I have studied that this is P1, this is P2 and this is P4. And sir, this was my D1, this was my D2, this was my D3 and this was my D4. Exactly the opposite. Just you need to invert. So if this option is written 1, 1, 0, 0, 1, 1, 0, that can also be correct. Okay, just the reverse of this. Last bit will become the first bit, first will become last. So 1, 1, 0, 0, 1, 1, 0, this is also correct. Is that understandable to you or not? Okay, so this is how you will determine the parity bits and this is how you will write down your answer. Just remember one thing, that exact opposite can also be mentioned. This is a GATE CSE problem. In GATE exam, in EC they are not asking much questions from here, but in GATE CSE they have asked. So assume a 12-bit Hamming code word consists of 8 data bits and 4 check bits. So K is equals to 8, M is equals to 4. Is it possible? Although you don't need to check, but it is possible. How it is possible? So 2 to the power M should be greater than N plus 1. So 16 is greater than 13. Yes. So this code word, which is 12, 8, that is surely possible. So 12 places are there. Now they have made the data bits are in this manner. Data bits are in this manner. Now what do you see here? first bit is in the last. Basically C1 is in the last. Are you able to understand this point? So they have made it in this manner that if I talk about the code word, so C1 they are representing by parity bits. So I will represent the code word in, how would I represent the code word? Code word, let's represent by n. Okay, so they have said n12, n11, n10, n9, n8, n7, n6, n5, n4, n3, n2, n1. Now according to us, here there will be parity bit, here there will be parity bit, and here there will be parity bit, and here there will be parity bit, and then data bits would be there: d1, d2, d3, d4, d5, d6, d7, d8. So in that manner they have said. Okay, parity bit they are representing by C1 actually. So what do you think, what will be your C1? P1, or you can call it C1. Drop first one, then take one by one. Take one, drop this one, then take one by one. I will drop n1 as well, but because itself is P1. So my answer would be D1 XOR D2, right? So you see from here only, right? Directly. So starting from here, D1 XOR D2 XOR D4, D1 XOR D2 XOR D4, D1 XOR D2 XOR D4 XOR D5 XOR D7. So what you are getting? D1 XOR D2 XOR D4 XOR D5 XOR D7. So D1 is 1 XOR D2 XOR D4 XOR D5, which is X, XOR D7. Now the value of P1 is given actually, P1 or C1, that is equals to 0. So this value will come out to be 0. So what do you think, what should be the value of X? Directly you can say that value of X should be equals to 0, sir. Say yes or no? Very straightforward, no? The value of X should be 0. If it is 0, then 1 XOR 1 will be 0, 0 XOR with 0, 0 XOR with 0, answer will be 0 only. So X should be equals to 0. Okay. Now I need to determine the value of Y. That means somehow I need to introduce C8. This will be my target. That somehow I introduce C8. So what do? I actually find out C8, which is my P8. I actually try finding out C8. I am trying to find out the value of Y. Itself I am trying to find out the value of Y. So what I would do? What would be my P8, or you can call it C8? So C8 would be starting from the 8th position. It will take 8 bits into action. 1, 2, 3, 4, 5. So only 5 it is having, and in these 5, this will be gone itself. C8 will be gone itself. So it will take only D5, D6, D7, D8. D5, D6, D7, D8. So D5, D6, D7, D8. So X XOR 0, XOR 1, XOR 1. And this is equals to Y. What is the value of X? X value is 0 only. So you will put 0 here. 0 XOR 0, 1 XOR 1. What will be the answer? 0. So X equals to Y equals to 0. This was the question. Very easy. Okay. Now we will see how to determine the error and how to correct the error. Okay. So this was the valid code word which was sent. Now what really happened? The received code word became 010100. So I need to detect the error and I need to correct the error as well. So basically I know that there is an error in this and third and fourth both are having the error. Let's do only 1 bit of error, no? Basically 2 bit of error it will not be able to correct, no? Like we need to detect the error and we need to correct it as well. So I need to correct the error. So how many errors it can correct? Only 1 error it can correct, no? So only 1 error has been done, that there is a problem in the third bit from the left. So what I would do, I would make a parity check bit 1. Basically I have seen that this is the length 7. Length 7 is there, 3, 3, 6, 7. Length 7 is there. And it will be mentioned how many parity bits are there. It will be mentioned in the problem that 3 parity bits are there. It would be mentioned. Sir, 4 is also possible, no? But it would be given. It would be given. that 3 parity bits we are having. They can give the position of parity bits as well, that they have given this position, this position, this position, and this position. These are the position of parity bits. Now you need to analyze this received code word. You need to check whether it is a valid code word or not. If it is not valid, then what changes you need to do such that it becomes a valid code word. This is what they are asking. So I went to this guy. Now I want to check whether it is a valid code word or not. So there is a method. What is the method? I need to determine parity check bit 1. So that parity check bit 1 would be start from position 1, drop 1 place, go to position, next position, drop 1 place, go to next position. So starting 0 XOR, drop this one, go to the next one. 0, drop this one, go to the next one. 0, drop this one, go to the next one. What is the answer you are getting? 1. Now I will write down parity check bit 2. Parity check bit 2. So these are your parity bits. Start from second position, take 2, drop 2, take 2. So take 2, drop 2, take 2. What you are getting? 1. Okay. Now start from, although it is the third parity check bit, but I will call it PC4 because now I need to start from the fourth position. Because what will be the position of my parity bits? The position of my parity bits would be P1, P2, P4, P8. So your position of parity check bits would also be PC1, PC2, PC4, PC8. The method goes same. So I will go to the fourth bit now, take 4, drop 4. So I will take 4, 0, XOR 0, XOR 1, XOR 1. And then what I would do, from the downward, I will see what is the decimal equivalent I am getting. So what I am getting? 0, 1, 1. Now what is the decimal equivalent of this one? That is 3. That means the third bit is an error. Third bit from left in error. If it is an error, I can correct it. So what will happen? 0, 1, 0, 0, 0, 1, 1 was received. Actually, what was sent? This was sent. So you see, this was sent. So here I have just verified the method. What does the method says? Only you need to remember is you need to remember the method. Previously, what did you remember? You remember the bit position, although it would be given. You can see that bit position are given. So here as well, everything they would give that M3 parity bits are there. What all are the position? What you need to check? You need to apply the parity check bits. PC1, PC2, PC4. PC1, stand at 1, start from 1, drop 1. Here there is nothing unknown, no? 0 is known, 0 is known, all these are known. So you will not drop anything. Starting from 1, 0, XOR 0, XOR 0, XOR 1, 1. Starting from PC2, starting from 2, take 2, drop 2. Take 2, drop 2, take 2. Starting from 4, take 4, drop 4, take 4, drop 4. That's it. So whatever the answer that you are getting, read from the downward. 0, 1, 1. Read from the downward to upward. 0, 1, 1. And what is the decimal of that? That is 3. That means third bit is in error. Yeah, third bit is in error. That is 0 should be flipped to 1. 0 should be flipped to 1. So this is your actual code word. Okay, let's solve one more problem. It will be clear to you. So received code word is this. Find out the transmitted code word, and along with that you need to tell the data word as well. And I am saying that this is your standard Hamming code. Standard Hamming code. So what is the pattern of standard Hamming code? There could be two patterns actually. Either you write down in this manner, backward, or you write down in the forward. So this has to be mentioned. Actually in the examination they will mention everything. I am pretty sure. They will mention the position of parity bit as well. What they would do, they would mention these will be a parity bit. Although you already know these will be my parity bit. And they will mention that these are your data bits. D1, D2, D3, D4, D5, D6, D7 and D8. Right? Wait a second. 110, 100, 1111. 11. Oh, sorry. This I have written wrong. What is my received code word? Let me write it down again. This is your received code word. 1, 1, 0, 1, 0, 0, 1, 1, 1, 1, 1, 0. Right? Parity bit would be there at the position P1, P2, P4, 5, 6, 7, 8. This would be your parity bit. And what would be your data bit? D1, D2, D3, D4, D5, D6, D7. So either they would give it is 7 comma, what you see here? What is the number of 7 plus 4? 4 parity bits are there. Parity bits are 4. Data bits are 7. So it would be 11. So this is your 11 comma 7 Hamming code. Okay. So this would be given in the examination. This position would also be given in the examination. You just need to find out whether this is correct or not. So what you would do? Sir, parity check matrix 1. Start from first position, drop 1 and keep on going. So 1 XOR with 0, 1 XOR with 0, XOR with 0, 1 XOR with 0, XOR with 0, XOR with 1, XOR with 1, XOR with 0, XOR with 1, XOR with 1, 1 XOR with 0, XOR with 0, XOR with 1, XOR with 1, XOR with 0. The answer is 1. Parity check matrix, parity check bit 2. 1 0, drop 2, 0 1, drop 2, 0. So 1 0 1 1 1, it would be 1 only. Okay, 1 XOR 0, that would be 1, 0 XOR 1, that would be 1, 1 XOR 1, that would be 0, 1 XOR 0, that would be 1. Okay, and let's recheck the first one. Let's recheck this one. 1 0 0 1 1 0. So 1 0 1 1 0 1 1 1 0 0 1 1 1 0 1. Yeah, that's correct. Let's check parity bit 4. I will write down. Okay, parity check bit 4. I will write down. Parity check bit 4. So 1 2 3 4. Fourth position, 1 2 3 4. Fourth position, take 4 into action, then drop 4, then take 4, drop 4. So 1 XOR 0, like from the fourth position you take 4 and then drop 4. That's it. All bits are completed. So what will be the answer? 0 here, because 1 XOR 0 XOR 0 XOR 1, that would be 0. And parity check 5th, not 5th, sorry, parity check 8th I will write down. Go at the 8th position, take 8 at a time and then drop next 8. So 1 2 3 4 5 6 7 8. This is the 8th position. Take 8 at a time, but I am able to take only 4. Actually I should have taken 8 bits, but only 4 are present. No, only 4 are present. So what will be the answer? That is 1, right? So answer is, looking from downward, go till upward. So 1 0 1 1. What is the decimal equivalent for this one? That is 11, right? 1 2 4 8, right? So it would be 11. So decimal equivalent is 11. That means 11th bit is in error. So 1 2 3 4 5 6 7 8 9 10 11. So total 11 bit are there. This bit is in error. So total answer is received, like what would be the valid code word? Valid code word would be, this would be the valid code word. Okay. Sir, again it is very mechanical, like we are not doing engineering. I don't feel like doing engineering. Yes, you don't feel like doing engineering and I can understand that. Just there is some method, apply that method and get the answer. In that way only we are learning this particular topic, because it is a topic of computer science, not of your EC engineering. But it has been mentioned in the syllabus, that's why we have to do it. There is no shortcut available for me. So I guess Hamming code has been completed. Right? Yeah. So Hamming code has been completed now. In Hamming code, if I just summarize what we have understood, starting from the first slide, everything we already knew. Just one thing, 2 to the power m should be greater than n plus 1. Other formula is 2 to the power d minimum should be less than dm m plus 1. So you remember these two things. Then everything came down to the d minimum is fixed here, d minimum equals to 3, maximum number of detectable error could be 2, maximum number of correctable error would be 1. Now if I talk about the standard Hamming code, then position are fixed of parity bits, p1 p2, first position, second position, fourth position, 8th position, 16th position, 32th position. In that manner positions are fixed. How would you find out p1 p2 p4 p8? p1 1 bit at a time, drop 1, 1 bit at a time, drop 1, 1 bit at a time. p2 2 bits at a time, drop 1, 2 bits at a time, drop 1, 2 bits at a time. And whatever that you wanted to find out, that you will remove from this particular expression. So in that manner you will find out. We have seen the example as well, and we saw this gate PIQ as well. And now we need to see the transmitted code word. So based on the transmitted code word, received code word, based on the received code word, if there is some error, if there is an error, then how will you rectify it? That we need to check. Let's just say, sir, there was 2 bit of error. Sir, when the example that you wrote, that was actually having 2 bit of error. So he would be able to recognize that there is 2 bit of error. Basically, this answer will not come out to be 0, 0, 0. If this answer is coming 0, 0, 0, what will be the decimal equivalent? Decimal equivalent will be 0. That means 0th bit will have the error, but we are actually starting from the first bit. So 0th bit will have the error. That means no error is there. So if there is 2 bit of error, then answer will not come out to be 0, 0, 0. It would come out to be something else. But you will not be able to recognize that, you will not be able to correct the bit error. You would be able to know that yes, error is there. But now you don't know which bit to correct. Are you able to understand what I am saying? Okay. You will be able to understand that there is a bit error, but which bit will be an error, that you will not be able to understand. Right. So this scenario we saw, and that's it. Another example we saw. Again, the same thing we need to do. Just write down the received code word, parity check bit 1, parity check bit 2, parity check bit 4, parity check bit 8. And the same way is there. Go from downward to upward. See the decimal equivalent. That bit is an error. Answer will be done. Okay. Hemming code is error detection and correction code. You have detected the error as well, and you have corrected the error as well. Maximum it can detect 2 bit of error, and it can correct 1 bit of error. 2 bit of error corrected and 1 bit of, 2 bit of error detected and 1 bit of error corrected, right? But CRC is not a linear code. Okay, it is a cyclic code, cyclic redundancy check, CRC code. So this is your cyclic code, not a linear code. Okay, so they are your cyclic code, and they will only be able to detect the error, no correction, no correction, no correction. Okay, and this is the line which you will be able to understand with respect to the questions, that this line you need to remember. CRC doesn't care about leading 0. What do you mean by leading 0? 0, 1, 1, 0, 0. Which is the leading 0? This is the leading 0. So if a 0 is coming before, then CRC will not care about this leading 0. Okay, CRC doesn't care about this leading 0. So if you are solving the problem of CRC, then this 0 will be of no use. These 0 will be of use, but this 0 will be of no use. Okay. So we will understand it. What do I mean by this? CRC doesn't care about leading 0. We will understand. But let's write down the example, that 0, 0, 1, 1, 0, 1, 0, 0. So they are the matter of concern, but they are not the matter of concern. Okay. So let's solve the problem. That's it. This is how the problem would be given, that there is a data word, there is a divisor polynomial. You need to find out that transmitted code word. Sir, how will I find out the transmitted code word? So first I will look at the divisor polynomial. So what this polynomial is given? Sir, x to the power 4 plus 0 into x to the power 3, 1 into x to the power 4 I can write down, plus 1 into x to the power 2 plus 0 into x plus 1. This is my divisor polynomial. So from here I will find out my divisor. That would be 1, 0, 1, 0, 1. So my divisor is 1, 0, 1, 0, 1. Now what is the maximum degree here? Maximum degree. Maximum degree is 4. So my dividend would be, what would be my dividend? My dividend would be, sir, this data word, that is 1, 0, 1, 1, 0, 1, 0, 1. And in the end, I will add up 4 0 bits. Now what I need to do, this is my dividend and this is my divisor. Again, let me repeat. First I saw this one, this is my data word. Okay, let's hold on to this one. My eyes went to divisor polynomial. From this divisor polynomial, x to the power 4, x to the power 3, x to the power 2, x to the power 1, x to the power 0. So whatever the maximum that we are starting from, now no one will say that, sir, x to the power 5 also could be there. CRC doesn't care about the leading 0. Forget them. Right? So 1, 0, 1, 0, 1. Divisor. And what is your dividend? This would be your dividend, but here you see the maximum degree. Maximum degree is 4. Or you can see number of bits. In the divisor, how many number of bits are there? 5. So 5 minus 1. 4 will be your, what will? It would be your 0. So 4 0 you need to add after this data word. Is that clear? Okay. Either you look here or you look here. So 4 zeros you need to add. Now what you need to do? You need to do the process that I will divide this particular thing by this particular thing. So I will do the division now. What I need to do? I need to do the division. So better let's just copy it now. This will be divided by 10101. 10101. So what is the answer that I am getting here? That is not a matter of concern. My matter of concern would be my remainder. So modulo 2 division would be there. Basically whatever that has been written here, 10101. So whatever that has been written here, whatever that has been written, that will come here. 10101. And what you will do? You will do the XOR operation. 0 XOR with 1, 1, 1, 0, 0, 0. Doesn't care about these guys. These guys will be 1. Now here there are 5 bits. So here also there has to be 5 bits. So 3 bits will come downward. Now again whatever that has been written here, that would come here. Again you might be saying that sir looks like it doesn't look like engineering, but it is what it is. In GATE 124 this kind of question only came. Ditto same question. Data word was given, divisor polynomial was given, they asked you to find out the transmitted code word. That's it. 2 marks. Can you believe that? So learn the method, you have to learn the method. We cannot do anything. Okay. Now 1 XOR with 0, sorry 1 XOR with 1, 0, 0, 0. Doesn't care about this guy. Here there are 4 bits left. Actually 5 bits should come. So this will also come. So again whatever that has been written here, that would again come into action. 5 bits should come. These 2 will not be cared. So this 0 has come. Now these next 2 zeros would come. So 1 0 1 0 1. This is 0 0 0 1. Now this guy should come. Now 4 bits cannot be fulfilled, right? Other space I am not having, no. Basically 0 0 0 1 I got. They don't care about these zeros. So other space I am not having. So I am left with this my final answer. So my parity bits were these 4. These were actually my parity bits. I added this 0 0 0. Then I did that division process. I know that my parity bits are 4. Now these 4 parity bits were fake. I just added 0 0 0 0 blindly. Every time I would add 0 0 0 only. So those were fake. So what are the real ones? These are the real ones. So your transmitted code word would be very straightforward question, right? Your transmitted code word would be 10110 101 0010. That's it. This kind of question was asked only in 2 marks. Are you able to understand? Nothing to understand, just a method, right? So just understand that I am in class 12th or class 11th or class 10th. Sir, some topic is there where I need just to understand that this is chemistry. When you are preparing for JEE, physics was interesting, maths was interesting, but in chemistry, there was some topic which you have to mug up. So here you need to remember the method. 10101. From here I got maximum degree was 4. That means here my parity bits would be 4. I don't know what all are my parity bits. That's the task to find out. So what I would do, I would add up these 4 zeros in the end. If I added up these 4 zeros in the end, I will divide it by 10101. So this would be your modulo 2 division. Whatever that has been written here, it will keep on coming. Do the XOR operation. Keep on cancelling your leading zeros and get the final answer. Now, in the final answer, here also someone will cancel, but you know that this division will not proceed. That means eventually I need last 4 bits. So these last 4 bits will be my parity bits. So my parities are 0010. These are my parity. Okay. Let's see another problem. Data word is given, divisor is given. You need to find out the code word. So can you let me know what will be the value of m? A lot of people directly will say that sir value of m is 4. Wrong. Because sir here there are 4 bits. No. What would be the divisor polynomial for this one? X to the power 3, x to the power 1 plus 1. This would be the scenario, no? Right? So you see the total number of bits here minus 1. So m would be equals to 3. Or you can make the divisor polynomial and from here you can say that m would be equals to 3. Is that clear to you? Okay. Now 0, 1, 0, 0, 1, 1, 0, 1. And I need to add up 3 more bits here. And I will be dividing by 1011. What will happen to this guy? I told you CRC doesn't care about leading 0. Only in the remainder they will care about the leading 0. Here they don't care about this guy. So this guy will play no use. So directly 1011 will be written downward. Some people will be starting 1011, they will have some issue. Okay, so directly you need to write down here 1011. So what you will be getting? So 0 1 0 0. Then make sure these are 4 bits only. 1011 I have written here, 0 0 1 0, then 0 0 1 0, then 1 0 is taking downward, then again 1011 would come. Here 0 0 0 1, right? So this 0 has come. Now 1 1 0 0 would come. सब सही जा रहा ना भाई? Like I should have written it in a border manner, right? So this 1 has come, then this 0 has come, now this 1 has come, and next 2 0 has come. Okay, 1 0 1 1, 0 1 1 0. Now this guy has come, 0 1 0. They don't care about these guys, right? 1 0 1 1. This is 0 1 0 1. Now everything has come down, no? This 0 has come down, this 0 has also come down, and this 0 has also come down. So there is nothing more to take out. That means this is my final remainder, right? And I needed how many bits? I need only 3 bits, right? I need only 3 bits. So these will be my final 3 bits. So what will be my transmitted code word? 0 1 0 0 1 1 0 1, and 3 bits only I need. So 1 0 1. So this is my transmitted code word. Okay. So what will be your transmitted code word, that you are able to understand. Now in the received code word, what will be the error, that we need to find out. But we will be only able to find out if the error is occurred or not. What will be the error, you will not be able to tell. But if the error has occurred or not, so what do you think? Error has occurred or not? This was your valid code word. For this divisor polynomial 1011, same divisor polynomial is there. Now your received code word is, sir, 0100, everything is same, 0100, then 110, sir, 110, then 1011. In place of 1011, what you are having? 1101. So 1101. So these 2 bits are in error actually. So error has actually occurred. So now what you will do, you will follow the same process. This will be your dividend, and this will be your divisor. So what you will do? You will do the division. You will do the division. And what you will notice is that the remainder is actually not coming out to be 0. Basically, if there was no error, so in place of this 000, what would have been there? 101. So here what would have been the scenario? If there is no error, that means if you divide this code word, or if you make this as dividend and you divide it by 1011, you would see that remainder would come out to be 0. Is that clear? That means this is a valid code word. If it is a valid code word or not, that we need to check out, right? So what I did, I took this guy and then divided by 1011. I will check the remainder. Here code word is given, that means data word is also there, along with that parity bits are also there. Everything is there. I just need to check if there is some error or not. So I will divide this particular thing by 1011. So 1011. So what you are getting? Oh. What is the problem I am doing? This is of no use. So 1011. 0 1. So here you are getting 0 0. This is of no use. Then 1 0. Then again 1 0 1 1. 0 0 0 1. This is of no use. Then 1 1 0 1. Right? These 3 are of no use. So this 1 0 1. 1 0 1 1. 0 1 1 0. Then this one comes out, and you are doing 1 0 1 1. What is the remainder you are getting? Sir, 1 1 0. This is the remainder you are getting, which is remainder is not equals to 0. That means there is error. Error has surely occurred. Now sir, how to rectify this error? How to make this corrected? That you cannot do using the CRC, because CRC cannot do any correction. So CRC will only tell that error has occurred, that's it. Correction, I don't know. He only knows error has occurred because this remainder is not 0. Okay, let's solve one more question. This question you can solve and your answer would be done. So I guess this is written correctly only. Okay, not written correctly. So same question is there, actually same question is there. Basically it is just your revision, just you can try it on your own so that you feel confident that sir, yes, I am able to solve the problems of CRC. Okay, so it's simply like your revision only. So what you would do, sir, 1011, again I am doing the same error, this will not come into action. 1011, so what you are getting, 1000, 1011, 1110, 1011, 101, फिर 1, 1011, all 0 I am getting, all 0 I am getting, and next only 1 would come out, right? So this is also not a valid code word. Remainder is not equals to 0. Okay, that means error has occurred. So this 50 minutes of discussion, I know in this 50 minutes of discussion 30 minutes was a boring part only, but it is what it is. Sorry guys, okay, it is what it is. This is how we need to study it. So we have studied it. I thought it would go for 30 minutes, but actually it is going for more than 1 hour. Now from CRC, like good question, like CRC, this kind of question has been asked. From CRC, this kind of question has been asked, that data word is given. I guess this question was only there, or I don't remember. You can see the gate PYQs. Data word is given, you need to find out the code word. From Hamming code, this question has been asked. Try solving this one. Hi everyone, welcome to PrepFusion. So now we are going to solve this particular question, which was asked in GATE 2021 examination. Okay, it was based on Hamming code. So when this question came, at that time there was so much of controversy that it should be MTA. So let's check that out, what this question is saying and what could be the possible answer. And this solution for this particular question have been given by IITs as well. On NPTEL, they have uploaded the video solution of this particular question. Now in that solution, what could be the ambiguity, that also we will check. So whatever the discussion that could be done regarding this particular problem, we are going to do that. So let's get started. What they have given a 7,4 systematic linear Hamming code. So with respect to data word, they have defined some code word. So if this is my data word, with respect to the data word, they have defined some code words. If your data word is 1100, then my code word is 010 is the parity bit and my data bits are 1100, right? Now 1110, then 001 is my parity bits and data words are 110. And if your data word is 0110, then parity bit is 100 and data word is 0110. So this is what they have defined. Now they are asking which of these are a valid code word. So generally what do we study? The Hamming code that we study in this manner. Like for 7,4 we will say that, sir, there will be total 7 bits in the code word. First parity bit would be there, second parity would be there, then data bit would be there, then another parity bit would be there, and then data bits. So this is the general, or you can say this is the standard Hamming code that we study, and this is known as asystematic Hamming code. Asystematic Hamming code. So this is your standard Hamming code, but this is not the pattern here, right? This pattern is not given. If this pattern was given, then what we could have done? We could have find out, sir, parity checker bit 1, parity checker bit 2, then parity checker bit 3, and if these bits are coming out to be 000, that means it is a valid code word, otherwise it is not a valid code word. So this process we would have done. This was your standard Hamming code. But now in the question, they are not giving you the standard way, they are giving you systematic Hamming code. Okay, now you know one thing, that Hamming code is a linear code as well. So if it is a linear code, then it will surely follow the property of all the linear codes. Now what all are the property of linear code? First one is that all 0 will be a valid code. Second one is, to get a particular valid code, if you do the XOR operation of any two valid code word, you would get a valid code word. If I do C1 XOR C2, I will get C3 for sure. I will get a valid code word. And what is the other property? That D minimum is actually equals to W minimum, right? So this property will not be used here. This property may be used and this property will also be used. So basically what I need to do, I need to find, now what will click to me in the examination? First thing, what should click to me? In the examination, it will click to me that, sir, 3 code words are given. I will try finding out other code words as well. What is the value of k here? Data word length is 4. That means number of code words possible. Number of code words possible, what that would be? 2 to the power 4, that means 16 code words are possible. So sir, I will try to find out 16 code words. Out of these 16 code words, only one of them will be valid. But just let me know, will you be able to find out 16 code word or not? Using these 3 code words, will you be able to find out 16 code word? Answer is no. Then how much code words you will be able to find out using this code word? Just focus on the last bit. Here, in all the code words, your last bit is 0. So if you do, let's just call this one as C1, this one as C2, this one as C3. If I do C1 XOR C2, what I will get? Sir, 0, 1, 1, 0, 0. Something is wrong. 0, 0, 1, 1, 1, 1, 0. 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 0, yeah. Right? 1, 1, 1, 0 and 0, 1, 1, 0. Yeah, everything is fine now. Yeah. So, sir, if I do C1 XOR C2, what I am getting? Sir, 0, 1, 1, 0, 0, 1, 0. So, sir, this valid code word, this is also a valid code word. What do you notice here? Sir, last bit is 0 only. If you do the XOR operation of C2 XOR C3, the last bit will be 0. If you do the XOR operation of C1 XOR C3, last bit will be 0. Now, whatever the result that you are getting, let's just say from C2 XOR C3, I will be getting the result of C5. I will do C4 XOR C5, last bit will be 0. I do C1 XOR C5, last bit will be 0. That means, from this particular method, I will be able to check only this option and this option. Now, if my luck is good, then one of the option B and D would match, and I will be able to click on the answer. I am not telling you the solution here. Here I am telling you how a student would be thinking. If I had been a student, this is how I would be thinking in the examination. The first thing that would click to me, surely it is a linear code. It is given as well, and I also know that Hamming code are linear code only. So I will apply the property of linear code, but I will notice one more thing, that all code words are having 0 bit at the last. That means I will be able to determine only option B and D. If my luck is good, I will do the XOR operation of all of them, and one of the option might be matching. Now, can you just let me know, using these kind of code words, how many code words out of these 16 code words you will be able to determine? Using this one, using this one, using this one, using this C4, out of these 16 code words, how many code words you will be able to determine? Just think about it. Sir, 8. Why is that so? Because you will not be able to determine all those code words which are ending with 1. Total 16 are there. With respect to 4 data word, 16 code word would be there. So you will not be able to determine the code words for those data words. You will not be able to determine the code words for those data words which are ending with 1. So how many these kind of data words would be there? So 2 into 2 into 2, these kind of data words would be there, 8. So for 8 data words, you will not be able to determine 8 code word. That means using this particular C1, C2, C3 code, you will be able to determine 8 code words only. Rest 8 code words you will not be able to determine. Is that thing clicking to you or not? Does that click to you? So using these data words, I will be able to determine 8 code words. So I am having data words, and let's simply copy it. No, why I am wasting the time? Let's simply copy it. What I am doing. So this I am calling as C1, this I am calling as C2, this I am calling as C3. So when I do C1 XOR C2, what I am getting? Sir, 0, 0, 1, 0. So here you will get, sir, C1 XOR C2 I am doing 0, 0, 1, 0. So, sir, 0, 1, 1, 0, 0, 1, 0. Let's do C2 XOR C3. So I will be getting 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0. I have got C4, I have got C5. Now what do I do? C1 C2 C1 C3. Let's do C1 C3. So what you will get, sir? 1 0 C1 XOR C3 I need to do, no? So 1 0 1 0. So you are getting 1 1 0 1 0 1 0. We have got C6, right? Now if you do C4 XOR C5, then you will be getting 1 0 1 0 only, doesn't make any sense. If you do C3 XOR C4, what you will be getting? 0 1 0 0. Yeah. So we will do C3 XOR C4. So what I will be getting? 0 1 0 0. And here I am getting 1 1 1 0 1 0 0. So this is the C7 I am getting. And C8 would be all 0 code word will always be a valid code word. So these are the 8 code word which I can determine. I cannot determine any code word which is actually ending with 1. So C1, C8. Now check the option. For 1010, they are saying that your parity bit should be 101. For 1010, your parity bit is actually 110. That means this option is not matching. Now let's go to option D. For 0100, your parity bit should be 011. For 0100, your parity bit should be 011, but it is actually coming out to be 111. It is actually coming out to be 111. So it is also not matching. So your luck is not good. If one of them would have matched, you would have clicked on the answer. It is not good now. Now you are stuck with these two options. Right? So now you need to check these two options. Now, which of them is correct? Which of them is correct? Now, a lot of you guys might not know this property of Hamming code that I'm going to write down. For linear code, what is the property? Like a lot of guys would not know this property as well. But if you have studied in a good manner, I have already uploaded complete video of information theory and channel coding. Everything has been uploaded on YouTube only. So you try to study from there once. Okay. So this property is also there. This property is also there. Whenever we study linear code, we only study this property. But no, 3 properties are there. No. So for the linear code, you know that all 0 code word will always be a valid code word. All 0 code word will always be a valid code word. But there is a property for Hamming code as well. Like Hamming code is a linear code. That means Hamming code will follow this property for sure. That all 0 code word will be a valid code word for sure. So this property it will follow for sure, right? But along with that, in Hamming code, another property is there that all 1 code word will also be a valid code word. But there is a catch. This property will not always be applicable. Okay, what catch is there that I will explain you. Later on I will tell. But for Hamming code, there is a property that all 1 code word will always be a valid code word. That means one more code word I already know. What that would be? All ones. This is not always applicable. But in this question, by default, they have considered this as applicable. Now, when this would be applicable, that I will tell you later on. But let's solve this question first. So, all ones will be a valid code word for sure. That means this I am telling as 9. So, for with respect to 1111, my code word would be 1111111. Okay. Now, what I can do? I can do some XOR operation, and finally, in the end, I can get 1. So, what I need to check? I need to check for 1001. I need to check for 1001, and I need to check for 0100. So first let's check for 1001. So my target is getting 1001. So with 1111, I need to XOR something that I get 1001. What it should be? Sir, you do this XOR operation. So with 1111, you do the XOR of 0110. So if you do C3 XOR C9, if I do C3 XOR C9, what I will be getting? C3 XOR C9. So you can see here, this would be 0, this would be 1, this would be 1. So 1, 0, 0, 1, right? This would be your C10. C3 XOR C9, which is your C3 XOR C9. So if I do C3 XOR C9, I am getting 0, 1, 1, 1, 0, 0, 1. But what is given? 1, 1, 0 is given. That means, sir, this is wrong. So only option left is C. That would be correct. But we will see everything. I haven't even tell that what was the solution given by NPTEL. Now what I need to make? I need to make 1011 now. 1011. and I will add it up with 1 1 1 1. That means what I need to add? Sir, you need to actually add 1 0 1 1 you need to make, no? So you need to add 0 1 0 0. What I need to add? 0 1 0 0 0 1 0 0. So C7 XOR C9. So this was with respect to 1 0 0 1. So if I do C7 XOR C9, what I will be getting? C7 XOR C9. So C7 C9. So 1 XOR 1 1 XOR 1. What you are getting? 0 0 0. C7 XOR C9. So 1 0 1 1. So this you are getting as C11, which was C7 XOR C9. So with respect to 1 0 1 1, you are actually getting 0 0 0 as the parity bit. Is that mentioned? Yes, sir. This would be the answer. Okay. So the professor who set up this question, I think he would have solved in this manner. But in NPTEL, like, professors are not giving the solution. PhD scholars are giving the solution. So the PhD scholar who gave the solution, he gave the solution in this manner. So what I am writing down? I am writing down NPTEL solution. So what was the NPTEL solution given? So what he said? He said that there is a random logic, right? He said that this was your data word and code words. These were your data word and code word. So you can see that your code word is actually in this pattern: P1, P2, P3, D1, D2, D3, D4. So basically this is the pattern that you are getting: 0 1 0, 0 0 1, 1 0 0, and here you are having 1 1 0 0, 1 1 1 0, and 0 1 1 0. Now he says that every parity bit could be written in this manner, that P1 could be written as D1 XOR D2. If you do D1 XOR D2, right? 1 XOR 1 0, 1 XOR 1 0, 0 XOR 1 1. So that means P1 you are getting. So you can write it down as D1 XOR D2, and here he added D4 as well. Okay? Because D1 XOR D2 XOR D4, what you will be getting? 1 1 0, that would be 0. 1 1 0, that would be 0. 0 1 0, that would be 1. What about P2? D2 XOR D3 XOR D4. 1 0 0 would be 1. 1 1 0 would be 0. 1 1 0 would be 0. So D2 XOR D3 XOR D4. I will tell you whatever the doubt that you are having, have some patience. Now then for P3 he said that if you do D1 XOR D2 XOR D3. D1 XOR D2 XOR D3. Okay. So now you are able to follow up that this is the equation of P1, this is the equation of P2, this is the equation of P3. So now you check all these four options. You put 1 0 0 1, you see what kind of parity bit you are getting. You put 1 0 1 0, what kind of parity bit you are getting. So in that manner you check, only one option will be satisfied, that would be option C. So then he said that basically you take your data bit as D1, D2, D3, D4. You take that data bit as 1 0 1 1, right? That is 1 0 1 1. You take it as 1 0 1 1. Then you find out your P1. Your P1 would be D1 XOR D2 XOR D4. D1 XOR D2 XOR D4. So 1 XOR 1 XOR 1, that would be 1. What would be your P2? D2 D3 D4. D2 D3 D4. Arre bhai. D1 D2 D4. No. So P1 would be equal to 0. Sorry guys. D1 D2 D4. So 1 XOR 0 XOR 1. That would be 0. What about P2? D2 XOR D3 XOR D4. D2 XOR D3 XOR D4. That would be 0. And what about P3? D1 XOR D2 XOR P3 is 0. So that means this is the answer. Now what will be the issue here? This is the solution that is given. Now what one can argue? The argument could be given. This D4 is 0 only, no? D4 is 0 only. Why you are using D4 then? What someone will say, use P1 as D1 XOR D2. Use P2 as D2 XOR D3 and use P3 as D1 XOR D2 XOR D3. These three equations are also satisfying these three guys. These three equations are also satisfying these three guys. And if I don't use this property, forget about this property. If I don't know that all one code word would also be a valid code word, like if you take till this point, then all these code words would be satisfying these P1, P2, P3 condition. What I mean to say is that you take any code word. Let's just say I take this code word 0010, 0010. So what would be the parity bit? D1 XOR D2. What that would be? 0. D2 XOR D3, that would be 1. And D1, D2, D3, that would be 1. So parity bits would be 0, 1, 1. Are we getting the same thing? For which one? For 0, 0, 1, 0. For 0, 0, 1, 0, we are getting 0, 1, 1. We are getting 0, 1, 1. So all the codes will satisfy. All these 8 codes will be satisfied. Here we applied another condition. What we applied? That all ones code word would be a valid code word. But sir, we never studied this particular property. I don't even know about this property. Then what I could have done is that I could have taken P1, P2, P3 in this manner, and let's check now what answer we are getting. If I am taking P1, P2, P3 in this manner, and my data word is D1, D2, D3, D4, that is 1, 0, 1, 1, then what would be my P1? P1 would be D1 XOR D2, D1 XOR D2, that would be 1. What would be my P2? P2 would be D2 XOR D3, that would be 1. And what would be my P3? P3 will be 1 XOR 0 XOR 1, that would be 0. That means your answer is coming out to be 1, 0, 1, 1. So using these 3 logics, if I am writing down this thing, that is also fine. If I am writing down this thing, that is also fine. So why this is correct and why this is not correct? Why? So this solution was not satisfactory for sure. There is no doubt about it. Whatever the solution that was given, that was not satisfactory at all. They just matched the answer. But whenever the question is coming on Hamming code, whatever that we have studied till now for Hamming code, we always assume that our Hamming code that we are using, that Hamming code is even parity Hamming code. Even if it is not mentioned in the examination, by default you will always consider even parity Hamming code. What is the meaning of even parity Hamming code? The meaning of even parity Hamming code is that whatever the parity bit that you are generating, let's just say this parity bit that I am generating, that is P1 equals to D1 XOR D2 XOR D4. Okay, so this parity bit I am generating. Now you do the P1, okay, and you do this XOR with D1 XOR D2 XOR D4. You do this particular thing, answer should be equals to 0 only. And which would be 0? Because this D1 XOR D2 XOR D4, that is P1 only. So P1 XOR P1, what that would be? That would be 0 only. Right? So by default, we will always take even parity Hamming code. Right? So even parity Hamming code says that whatever the parity bits that you are generating, you actually do the XOR operation of these parity bits with the generated parity bits. Basically, you do P1 XOR D1 XOR D2 XOR D4. It should come out to be 0, which will surely come out to be 0 only. Right? Just one second. Yeah, so what I was saying. So by default, it will be applicable that all ones will be a valid code word. Because you know that P1 XOR D1 XOR D2 XOR D4 would come out to be 0 only. P2 XOR D2 XOR D3 XOR D4 would come out to be 0 only. P2 XOR D1 XOR D2 XOR D3, that would also come out to be 0 only. Sir, in this case as well, it would come out to be 0 only. That means P1 XOR D1 XOR D2, that should come out to be 0 for sure. P2 XOR D2 XOR D3, that would come out to be 0 for sure. Are you able to understand why they will be 0 only? Very simple, no? Like P2 XOR with D2 XOR D3. What is D2 XOR D3? That is P2 only. So in all these cases, P1 XOR D1 XOR D2 XOR D4, that would be 0. This would be 0. So for both of the logics, both of the Hamming codes are even parity Hamming code. That means all ones should be a valid code word. This should be a valid code word. 1 1 1 1 1 1 1 1 in both of the cases should be a valid code word. This is our required condition. What is the condition? That this should be a valid code word. Now if I put these values using this coding scheme, what I mean to say is that if my P1 is D1 XOR D2 XOR D4, that means 1 XOR 1 XOR 1, that would be 1. What would your P2? D2 XOR D3 XOR D4, 1 XOR 1 with XOR 1, that would be 1. And what would be your P3? 1 XOR 1 XOR 1, that would be 1. That means your parity bit is actually coming out to be 1 1 1 and your data bit was 1 1 1 1. That means 1 1 1 1 is a valid code word. So this coding scheme is fine. Again, let me repeat one statement. All ones will be a valid code word in Hamming code for sure. That's it. This is the bottom line. Forget about even parity Hamming code. Forget about it. By default, always even parity Hamming code would be there. And what is the meaning of even parity Hamming code? That P1 XOR P1 should be 0, and which is pretty obvious as well. That would be 0 only, right? In this case as well, sir, this property is being satisfied. That means this coding scheme also tells that you are a even parity Hamming code. Here also you will say that this is a even parity Hamming code. That means they should also satisfy that 1111111 should be a valid code word. But what really happens if I use this coding scheme? Then what will be the value of P1? So that would be D1 XOR D2, 1 XOR 1, 0. What will be the value of P2? D2 XOR D3, 0. What will be the value of P3? D1 XOR D2 XOR D3, 1. So with respect to 1111, your parity bits are actually coming 001. That means 1111 1111 is not a valid code word for this coding scheme. It is not a valid code word for this coding scheme. They are not having any relation. That means this coding scheme is actually wrong. Whatever the coding scheme that you have made, in all the previous example that we have seen, okay, we have studied the whole chapter. In the whole chapter, whatever the value of P1, P2, P3 we have written down. Take your data bit to be 1111. In any example, take all the data bits to be 1111. You would see that P1, P2, P3 would always come out to be 1. Any example you can take. Take all the data bits to be 11. Take all the data bits to be 11. Then surely your parity bit would be 111 only. No one can stop it. Is that understandable to you? That means all ones will always be a valid code word. Although it is defined for even parity Hamming code, Hamming codes are by default even parity only. That means all ones will be surely a valid code word. So you cannot actually use this coding scheme. You can use this coding scheme. If you have seen, you might have studied from some other platform. In your coaching center, this solution would have been given, but they never told you that why this cannot be the actual answer. Some guy may think that, sir, using this logic, I will say this is my answer. But if it is a Hamming code, then along with this logic is also present. This particular logic is also present. Now, if you consider these 4 logics all together, then you would see that only this is the possible coding. Okay, so this is the property of Hamming code. Property of Hamming code, this is very, very important, that says that all ones are also a valid code word. Okay, and I'm very, very soon expecting that this kind of question would again come up. So forget about all these things. Like, it is not that easy that I will be able to write down P1, P2, P3 just by observing it. Not that easy. So what I would do, sir, whatever that is given, based on that I can make some code words. Along with that, I know that I can use this particular thing. This is always there with me. If this is with me, then my life will be easier, right? Because if this is with me, then something I can do, something I can get out of it, and I can make more code words as well. Is that understandable to you or not? So this line is actually very, very, very important. Okay, and very soon, if the question is coming on Hamming code, somehow they will relate it to this particular question. So what I feel is that when the professor, whoever framed this particular problem, he would have solved the problem in this manner. Okay, but the research scholar, he made the solution in this manner. He was also right in his place. I'm not saying he is wrong, but the reasoning was not clear to a lot of students, that why this is not possible. This is not possible because it is not following 1111 1111. It should have followed 1111 1111. Then only this would have been possible. So now everything about this question is crystal clear, and the conclusion that you take out of this particular question is that 1111 1111 will be a valid code word. Using this particular property, I would be able to do something pretty good. Say yes or no. Okay, yeah, that's it. So this was the question, and now we have ended our complete digital communication system. Okay, started with random variable, random process. Then what we studied about digital communication system. So first we started with sampling, then quantizer, encoder, line coder. We studied about the bandwidth requirement. We studied about the channel, then receiving filter. We studied about meshed filter. We studied about decoder. Everything we studied. Then we came to information theory. We studied about entropy, mutual information, channel capacity. Then we studied about source coding, channel coding. Every single thing we have studied, and not a single question would be coming out of it. Okay, and I hope you have enjoyed the actual communication system. not mathematics, nothing, pure intuition, pure learning. Okay, so if you have enjoyed, you need to comment down. If you have reached to the last of this video, you can let me know in the Telegram group, or you can let me know in the WhatsApp group as well, that how did you like this digital communication system, because mostly you are coming here for digital communication system, right? For analog communication, like everyone is comfortable, that is very straightforward. You are coming here for digital communication system, I know. So if you have came here, and how did you like it, that you need to tell. Okay then, yeah, thank you very much, happy learning.